Okay, so let's begin with this. This is the next topic. Let's start with vectors. So what are vectors? First of all, you need to be able to represent vectors. Vectors are things that have both magnitude and direction. So how do you represent vectors? You can represent them using a line like this that is going from A to B. That's vector AB. Or you can represent them using these letters like this, the vector AB. We could write it like this with an arrow on top. Okay. A is the starting point of this vector, B is the end point of this vector. If you just have AB written, that means the length of AB. Okay, so make sure that you understand the difference. When they just represent the length, when they don't have an arrow sign on top, that means they're talking about the length or the magnitude. For vector, it's necessary to have this arrow sign on top. You need to be able to add vectors. For example, AB plus BC, that is equal to AC, right? Similarly, you can add multiple vectors as well. If the starting point, if the end point of the first vector and the starting point of the next vector that they match, you can just write down the final vector as the starting point of the first vector and the end point of the last vector, like this, right? You've done this in O levels as well. How to add vectors like this. Then there's concept of negative vectors. If you've got a vector AB, if you want to reverse the direction for that, you can put a negative sign with that. AB vector is equal to minus BA. They're both the same, right? XY vector is minus 5x. Then you have the concept of position vector. What's the concept of position vector? It's the coordinates of that point written in vector form. So for example, if you have a point P, that's this 3, 2. What's the position vector of this going to be? You say it's 3, 2, like this in 2D. But mostly we will be dealing with three-dimensional vectors. I'll show you those as well. But the idea is, we say, starting from the point O, how can we reach the point P? We have to go 3 units to the right side, 2 units up, and we'll reach that point. We write that as this vector, and the first number represents the x component, the second number represents the y component. That's the position vector of that point. So if you write the coordinates of a point in vector form, you can say that's the position vector. And the format, the notation that we have for this is O and then that point, because that tells you from origin, how can you go from the origin to that point? By moving some units in the x direction and y direction and z direction. What is that? That's the idea of position vector. Now, this is very important. A result from position vector that you need to remember. If you have any vector like this, AB, for instance, you can write that in terms of its position vectors. In terms of the position vectors of the 2 points, A and B, you would say AB vector is the same thing as OB minus OA. We'll be using this a lot. Keep this in mind. If you have any vector, if you want to write that in terms of the position vectors of the 2 points, you would say it's the position vector of the second point minus the position vector of the first point, right? So AB vector would be OB minus OA, MN would be ON minus OM, FG would be OG minus OF, and so on. Okay, so that's how you can write any vector in terms of the position vectors. Then mostly, in fact, always, in our case, we will be dealing with 3-dimensional vectors. So that means we'll have 3 components. We'll have X, Y, and Z, all of these components. Now, we need to be able to find magnitudes of vectors. Now, in 2D vectors, magnitude was fairly straightforward. You can just use Pythagoras for that. That's x squared plus y squared and square root of that. In 3D vectors, we have a similar formula as well. There's a background to this where this comes from. But this is the formula that we've got for magnitude of a 3D vector, and that looks like this. If you have a vector in this form x, y, z, its magnitude is given by square root of x squared plus y squared plus z squared. Okay, so you just square each component, add them up all together, and then take square root of that, and that gives you the result. Now, this represents the length of the vector, right? Magnitude of the vector or the length of the vector. That's what this represents. How do you add or subtract vectors? If you have to add or subtract vectors, you just add and subtract the like terms, x component with x component, y with y, z with z. Okay. Multiplication by a number. If you have a number, you might want to multiply that by a vector. All you have to do is multiply that number with each component. So -2 will have to be multiplied with all of these components. Okay. And that gives you the result. How do you multiply 2 vectors? There are 2 different ways of multiplying vectors. In our syllabus, we only have one of them, and that's called the dot product. The other is cross product. You might have seen that in some marking schemes. That's not required anymore. It used to be one way of doing some problems earlier, but now in the updated syllabus, you don't have to do that anymore. There's only one type of multiplication that you need to know of, and that is dot product. It's also called a scalar product. You should be familiar with this terminology. Sometimes they use this in questions. They talk about scalar product. You should know that they're talking about the dot product. Okay, how do you multiply two vectors using the dot product? You just multiply corresponding components. For example, if you have these two vectors, you want to multiply them. What you do is you multiply the x components, y components, z components, and you add the results, and that gives you the dot product. Okay, so in general, we can say if you have a vector like this, a1, a2, a3, and b1, b2, b3, the dot product would be this: a1, b1 plus b2, a1, a2, b2 plus a3, b3. Right, that's the dot product. This is one definition of dot product. There's another way of defining dot product, and that's given in the formula sheet as well. And that's this: a dot b is equal to modulus of a into modulus of b, or in fact, magnitude of a and magnitude of b into cos of theta. Theta in this formula represents angle between vectors a and b. Okay. If you rearrange this, you can get this formula that we'll be using a lot to find angles between vectors, and that's cos theta equals a dot b divided by modulus of a into modulus of b. This is given in the formula sheet. You can rearrange that to get this, and you'll be using this to find angle between any two vectors. This is the only formula that we have for finding angle between vectors in this topic. So whenever they talk about angle, this is the formula that you'll be using for that. Okay. For example, if you want to find acute angle between these two vectors, a and b, all you have to do is input values in this formula. Cos theta equals a dot b divided by modulus of a into modulus of b. You evaluate the dot product. You evaluate the magnitude of a, the magnitude of b. Input values in the formula. When you do that in the formula, from the formula, you get an obtuse angle. But why? Because the dot product was negative. Cos is negative in the second coordinate, so you end up getting an obtuse angle from your calculator. They wanted an acute angle. Now, if you had two vectors like this, a and b, if this is the obtuse angle, what will be the acute angle between them? We could write the angle in both ways, right? We could say obtuse. We could write 126.5, or this acute angle that will be 180 minus 126.5. That's this. Both of these are angles between two vectors. But in this question, they have specified that they want an acute angle. So what you would do would be, if you're getting an obtuse angle, you'll subtract that from 180 and write down 53.5 as the result in this case. Okay. In dot product, we multiply corresponding components and then add them up together. Yes. So that's what we did here. Minus 1 into 3 plus 2 into minus 3 plus 6 into 7. And that gives us the result. That's 33. That's the dot product. Okay. All right. Now, in some cases, they will specify if they want an acute angle or an obtuse angle. In that case, if you're getting one, you'll do 180 minus that to find the other one. Okay. Now, sometimes they won't specify anything. In that case, any of them is going to be okay. However, if they want angle at a specific point, for example, if they say something like this, find the angle ABC such that the AB vector is equal to this and BC vector is equal to this. Okay. Now, we want to find the angle at the point B. So if you were to represent this vector, let's suppose the vectors look like this, AB and BC. Now, if you were to randomly find angle between these two vectors, the formula could give you any of the two angles. Which two angles? If I were to extend AB like this and extend BC like this, one angle between the vectors is this, and the other is this outer angle. We have to find the angle ABC. Which angle is that? That's this yellow angle that's highlighted, and that's an obtuse angle. We do not want the acute angle, this one. That's not what we want. We want the obtuse angle. If it looks like this is the angle that we want, not the outer one. But in this question, they have not specified that the angle is obtuse or acute. So we don't know whether it's going to be obtuse or acute. In such cases, we have to be careful. The two vectors that we use, they have to be in a particular order. So if the angle is at the point B, the vectors that we use, both the vectors should either be starting from B or both of them should be ending at B. Okay, one of these two cases can be used. The vectors that are given, they are A, B, and BC. we cannot use them as it is because one of them is ending at B and the other is starting from B. That will give us the wrong angle. So what you should first do is, you should first make sure that one of these conditions is met. Either both vectors start from B or they end at B. Okay, so in this case, we could say, let's convert BC vector to CB. Okay, how do you do that? By multiplying this vector by negative. So it becomes -3, 2, and -1. And now these are the vectors that you can use, AB and CB, apply that formula, and the angle that you get from this will be the correct angle. If you were to do it without converting it to that form, you would end up getting an acute angle, and that will be incorrect in this case. Okay, so when you have a specific point given at which you have to find the angle, you need to make sure that this condition is met before you input values in the formula. Both vectors should either start from that point at which you're finding the angle, or they should both end at that point. So the alternative in this case could be that we could have used the vectors BA and BC, right? So any of these combinations will work. Now, the angles in this topic, you could give them in degrees as well. That's okay, that's not a problem. In vectors, you can use degrees or radians, both of them, they work. Okay. A lot of times they use degrees here. In case in the question they use degrees, then you have to use degrees. Otherwise, it's your choice to use any of them, and that will be fine. Perpendicular vectors. How do we know if two vectors are perpendicular? If two vectors are perpendicular, their dot product is going to be equal to 0. Because in the formula, if the angle is 90, cos of 90 is 0. So from that, we get this result that the dot product is equal to 0. So if the dot product of two vectors is equal to 0, that means the vectors are perpendicular. And it works both ways. If you know that two vectors are perpendicular, that means their dot product should be equal to 0. And this is the result that we have to use quite often. So you need to remember this. When two vectors are perpendicular, their dot product is going to be equal to 0. Okay. If the dot product is positive, the angle that you would get from the formula will be an acute angle. Why? Because if the dot product is positive in the formula, you'll get cos theta equal to a positive value. And cos is positive in the first quadrant. And if the dot product is negative, the angle that you would get would be obtuse because cos is negative in the second quadrant. Okay, so in the formula, if A dot B equals 0, that means the angle is 90. If it's positive, the angle is acute. If it's negative, the angle is obtuse. Okay, now if you have to figure out if two vectors are perpendicular or not, and we have these two vectors given, how do you do that? You just find their dot product. If the dot product turns out to be 0, that means they are perpendicular. If the dot product was not equal to 0, then they would not be perpendicular. Okay. How do you figure out if two vectors are parallel? If two vectors are parallel, that means one should be a multiple of the other. You should be able to write one as a multiple of the other. For example, if you have these two vectors, P and Q, can you multiply one of them by some number to get the other vector? Now, a lot of times you can just think of it in your head directly, and that will work. Look at the smaller vector, as in the vector that has smaller values. This one has smaller values, right? Now, what do you multiply -1 to get -1 by to get 4? You get multiply that by -4. So you think of whether multiplication with -4 is going to give you the second vector for all the components. 5 into -4 also gives you -20. 2 into -4 also gives you -8. That means if you multiply the vector P with -4, that is equal to Q. So Q can be written as a multiple of P. These two vectors are parallel. Okay, so if you can think of it in your head like this, that's great. You can do it quickly like this. Alternatively, what you can do is something like this. You just divide corresponding components. 4 divided by -1. So the bigger number, divide the vector having bigger numbers with the other vector and see what you get from that. 4 over -1, -20 over 5, -8 over 2. All of them turn out to be -4. If all of them are equal, then that means they're parallel. You could do the division the other way around as well, but that will give you fractions, so it will make things more complicated. So it's better to just divide the bigger numbers by the smaller numbers. If all of these divisions give you the same result, then that means the vectors are parallel to each other. Okay. So two vectors A and B are parallel if one can be written as a multiple of the other. For example, A equals K times B or B equals K times A. That's how you prove or figure out if two vectors are parallel or not. For example, if you have these two vectors, and you have to figure out if these vectors are parallel or not. You can check if one can be written as a multiple of the other. 10 over minus 5 is -2, -4 over 2 is -2, 21 over 7, however, is 3. All of these numbers are not the same, so we say they are not parallel. Okay. What is a unit vector? Unit vector is a vector that has a magnitude of 1. Any vector that has a magnitude of 1, we call that a unit vector. Okay. Now, you will have to sometimes find the unit vector parallel to a given vector. For example, if you have this vector given, -3, 4, and 0. Okay. Now, this vector, if you find the magnitude of this vector, that is actually 5. Okay. 3 squared plus 4 squared, square root of that gives you 5. We want a vector that is parallel to this. However, it has a magnitude of 1 instead. Okay. Now the magnitude of A was 5. We want a vector that has a magnitude of 1 in the same direction. How can you do that? You can just divide this by, or in fact, we don't call this division. We multiply this by 1 over 5. We multiply this vector by 1 over 5, and that will change this vector in such a way that its magnitude becomes 1. And since it's just a scalar multiple, we know that it's in the same direction. It's parallel to that original vector, and we would get that unit vector in that direction. For example, in this case, all you have to do is, for the unit vector in that direction, we say 1 over 5 times -340. Now, this is not very important, the notation for this, but just for your information, sometimes they might use this in a question. For unit vector, we use this notation. We have a hat on top of that vector. So we have vector A, unit vector in that direction will be A hat. Okay, that's the notation that we sometimes use for this. So how do you find unit vector in any direction? If the vector is x, y, z, unit vector in that direction would be 1 over the magnitude of A times that vector. Okay, so find the magnitude of the vector, take reciprocal of that, multiply that by that original vector, and that will give you the unit vector in that direction. Okay. Now, sometimes there's a variation of this that comes. So unit vector is a vector that has a magnitude of 1, right? But they could give some other magnitude as well. For example, you want to find the vector with magnitude 24 that is parallel to vector A, such that vector A is this. Now, how do we think about this? First of all, find the magnitude of the vector A. What does that turn out to be? The magnitude of the vector A turns out to be 6. We want this magnitude to be 24. Earlier, we were finding unit vector. We divided by 6. We did something like this to the vector, right? And that gave us that resulting unit vector. Now we want the magnitude to be 24 instead of 6. Now, how do you go from 6 to 24? You have to multiply by 4 so that the magnitude becomes 24. So what you do is, to find that vector, you multiply the vector A by 4, and that gives you this, -8, 16, -16. That's the vector in the direction of A that's parallel to A and has a magnitude of 24. Okay. Now, there's another notation that we have for vectors. One is x, y, z, column vector form. You can also write this as xi plus yj plus zk. So for instance, if you have -253, you can write that as -2i, not iota, -2i plus 5j plus 3k. Right? That's another notation that we've got. We've got for vectors. In this case, I, j, and k, they're basically unit vectors in directions, in the x direction, in the y direction, and the z direction. So I is basically 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1. So if you think about it, you can actually, if you input these vectors there, you get that vector back from that. And that's the background for this, but just remember this. If you have a column vector like this, you can write that in ijk form. Put I with -2, j with 5, and k with 3, and that gives you the vector. Now, do not write it as -2i, 5j, 3k. You can't mix up the two forms. That will be marked wrong. Okay, this is not acceptable. You have to use either this, only numbers in column vector form, or just this ijk form. All right. Okay. Now let's have a look at a couple of very quick questions on this. Then we move on to the more difficult part. You have to calculate the angle AOB given these two vectors. OA and OB, they're given in IJK form. The angle that you want is at the point O. So both the vectors that you use, they should either start at O or end at O. So we can use OA and OB, for instance, apply the angle formula, and you get the result. The second part says, the point C is such that AB vector is equal to 2 times BC. Find the unit vector in the direction of OC. Now, how do you do that? First of all, for finding the unit vector in that direction, you have to know what the vector OC is, first of all. Now, this will happen in a lot of questions in the recent papers as well, that you'll be given some kind of ratio like this, and you'll have to find some missing vector from that. Now, one idea that you can use in such questions is, you're given that AB vector is equal to 2 times BC vector. You want to find the vector OC from this, right? How do you do that? You can say AB vector is equal to 2 times BC. AB can be written as OB minus OA. BC can be written as OC minus OB. So just input and just replace AB with OB minus OA and BC with OC minus OB. And now you know what OB is, you know what OA is, only OC is missing. You can just rearrange this, make OC the subject, and you get something like this, and then just input those vectors and you would get the result, right? It involves some algebra, but eventually you get the result without a lot of thinking. Just input values in this and you get the result. The other way is doing it graphically, as we'll do in some questions when you have diagrams given. In this case, there's no diagram given. So it's much more efficient or much easier to just write it like this, convert it to the position vector form, and then find the missing vector OC from that. Now, once you have OC, this is what the vector OC looks like. Okay. Then what about the unit vector in that direction? You find the magnitude of OC. And then you say 1 over 12 times that vector. 12 is the magnitude, so 1 over 12 times that vector, that's going to give you the unit vector. This is the unit vector in the direction of OC. If you were to try and find the magnitude of this vector now, that would turn out to be 1, right? It's because it's a unit vector. All right. This would be an alternative way of doing this, that you think of a diagram, right? AB is equal to B, 2 times BC. What that means is, if you were to draw these vectors like this, AB and BC, they're parallel to each other, right? They are on the same line, in fact, because B is common, and they have the same direction, because since they're scalar multiple, they have to be on the same line. So if we had A here and B here, for instance, then what's the ratio that we're getting? AB is 2 times BC. So if this is 2 parts, then BC is 1 part, right? So you can make a diagram like this. That would be an alternative. And then try to find OC from that. So you can go from O to A, then A to B, and then B to C. Find those vectors, input their values, and you get the result from that. A bit more thinking that you need to think a bit more here. I would recommend that you just use that other method that we did earlier, and that will work. Although it requires a bit more algebra, but that works eventually. Now, sometimes you get very complicated diagrams like this, and using those diagrams, what you have to do is you have to find some vectors. For example, look at this diagram. It's a cube. It's a cube. Cube means all the sides are equal. They're all 4 lengths, 4 units. They're all 4 units each. We have to find the vector PR and PQ. Now, the question says, the unit vectors I, J, and K are parallel to OA, OC, and OD. Now, these actually give you the directions. I is this direction, J is this direction, and K is this direction. And then the magnitudes, the lengths of these sides, what are they? They're all 4 units. So using I, J, and K, you could basically say the vector OD, what would that be? That will be 4 times K, okay? Because the direction is K, magnitude is 4, that will be 4 times K. You can say the vector OD in this case is 4K. Similarly, vector OA, what would that be? The direction is I, and it's 4 units, so we say that's 4I. And then OC, that's J direction. Length is 4, that will be 4J, right? So when you're given directions like this, unit vectors in these directions, I, J, and K, and you know the magnitudes of those sides, you can just multiply the magnitude with that unit vector, and that will give you the complete vector in that direction. So you've got this information given. You want to express PR and PQ in terms of I, J, and K. Now, when you have a diagram given like this, it's often a good idea to look at the diagram and see how you can go from the starting point to the end point. You have to start from P and end at R in this case. So how can you go from P to R? This is the point P, and this is the point R. One idea could be that you could go from P to A. P is the midpoint, so this vector would be 2i. And then you can go from A to the midpoint of AB, and then point R is right on top of that. So you go 2i units here, 2j units here, because that's the j direction, right? If this is j direction, this is also j direction. And then you go vertically. Again, R is in the middle, so that in the vertical direction is also going to be just 2 times k, because the vertical direction complete is 4k. Half of that will be 2k. Just add all of them up, and that gives you the vector PR. Let's see what that turns out to be. Okay, it's stuck. So this is what it would look like. You can say, if you have to go from P to R, if you mark this point as X, you have to go from P to A, then A to X, and then X to R on this diagram. Those vectors are 2i, 2j, and 2k. And that's the vector PR. Similarly, if you have to go from P to Q now on this diagram, you could follow, for example, this path, P to O, then O to D, and then D to O. You know these vectors? P to O will be minus 2i, because it's in the opposite direction of I. Minus 2i, it's 2 units, then 4k, and plus 2j. And that will give you the vector PQ. Okay, so you can follow the path in the diagram to find that vector that you're looking for. Very similar to what you used to do in O levels as well. There you used to have 2D vectors. Now we have 3D vectors, so the diagrams are also 3-dimensional. You just have to find a path in the diagram that gets you from the starting point to the end point. Okay, the second and third part, they just want you to find the angle, and the last part is perimeter. Perimeter means you find the lengths of all sides that are there, and then just add them up together. So triangle PQR, you can find the length PQ, find the length QR, find the length PR, and then add them up together. That will give the magnitude. That will give the perimeter. How do you find each of those lengths? Using the magnitudes. In the second part, you would have already found the magnitudes of PQ and PR. You can also find QR then, and that gives you the perimeter. You can have a look at this working. It's pretty straightforward. And that's how you could do it. Okay. Similarly, you can sometimes have a bit more complicated diagram. For example, you've got this. You can have a look at this shape. It's a symmetrical shape with DE on top, exactly in the middle, like this. If you were to draw a line here horizontal, this DE is right on top of that. Okay, so it's like a Toblerone, right? It's that shape roughly. We've got I, J, and K vectors given in these directions. I is this direction, J is this direction, and K is the vertically upwards direction. So it's a 3D figure. K is vertically upwards. And they're saying some of these lengths are given. OA, CB, they are 14. These are 8. Top of the roof is 5 meters. Above the base, that means this vertical height, that is 5 meters, right? The sloping edges OD, CD, A, and BE, they're all equal in length. So these edges, this, and this, they're all equal. And that tells you that the figure is symmetrical, right? We have to express OD in terms of I, J, and K and find its magnitude. So we have to start from O and end at D somehow. How can we do that? This is one possible path that we can follow. This complete length is 14 meters. Now, because of the symmetry of the diagram, they told us that DE is 6 meters. If D is 6 meters, corresponding to that, if we were to mark 2 points here, let's call this point X and let's call this point Y, then this could be also 6. Then what are we left with on the sides? If this is 6, the figure is symmetrical. We have 4 units left on the, we have 8 units left after 6, right? So 14 minus 6 is 8. 4 will be on the left side, 4 will be on the 4 will be on the right side. That means from O to Y, this distance is 4 units. And then we could find this point exactly below the point D. Remember, it's 3D. This rectangle is horizontal, and then that roof is on top. It's a 3D figure. So you go from this point Y to this point X. That's exactly below the point D. That's 4 units because this total length is 8 units. What direction is that? That's J direction. So you go 4 units in J direction, you go 4 units in I direction, and then you go vertically upwards from X to D. That's 5 units, and that's in K direction. And that gives you the result. You can see what that is. OY, that's 4I. YX, that's 4J. XD, that's 5K. Not a lot of working involved, but thinking process here is what gets you those 4 marks. You have this vector, then you have to find the magnitude. That's just a simple formula. The magnitude turns out to be square root of 57. The second part just requires the use of that angle formula, and you get the result from that. Sometimes you can have complicated calculations to make like this. This is how it would work in this case. You can have a look at this again in your own time as well. Now, sometimes they say, you have a straight line like this. So they give you 3 points on a single line, on a straight line. And then they ask you to find something based on that. If OAB is a straight line, these 3 points lie on that straight line. So like this, as shown here, we have point O here, point A here, point B here. Now, when that is the case, the 3 possible vectors that you can get from this are vector OA, OB, or AB. Since all the points lie on the same line, these 3 vectors will have the same direction. They will be parallel to each other. They have the same direction. So OA vector, OB vector, AB vector, any vectors that you can make using those 3 points, they will be parallel to each other. So they will be scalar multiple of each other. So in this case, that means the vector OA that's given to be this, OB is given to be this. All of these points lie on the same line. They have to be in the same direction. Okay, these vectors have to be in the same direction. That means one of these vectors should be multiple of the other. So you can see that in the diagram. 1 into 2 gives you 2. So for the other ones, also it should be true that you multiply them by 2 and you should get the other vector. For example, 1 into 2, that should give you the value for P, that's 2. So here as well, if the value for P is 2, you multiply that by 2, and that gives you 4 as the result. So multiplying the vector OA by 2 gives you that result. Alternatively, if you find it difficult to think of this in your head, just make those, do those divisions as I showed you earlier. This is 4 over P, this is 2 over 1, this is P over 1. They should be equal to each other, right? 4 over P should equal 2 over 1, and that should equal P over 1. That gives the value for P, and that turns out to be 2. Once you have that, then they just want you to find the unit vector in that direction. That's really straightforward. In the case where OA is perpendicular to AB, find the possible values of P. Now, in the first part, they said in the case where this is a straight line, right? So that was one case. In the second part, that's a different case now. So the value of P that you find in the first part, that's no longer relevant. The second part says, if they are perpendicular to each other, OA and AB are perpendicular to each other, find the possible values of P. How do you do that? You could say, let's find the vector AB first of all. That's OB minus OA. In terms of P, that turns out to be this. So now we've got vector AB, and we already had the vector OA. They have to be perpendicular to each other, right? OA and AB have to be perpendicular to each other. If they're perpendicular to each other, what does that mean? Their dot product should equal 0. So we find their dot product, put that equal to 0, and that gives us the corresponding value for P. Okay, you can simplify that, find the value of P from that. And then in the third part, they say, in the case where P is equal to 3, and the point C is such that OABC is a parallelogram, find the position vector of C. How do you do that now? P is equal to 3. So now they've given you the value of this constant. And the third part, they're saying that's 3 now. OABC is a parallelogram. What you can do is you can make a parallelogram like this. You can say, okay, let's suppose we have a parallelogram that looks like this, OABC. Now, in a parallelogram, opposite vectors are always equal to each other. So if you have the point O, that's the origin. You have the point A, you have the point B, right? You have vector OA, you have vector OB. What you can do is you can say, use any of these vectors. For example, OA should be equal to CB vector. Or you could say OC is equal to AB vector. Since you want to find the position vector of OC, you could use this. You could say OC vector is the same as AB vector. right? Opposite vectors have to be equal to each other. So you say OC is equal to AB, and that gives you the vector OC. That's the position vector of the point C. So if you have a parallelogram, remember, if there's any one point missing, all you have to do is just equate the opposite vectors. Okay, equate the opposite vectors, and that will give you the result. Whatever is missing, you can find that using that. Now, the major part of this topic is equations of lines and how to work with them. So vector equation of a line, that looks like this. So this is the equation of a line in coordinate geometry, right? Y equals mx plus c. What did that equation used to represent? If you had a line like this, and the equation of this line is y equals 5x plus 2. If this is the equation of that line, what that means is this equation represents every single point on the line, right? That's very important to understand. This equation represents every single point on the line. So if you were to input x or y value for any point here, the equation will satisfy. And for finding any particular point on the line, you can just put a value for x. For that, you'll get the corresponding value for y. So putting different values of x in this equation gives you different values of y, and that way you can find every single point on the line that you have. So this line represents every single point on the line. This equation represents every single point on the line. Similarly, we can have equations of lines in 3 dimensions as well. We call them vector equation of a line. That's the form that we have. And this is what the standard form looks like. R equals a plus lambda d. That's the standard form for equation of a straight line in 3 dimensions in vector form. Now, what do these numbers, what do these notations represent? R is equal to a plus lambda d. R equals a plus lambda d. A could be any point on the line. So we need to know one point on the line. It's the position vector of any one known point on the line. D is the direction vector. Direction vector means any vector that is parallel to the line. That will be the direction vector for the line. So in order to write down the equation of a line, we need to do these 2 things. We need the position vector of any one point on the line. That's number 1. And we need the direction vector of the line. If we have these 2 things, we can write down the equation of the line. Now, before we talk about the other ones, let me show you how the equation might look like. For example, if you have an equation, have a line that is parallel to this vector, and it passes through this point, it's written in coordinate form here. Find the equation of this line. How can we do that? We can say the position vector of this point, what's that? That's minus 7, 2, 3. This point lies on the line. So we could say the equation of the line would be of this form. R equals a plus lambda d, right? A is the point on the line. We put in minus 7, 2, 3 in this place. D is the direction vector. We put direction vector in this place. And that gives us the equation of the line. Now, what does this equation represent? What is lambda here and what is R here? Lambda is basically a parameter that can take any real value. Different values of lambda will give you different points on the line. So in the coordinate geometry equation, when you had something like this and you wanted to find different points on the line, what you used to do was you would input a value for x, for example, x equals 2, and that will give you a corresponding value for y. In this case, that will be 12, for instance, right? When x is equal to 2, the value of y that you get in this case, that is 12. Different values of x used to give you different values of y on the line, and those will be the points that you have on the line. In vector equation, what x was doing there is kind of similar to what lambda does here. Lambda can take any real value, and different values of lambda will give you different points on the line. For example, if lambda was 0, so let's say this is what the line looks like. If lambda is 0, what do you get from that? You get 0 times this, and you're just left with minus 7, 2, 3. So the point that you have is this. Now, this point, we know it lies on the line. It was already given, right? That's the point minus 7, 2, 3. But other values of lambda now can give you other points on the line. For example, if you input lambda equal to 1, that gives you this minus 608. That will be another point on the line. For example, if this was p, then q might be here. Input another value of lambda, maybe minus 0.5. It could be any decimal value, any real value. You can put minus 0.5, and that gives you this. That's another point on the line. If q was on one side, since we're using a negative value now, it will be on the other side, and that will be here. That's the point r. That's another point in the line. Similarly, if you keep inputting different values of lambda, you keep getting different points on the line, such that every single point on the line can come from this equation. It's just that the lambda value will be different at each point. Okay, let's go back there now. So what does lambda represent then? It's a parameter that can take any real value. Different values of lambda, they give you position vectors of different points on the line. Okay, and what does R represent? That's like a general point on the line. It's the position vector of a general point on the line. That's of the form x, y, z. So just like in a straight line equation, if we have in coordinate geometry, if we had 2x plus 5y equals 7, what do these x and y represent? X, y is a general point on the line, right? Every single point on the line is of this form. It's x, y, right? So that's a general point on the line. In vector form, that is represented by R here. So R is basically equal to x, y, z like this, right? That represents every single point on the line. So that's the understanding of the straight line. Now, you will have to find equations of straight lines. For example, if you have this scenario in which you're given that there's a vector OA, there's a point A that has this position vector, and there's a point B that has this position vector. We want to find the vector equation for the line AB. Now, how do we find that? Vector equation for the line AB. No, you cannot. I would not recommend that you use this notation for vectors. As in, why would you do that? You already have two forms, column vector and IJK form. Just stick to them. There's no point of taking risks. Just use one of those standard forms. Okay. Achha. With respect to the origin O, the points A and B have position vectors given by this and this. We want to find the equation of the line AB. Now, let's say the line AB looks like this. Okay. Equation of the line is going to be R equals A plus lambda D. A is any one point on the line, and D is the direction vector. How do you find the direction vector? Direction vector is any vector that is in the same direction as the line, that's parallel to the line. So in this case, we could say the vector AB, that is in the same direction as the line. So we can use that as the direction vector. How do you find AB? AB will be equal to OB minus OA, and that gives us this vector. That's the direction vector of that line now. And now we could say R is equal to A plus lambda D. This is direction vector 2, 2 minus 2. A could be any of those points. You could use this point. You could use this point. It doesn't matter. Both of them will work. So this is one possible equation of the straight line. However, you could use the other point as well. So you could say it's 1, 2, 2 using this other point, and that will also be fine. These two are equivalent equations. Okay. You could also use a different direction vector. For example, you're using 2, 2 minus 2 here. You could have used 1, 1 minus 1. Where does that come from? This is a vector that's parallel to this. 2, 2 minus 2, 1, 1 minus 1. There are multiples of each other. You could basically use any multiple of this direction vector as well. That will also be fine. Okay. So all of these are equivalent equations. Any of these would work, right? Instead of AB, you could also use BA like this. Minus 2 minus 2, 2. That also works. All right. So all of these are equivalent. All of them are acceptable. That's how you write equation of line. However, that's just for understanding that sometimes in the marketing scheme, they have a different form given and you get a different form. As long as it's equivalent to that, that's acceptable. However, in the exam, what you would do would be, you just do it the standard way. You'll find the vector AB. That turns out to be this. You'll just use that as the direction vector. And then A will be any of the points. So to use the point that looks relatively simpler, for example, in this case, this does not have a K component. So that will simplify things for you. So it will be more efficient to use that as the point A. All right. No, so if you're doing everything correctly and you're using any of these vectors, the final result that you get, that will always be the same. You will not get wrong answers from any of them. So any multiple of this is going to work. So if the marking scheme uses, for example, 1, 1 minus 1, and you are using 2, 2 minus 2, both of them will give you the same result eventually. The final result will remain the same. That will not be affected. Okay. All right, so that's how we find equations of straight lines. Now, how do you find angle between lines? Angle between two lines. So if you have these two lines given, L1, let's say L and M, we have these two lines. We want to find angles between these two lines. How do you do that? The direction of the line is represented by the direction vectors here, right? What are the direction vectors? 5, 7, minus 2, and 3, 0, 7. So when finding angle between lines, all that matters is the direction vector. We don't care about what point is used here. That is irrelevant, because this is all that is going to tell you about the direction of the line, and angle comes from the direction of the line, right? So when you want to find angle between two lines, what you have to do is just find the angle between their direction vectors. Whatever is the angle between their direction vectors, that will be the angle between those two lines. Okay, angle between any two lines is given by the angle between their direction vectors. If you had to figure out if two lines are perpendicular, how do you do that? Again, it only depends on the direction vectors. If the direction vectors are perpendicular, then the lines are perpendicular. So you find the dot product of the direction vectors. If that turns out to be 0, then that means the lines are perpendicular. Okay. If that's not 0, the lines are not perpendicular. How do you prove that two lines are parallel? So this is what we just talked about. How do you prove that two lines are parallel? Again, just think about the direction vectors. If the direction vectors are parallel, then that means the lines are parallel. So you just check if the direction vectors, they are multiples of each other. If that is the case, then they're parallel, otherwise they're not parallel. Okay, in this case, we check the ratio, and this ratio turned out to be different. So they're not parallel, the lines are also not parallel. So direction vectors are not parallel, that means the lines are also not parallel. So for finding angles between any two lines, we use their direction vectors. And similarly, for proving or checking if two lines are parallel or perpendicular, again, we just have to use their direction vectors, and whatever is the relation between the direction vectors, if they're parallel, perpendicular, or have some angle, it will be the same for those lines as well. Okay. All right. The next thing is how to find point of intersection between two lines. Now, in 3 dimensions, there can be 3 different cases that you can have for any two lines. In 2 dimensions, if two lines are not parallel, they always intersect, right? But in 3 dimensions, we can have a third case as well. One is that you have the lines that the lines are parallel. The second case is that the lines are intersecting. But there's another case that the lines are not parallel and not intersecting as well. So that means the lines are skew. Okay, the lines are skew. That's the third case. Neither parallel nor intersecting. In 2D, we only had these two cases. In 3D, however, we have this third case as well, that two lines are not parallel, but they still do not intersect. Okay. Now, how do you figure out point of intersection of any two lines? And how do you know if the lines intersect or not? Let's have a look at this example. You've got one vector here, another vector here, and two lines here. You have equation of one line here, another line here. We need to show that L and M intersect. Show that L and M intersect. That's one thing. And also find the position vector of the point of intersection. You have to do these two things. Show that the lines intersect and find the position vector of the point of intersection. How do you do that? How do you find points of intersection of any two lines? You just solve them simultaneously. Any two functions, whenever you have to find their points of intersection, at the point of intersection, what happens is those functions would have the same value, right? Any two functions, when they intersect, that means at this particular point, they both have the same value. So to find points of intersection, the idea is we equate the two functions because they're supposed to have equal values at that particular point. So in this case as well, in vector equations as well, what we do is we say, this is one equation, this is another equation. I would recommend that you write them in column vector form. That makes things easier to understand. These are two equations that you have. What you do is you just equate both of them, right? Because we're looking for points of intersection. Now, when you equate them, you can simplify both sides like this. The left side becomes 1 plus s, 1 minus s, 1 plus 2s. Similarly, simplify this as well. And that gives you 3 equations. If these two vectors are equal to each other, it's necessary that the x components are equal, the y components are equal, and the z components are equal. So if they intersect, then we get these three equations from that. Okay. What we do is we have two unknowns, three equations. We can find the values of these unknowns by solving them simultaneously. Solve any two of these equations simultaneously. You can use 1 and 2, for instance. Solve them simultaneously. And that gives you t equals -2 here, s equals -1. Now, you had to show that the lines intersect. Show that the lines intersect. The lines would intersect if these values of s and t also satisfy the third equation. So whatever equations you have used for finding the values, put them in the third equation that is not used to check if that is also satisfied by these values. So you input s and t in the third equation, and that gives you -1 equals -1. That means that the third equation is also satisfied by these values of s and t. So all three equations are satisfied by these values of s and t. For example, that means that at these values, all of these three components are equal. So the lines therefore intersect because the two vectors would be equal at these two values of s and t, right? So s equals -1, s equals t equals -2. They satisfy all three equations. That proves that the lines intersect. If it happened that these two values did not satisfy the third equation, that would mean that there are no values of s and t that satisfy all three equations at the same point, at the same time. Then these two vectors can never be equal. X and y components might be equal at some point, but z component would not be equal. And similarly, any two components would be equal, but the third would not be equal. And that would mean that the lines do not intersect. Okay. So if they ask you to prove that the lines do not intersect, we use exactly the same process. We find two values from two equations, input them in the third equation. If it does not satisfy that, that means the lines do not intersect. Okay. Now, once you know that the lines intersect in this case, how do you find the point of intersection? You know that the lines intersect when t is equal to -2 and s is equal to -1. If you had to find the point of intersection as well, how would you do that? You would input this value of t back in this equation, or this value of s back in this equation, right? Any of them will work. You can input t equals -2 here, or s equals -1 here. You will get the position vector of the point. You can input them in this simplified form directly as well to make it easier to calculate. So in this case, what I've done is, in the second equation, I've put t equals -2, and that gives me 0, 2, -1. That's the position vector of the point of intersection. So that's the process that we follow for finding points of intersection, or for proving that two lines intersect, or for proving that the two lines do not intersect. Okay. Now, let's have a look at this example. We have a line that passes through these 2 points, 0, 1, 5, and 2, -2, 1. And there's a line that has this equation. We need to show that the lines L1 and L2 are skew. Now, what are skew lines? Skew lines are lines that are neither parallel nor intersecting. So if you have to prove that the lines are skew, you have to prove both that they are not parallel and that they're not intersecting. You have to prove both of those things. Okay. So in this case, first of all, we don't have the equation of this first line. We can find that equation. I'm calling this point A, this point B. Then what's the direction vector of that line going to be? We just find OB minus OA, and that turns out to be this. That's the direction vector. What's the equation of that line? R equals A plus lambda D. You can use any one of these points as A, and then direction vector is this, and that gives you the equation of the first line. This is the second line. They already have given the equation for that. I've just written that in IJK in the column vector form. These are two equations that we've got. Now we need to prove that they are skew. They are skew lines. How do you prove that? We have to first prove that they are not parallel. How do we check that? Check their direction vectors. We have these two direction vectors. Find the ratio between corresponding components. Since the ratio is not turning out to be the same, we say they're not parallel. That's the one thing that you have to do there. Okay. The second thing is that you have to prove that the lines do not intersect. How do you do that? You equate them. You follow the process of finding point of intersection like we did earlier. You equate both of them. You get two equations from that. Solve any two equations, doesn't matter. You'll get some value of mu, some value of lambda here. Then you input them in the third equation. The third equation in this case does not satisfy. If the third equation does not satisfy, that means there are no values of lambda and mu that satisfy all three equations. And that means the lines do not intersect. The lines are not parallel. The lines are not intersecting. That means they are skew lines. And that's what we had to prove. Okay. Now, in this case, the values of mu and lambda will come out to be different from each combination of equation used. So if you use equation 1 and 3, you'll get different values of lambda and mu. If you use equations 2 and 3, you'll get different values of lambda and mu. So when the lines are not intersecting, every single combination is going to give you different values of lambda and mu. Okay, so all of them are going to be correct. You can use any two equations, and then check that in the third equation that does not satisfy. When the lines intersect, in that case, all of them are going to give you the same values of SLD. But when they do not intersect, different combinations will give you different values of lambda and mu. All of them would be acceptable. They would have, sometimes they will give all of them in the marking scheme, or they'll just mention that the other possible combinations will also be acceptable. So don't worry about that. If you're getting different values of lambda and mu because you have used different equations in the marking scheme that use different equations, it doesn't matter in this case, as long as your working is correct, that might still be correct. Okay. All right. In the second part, they just say, find the acute angle between the directions of the line. Okay, this is important. Find the acute angle between the direction of the line L2 and the direction of x-axis. What does that mean? What's the direction of x-axis? Direction of x-axis. Let's say this is x-axis. What's the direction of this? Let's say this is origin. You can take any point here. Let's say 5. What's the direction? It only has x component and no y component. It only has x component, no y component, no z component. So direction of x-axis would be something like this. You could say the y and z components are 0, and the x component, you could write anything in that place. You could write 1, 0, 0. You could write 2, 0, 0, 10, 0, 0, minus 3, 0, 0. That doesn't matter. Y and z components, they should be both 0. And that will be fine. So generally what we do is we just use 1, 0, 0, the unit vector in that direction. So direction of x-axis, we would say that is 1, 0, 0. Direction of line L2, that's this. Find the angle between them and see what that turns out to be. If the angle is acute, you keep it as it is. If the angle is obtuse, they want an acute angle, so you just do 180 minus that to find that result. Okay. Now this is important. A lot of people, end up getting this wrong, and it's the standard method that keeps getting repeated in so many papers. You need to make sure that you understand this well. This is one thing that I absolutely recommend that you memorize the steps for. Memorize every single step in this process. Otherwise, in the exam, you often end up making errors in this. Now, distance between a point and a line, right? That's what we're talking about. Now, first of all, let's understand how to find distance between 2 points, first of all. If you have a point P and you have a point Q, we have their position vectors given. One is OP and the other is OQ. Okay, we have the position vectors of these 2 points. If we want to find the distance between these 2 points, one idea is that we find the vector PQ first of all, OQ minus OP. Once we have that vector, find the magnitude of that vector, and that will give you the distance between the points P and Q. Right? That's how you find distance between 2 points. Now, keep that in mind. And think about how to find distance between a point and a line now. Let's take this example for that. So we have a point P. It has coordinates -1, 4, and 11. And the line L has this equation. We want to find the distance, the perpendicular distance from P to L, from that point P to the line L. How do you find this perpendicular distance? You can try to visualize this a bit like this. You can draw a line. This is the line L. Mark a point P somewhere. Let's say this is the point P. Now you have a perpendicular coming from that point P to this line. This point where this perpendicular meets the line, this is known as the foot of the perpendicular. You should know this terminology. Sometimes they use this as well. You need to know what this is. Foot of the perpendicular, the point at which you have that 90 degrees angle. I'm calling this point X here. Okay. So we have the equation of the line. We have the position vector of this point. And the idea is we want to find the distance between the point and the line. We say X is the foot of the perpendicular. So we want to find the distance Px. The problem is we don't know what the point X is, right? That's the problem. If we knew that, we could just find the distance between the points using this method that we discussed earlier. But we do not know what the point X is. So we first have to figure out what the point X is. How do we do that? We have the point P, the position vector of that, that's OP, right? And the line L, that is this. Now remember, equation of the line is this. This equation is supposed to represent every single point on the line, right? That's what an equation is supposed to do. An equation represents every single point on the line. So this equation represents the position vector of every single point on this line. X is also a point on the line. So the position vector of X should be of this format, right? Remember, different values of lambda, when you put them there, they give you different points on the line. For example, one value of lambda might give you this point. Another value of lambda might give you this point. Another value of lambda might give you this point. We want to find the value of lambda that gives us X. We don't know what that is, but we could write the position vector of X in that form. We could say, if we simplify this, we get 1 plus 2 lambda, 3 plus lambda, minus 4 plus 3 lambda. That's the position vector of the point X. Okay, that's the position vector of the point X. OX equals this. And now, once we have this position vector, how do you find the value of lambda at which we would get that point X? Px vector and this line L, they are perpendicular to each other. Px vector and the line L, they're perpendicular to each other. So we use that idea. We say the vector Px and the direction vector of line L, their dot product should equal 0. Okay. Dot product is only used for vectors. Okay. So we will use the Px vector and the direction vector of the line L, not this whole equation, just the vector, just the direction vector. Okay. And we will put their dot product equal to 0. Now, do we have the direction vector of the line L? Yes, that's 2, 1, 3. That's the direction vector of the line L. That's one vector that we need. The other vector is Px. How do you find Px? You have the vector OP, you have the vector OX now. You could say Px is OX minus OP, right? So OX is this, OP is this. Just evaluate this, and you end up getting this vector Px. And now, since the vector Px and the line, they are perpendicular to each other, we say the vector Px and the direction vector of the line L, their dot product should equal 0. Okay, Px vector and the direction vector of the line L, their dot product should equal 0. So that's what we evaluate now. Right, this is Px dot 213. Put that equal to 0, and that will give you the value for lambda. Now, be careful when you're working here. A lot of careless errors happen in this working, so you have to maybe slow down a little sometimes to make sure that you are not making those errors. Now, this gives you a value for lambda. That turns out to be 3 in this case. Once you know the value for lambda, now you know what that point is, right? Now, they could ask you to find the distance between these points like they've done here. Distance between the point and the line. How do you find that distance now? Now that you know the value for lambda, you have the vector Px, right? You can just input that value of lambda in this vector Px, and that gives you this. Put lambda equals 3 in the vector Px, you get this vector 8 to minus 6. Find the magnitude of this vector, and that gives you the result. That's the distance between the point and the line. Sometimes they will ask you to find the foot of the perpendicular. That means the position vector of the point X. How do you find that? You have the vector OX here as well in terms of lambda. So you would put the value of lambda in this, and that will give you the foot of the perpendicular. So this is OX, put lambda equals 3 there, and you get the foot of the perpendicular from that. Okay, it's the same working that you use for finding perpendicular distance and foot of the perpendicular until this point, until you find lambda. At the end, if you're looking for a perpendicular distance, then you use Px vector and you input the value of lambda there, find the magnitude. Otherwise, for foot of the perpendicular, we put the value of lambda in this case, in this vector. Okay, that's the process that we use for finding perpendicular distance between a point and a line You need to memorize these steps, otherwise it becomes quite complicated. And it's a question that keeps getting repeated so many times because this is the trickiest part of this topic. So they, give this again and again in different questions. Okay. So you have equation of the line. You have the point P. First of all, you write the position vector of OX in terms of lambda. It'll be the same as the equation of the line. Then you find the vector Px, and then you put the dot product of Px and the direction vector of line L to 0, equal to 0. For finding perpendicular distance, you find Px vector. For foot of the perpendicular, you find you put that value in OX. Okay. Now, that's all the concepts that you have in vectors. Now, I'll show you some questions now to show you how these concepts are tested. This is a very simple example. You have the vectors OA, OB, OC, OD, and you have to calculate the acute angle between AB and CD. So find the vector AB, find the vector CD, and then just find the angle between them. That's pretty straightforward. Prove that the lines intersect. How do you do that? You equate both of them, solve two equations, input those values in the third equation. If the third equation is also satisfied, that means the lines intersect, right? This is the process that you can see here. Equate two equations, find lambda and mu from two of them, put them in the third. If that's satisfied, that means the lines intersect. Perpendicular distance from a point to the line AB. You have to find the line AB first of all. You find that first. Find the equation of the line AB. You have the vector OP, the position vector of the point P. Then you follow exactly the same process that we learned just now. Find OX in terms of lambda, then find vector PX. Put the dot product of PX and the direction vector of line L to 0. Find the value of lambda, and then eventually you find that magnitude of the vector Px that you're looking for. Okay, so exactly the same thing. You have to do this over and over again. This is another example. Now, sometimes they have ratios like this that you have to work with. That's the more complicated part sometimes, but it's very important that you understand this very well, even though it'll be not a lot of marks in this question, generally 3 marks, mostly in very rare cases 4 marks. But the problem with this question is that the next parts are going to depend on that. So this first part is very important for that reason, because the next part would often be relatively simpler, and this first part might be a bit difficult. If you can't do that, then you also cannot do the next parts after that. So it's very important to understand how to work with these ratios. So you're given the point OA, the position vector of the point OA, point A and B and C. The midpoint of AB is M. The point N lies on AC between A and C such that AN is equal to 2 times NC. Given this, find the vector equation of the line MN. Now, finding the equation is not the complicated part. Finding the points M and N, that's the complicated part, right? Because once you have the point M and the point N, then we can just easily find the equation after that. That's not a problem. Now, one way to think about this could be that you say, just draw these points randomly, right? So you can have O somewhere. So what I've done is I've drawn this point O. That's the origin. And then mark those points somewhere randomly. So let's say this is point A, this is point B, this is point C. So I just mark those points randomly. Okay, and then I join them because we have vector A. We can join them like this, AB. We know that the midpoint of AB is M. Okay. And we can join AC. We are given the ratio here. We're given the ratio here. What's the ratio? AN is equal to 2 times NC. We can write this in fraction form. So it becomes AN over NC equals 2 over 1. 2 over 1. Okay. That means if AN is 2 parts, then NC is 1 part. Right? That's the ratio that you have between them. If AN is 2 parts, NC is 1 part. Now, given this, can you find the vector OM and ON? This is one way to think about this. You say, let's go from O to A and then from A to M to find the position vector of the point M. So OA plus AM. Now OA is given, you can use that. What about AM? M is the midpoint. AM would be half of AB, right? And then that gives you OB minus OA in place of AB. Now you know everything in this. OA is known, OB is known, OA is known. You can simplify that and you end up getting this. Now, this is actually a direct formula that you can use in case of midpoints as well. If you have 2 points, and there is a midpoint that you have to find for them, you have the points A and B, both of them, you know their position vectors. You want to find the position vector of their midpoint. You can find that directly, skipping all of this working. If you just remember this formula for this, it's very similar to the midpoint formula that you have in coordinate geometry as well. We add the two vectors and divide them by 2. 1 over 2 times OA plus OB. For midpoint, for the position vector of the midpoint, we can use this formula directly, and that could save us some time. We could just skip all of this working and do this directly like this. So when they say midpoint, if M is the midpoint of A and B, then the position vector of M is given by this. Okay. So this formula, you can remember directly. M is midpoint of A and B. That's the formula that you can use directly, and that will give you the vector ON. That turns out to be this. Now, the second thing that you have is, you want to find the vector ON. You have to go from O to N. Now, again, if you have drawn this diagram like this, you can think of it like this. You can say, let's go from O to A, and then let's go from A to N, right? That's the path that you can follow. So go from O to A and then A to N. And that gives you OA plus AN. However, we know the ratio is, if AN is 2 parts, then NC is 1 part. What does the total become? The total is 3 parts. AC is 3. AN is 2 parts. So what does AN become out of the total? AN is 2 out of the 3 parts. So the total parts are 3, right? So we could think of it like this. There are 3 parts in total. This is 2 out of 3 parts. This is 1 out of 3 parts, right? So AN could be written as 2 over 3 times AC. How does that help? Because we know the point A and the point C. So we could say OA vector that equals AC vector that equals OC minus OA. And now we've got everything that we need for this. We can input the values OA, OC, OA, simplify everything, and we'll get that point ON. This is one way to deal with ratio problems like this. The other idea, which is going to be slightly longer than this, but simpler, you would not have to do as much thinking on that. And that is without the diagram. If you're given a ratio like this, AN equals 2NC. Now, this ratio is between their lengths, not their vectors, right? The ratio that's given originally, that's between their lengths and not the vectors. However, since they lie on the same line, we know that they've told us that here. Point N lies on AC. So all of these 3 points lie on the same line. If the lines are parallel to each other, or if they lie on the same line, that means their directions are also equal. AN and NC, their directions are equal to each other. So if their directions are equal, we can say, if their directions are the same, we can say whatever is this ratio, that will be the ratio between their vectors as well. So the vectors would also have the same ratio. In this case, AN vector would be 2 times the NC vector, right? The ratio between vectors would be the same. Now, if you know that, then you could just not think about the diagram and just do it algebraically like this. You say AN vector is equal to 2 times NC. I showed you this, I think, earlier as well. What you're looking for is ON. That's what you want to find out. ON vector. So AN can be written as ON vector minus OA vector. NC can be written as OC minus ON. And then all you have to do is just make ON the subject from this. Make ON the subject. Okay. You know everything else, make O in the subject, and then just input the values of OC and OA. Simplify that and you get the result. And this is something that a lot of people find easier because then you don't have to think about those ratios. That becomes a bit more complicated, especially when you have to draw the diagram yourself. This becomes a bit more tricky. So I would recommend when you have ratios given, not just the midpoint, but you have some other ratio given, then you could just work with those vectors like this, convert them to position vectors, and then just make whatever it is that you want to find out the subject. For example, in this case, you wanted to find out ON vector, you make that the subject, and you have everything here given. You can just evaluate that like this. Okay, so that's how you would deal with problems like these when you have ratios given like this. Okay. Now, the second part says it's given that MN intersects BC at the point P. Find the position vector of the point P. Now, that's this point of intersection of two lines. You find the equation of line MN. You can do that now, right? Once you have the point OM and the point ON, the point OM and ON, you can write down the equation quite easily, right? Find the vector MN. And that will be the direction vector. Use any of these points as a point A in the equation, and you can write down the equation. You can write down equation in IJK form as well, and in column vector form as well. Generally, the recommendation is if the question gives you values in IJK form, then your final answer, you can write that in IJK form as well. If the question gives you vectors in the column vector form, then the final answer, you can write that in column vector form. Although both are acceptable, but it's better to follow the form that they give you in the question. Sometimes they will tell you in the question to give your answer in terms of I, J, and K. In that case, you have to make sure that you follow that. If they have not specified, then any of them is going to work, but it's preferred that you use the form that is given in the question just for a final answer. In your working, you can work with either of them, but in your final answer, you could write that in IJK form because that's what the question is giving you. So you just use IJK form at the end, and that will be the equation. In the second part, you just have to solve those equations simultaneously. That's not that difficult. You can do that. Let's have a look at this example. We have two lines, these two lines, and the question says it's given that the lines L and M intersect. We are given that the lines L and M intersect. Given that, show this thing. 2a minus b is equal to 4. How do you do that? Now, if two lines intersect, what that means is if you were to equate them, all three equations would be satisfied with the values of the parameters that we get from that. So we've got one equation this, another equation this. What we do is we equate both of them first of all. Follow that process of finding points of intersection. See what you get from that. You have these vectors given, the equations given in terms of A and B. So your working will have to be in terms of A and B. So you equate both of them, you get three equations. These are the three equations that you get. You can solve any two of them simultaneously. So I've used equation 1 here and equation 2 here. Solve them simultaneously. That means find the values of lambda and mu in terms of A and B. So in this case, I made lambda the subject in the first equation, put that in the second equation, that gave me mu equal to this. Put that back here, that gave me the value for lambda corresponding to that. Once you have these values, input these values in the third equation now. If the lines intersect, the third equation must satisfy these values of lambda and mu as well. Okay, it must satisfy as well. So in the third equation now, you input those values of lambda and mu, simplify that, and eventually you'll get that form that they wanted you to prove. That's 2a minus b equal to 4. So when they give you in the question that the lines intersect, what that means is, if you solve two equations, the values of lambda and mu that you get from them, they must satisfy the third remaining equation as well, and that will give you that form that they want here. Then they're saying in the second part, the lines L and M are perpendicular. If they're perpendicular, find the values of A and B. Now we've got one equation in terms of A and B. Now they're saying the lines are perpendicular. If the lines are perpendicular, that means the direction vectors of these lines, they should be perpendicular. So we can find the dot product of the direction vectors, put that equal to 0, and that will give us another equation. You can do that here. Put the dot product of these direction vectors equal to 0. You get another equation from that. Solve these simultaneously, you get the values of A and B from that. Okay. The third part is straightforward after that. Find the position vector of the point of intersection. Now you've done all of this work already. You found the values of lambda and mu in terms of A and B. You know the values of A and B now. Input them in any one of them to find the value of lambda and mu. I've done that here. I found the value of lambda. Once I have the value of lambda, I can input that back in the equation that has lambda to find that point of intersection. Okay, you can have a look at this work in your own time later on. That's how it works. Let's move on. Now, this is the more complicated type of problem. You have a line that has this vector equation. L does not intersect the line passing through A and B. Now, it looks like a weird way of writing the equation of line, right? So you need to understand what the actual format is. It's basically like this: 1 minus 2t, 5 plus t, 2 minus t. So if you were to write this in column vector form, that looks like this. So what they've done is, the actual equation was like this: 1, 5, 2 plus t into minus 2, 1, minus 1. That's the actual equation. They have given us the simplified form for that, right? So don't get confused by that. It's just that equation. It was supposed to be in this form. They've given you the simplified form for that. Okay. Now in this first part, they're saying, show that the lines do not intersect. You find the equation of the line AB first as well. Equation of the line AB, that turns out to be this. And then you equate both of those lines, solve two equations simultaneously. The third equation would not satisfy, and that means the lines do not intersect. Okay, so that's straightforward. The second part says the point P lies on L and is such that the angle PAB is equal to 60 degrees. Given that the position vector of P is this, you see it's the same as the equation of the line because the point P lies on the line L. So its position vector will be of the same format. They're saying the position vector of P is this. Show that this is true and hence find the position vector of the point P. Now, how do you do that? You're given the angle between two vectors. What two vectors? AP and AB. The angle is at the point A here. The angle at the point A, they're saying that is 60 degrees. Okay, the angle at the point A is 60 degrees. So the vectors that you'll be using, they will be either both starting at the point A or both ending at the point A. So you can either use AP or AB. Any of them will work. So, sorry, AP and AB, that's one combination that you can use, or you can use BA and PA. Any of those combinations, let's use them here. We have the vector OP given. We have OA, OB. They're given as well. We can find the vector AB from that. Now, we want to use the vectors AP and AB. Using OP, we can find the vector AP. Whatever done that here. Yeah. AP vector, we can find that. Right? That turns out to be this. Now you have AP, you have AB. Input values in this formula. Simplify everything. It becomes a bit complicated equation, as you can see here. You have square roots there. You have to square both sides to get rid of that square root. And eventually, when you simplify that, you end up getting that equation that they wanted. Okay, you can have a look at this working. It's in terms of T here, especially for the magnitude of AB here. So you'll have to do some, algebra there. And you get that equation. Now, when you get that equation and you solve that further, you get two values of T from that. The question asked you to give the only possible position vector of P. That means both of these values are not going to be possible. Only one of them is going to be the answer. So which one do we use? How do we know that? Now, one of these values is going to give you acute angle. The other is going to give you obtuse angle. This is 60 degrees. They want the angle to be 60 degrees, right? Since we squared both sides, that's giving us multiple answers. So you have to check now which one of these gives you an acute answer, right? So when you find dot product using one value for T, for example, T equals -1/3, that dot product turns out to be negative. If that's negative, that will give you an obtuse answer, as we discussed earlier. And if the dot product is positive, that gives you an acute answer. So dot product is positive in the case when t is equal to -2. So that's the case that we use here. We say t equals -2. That's the answer that we will accept from there. Input that in the vector OP, and you find the vector OP that we were looking for. You could also just input this value of t back in this formula and see if it gives you 60 degrees or not, right? This would not give you 60 degrees. When you input that in the formula, that will give you 120 degrees, the obtuse angle. That's not what we want. Okay. So that was the tricky part here. You can have a look at this again. Now let's have a look at some more questions from recent papers. I'll try to go through them quickly. There's some specific parts that I would just want to discuss, then we will end. We have these two lines, L and M, that intersect at the point P. First of all, we have to state the coordinates of the point P. Okay, now, point of intersection, that's what we're looking for. And it's only a 1-mark question. How does that make sense? We have these two equations. You see the point that they're using here in both of those equations, this point and this point. That's common between them. That means that has to be the point of intersection, right? There's a common point between two lines. That means that's the point of intersection, right? So you can just write that directly, 2, 1, -3. They wanted the coordinates of the point, so you'll write them in this form, 2, 1, -3. If they ask for position vector, you'll write that as 1, 2, 1, -3, like this in vector form. In the second part, they say find the exact value of the cosine of the acute angle between L and M. You can just use the formula, find that value. That turns out to be this. Now they're saying the point A on line L has these coordinates. So there's point A on the line L that has these coordinates 0, 1, 1. The point B on line M has coordinates 0 to -1, -0 to -8. Find the exact area of the triangle APB. So we've got 3 points. One is on line L that has coordinates 0, 1, 1. So what I've done is I've just drawn 2 random lines. One L, the other M, right? Just randomly. Just to understand the situation better. On line L, we have this point 0, 1, 1. Okay. On the other line, we have the point B that has coordinates 0 to -8. Okay. Now it's actually in 3 dimensions, so you cannot mark these points accurately. You just mark them randomly for your own understanding. Now these are 2 points that you've got. They're saying find the exact area of the triangle APB. Now this is B, this is A. What's P? P is the point of intersection that we've already found before. The point of intersection was 2, 1, -3. This is 2, 1, -3. This is a triangle that we have. We want to find the area of this triangle. How can you find that? In the previous part, when you found the angles, you already found the 2 magnitudes, magnitude of A and the magnitude of B, right? You found these 2 magnitudes in the previous part for A and B. What was A and B? I'm sorry, it was the direction. That was something different. Sorry. So you have these 3 points, PB, PA, and P. You have found the angle before in the previous part. The angle cos theta of that angle is 400√6/15. That's what you find out. So let's say this angle is theta. We know that cos of this angle, that is 400√6/15. That's what we have found out already. What we can do is, for finding the area of the triangle, we've got 2 formulas, half into base into height or half into AB sine C. We can use half into AB sine C here. We could say this side, this is one side, this is another side. Theta is the angle between those 2 sides, right? Can we find the lengths of these 2 sides? We can use distance formula for that, or use magnitude of the vectors. You can either find the find the vector PB, vector PA, and then find their magnitudes. That's one idea. Or you can just use the distance formula directly. Just like in coordinate geometry, we used to have this formula, x2 minus x1 whole squared plus y2 minus y1 whole squared, square root of that. In 3D, we could extend the distance formula like this. That becomes x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared, and square root of that whole thing. Not cube root, square root. Okay. So you can find the distance between these 2 points directly like this, square root of 30, square root of 20. So you've got this length and this length. So you have 2 lengths in that triangle and the angle between them. So this length is square root of 30, this length is square root of 20. Now, how do you find the area? You can use half into AB sine C. The problem here is they want an exact area. They don't want decimal values. How do you find exact area? You don't have sine of theta. Now for this, you need to know this method. Cos of theta is 4 under root 6 over 15. You can think of a right angle triangle. Think of this right angle triangle in which, let's suppose this angle is theta. If cos of that, what's cos of this angle? That will be base over hypotenuse. So we can think of this as base over hypotenuse. So if base is equal to 4 under root 6, then height would be equal to 15. Can we find the perpendicular from that using Pythagoras? We can find the perpendicular. The perpendicular turns out to be square root of 129 here. Okay, so we've got the base, the height. These are the ratios between them. 4 under root 6 here, 15 here. And now we can write sine theta. What's sine theta going to be? Perpendicular over the hypotenuse. That's square root of 129 over 15. That is what we will be using here as the value for sine theta. Simplify that, and that gives the result in exact form. You cannot find angle from your calculator in this case. That will give you a decimal value. That will not be acceptable. You'll have to do it like this to find the exact value for the area. If you have cos theta given, you can find sine theta from that like this using a right angle triangle. And this is something that you can do in paper 1 trigonometry as well. That's how it would work. Okay, let's move on. We have these 2 lines. They are perpendicular to each other. And we need to show that A is equal to 4. That's straightforward. Put the dot product of direction vectors equal to 0, and that will give you the value for A. The second part asks you for the position vector of the point of intersection. Now, this is important. There's a point A that has position vector minus 5i plus j minus 9k. Okay, there's this point A. We need to show that the point A lies on L1. A point lies on a line. How do we show that? We have the equation of the line. That's this. We need to show that this point lies on this line. What's the process for that? We just input that point here. Input this point in the equation. How would you put that? You would put that point in place of R here. Put that point in place of R. Okay. Now, when you put that in place of R here, you get 3 equations from that. If all of those 3 equations give you the same value for lambda, that means that this point lies on the line. Okay. A more efficient method could be that you find the value of lambda from one equation, from the first equation, for example, that turns out to be lambda equals minus 3. And then rather than solving the other equations, just put lambda equals minus 3 here, lambda equals minus 3 here, and see if that value is satisfying the other equations or not. If it is satisfying the other equations, that means when lambda is equal to minus 3, you get this point. Minus 5, 1, minus 9. So that means this point lies on the line. So when you have to show that a point lies on the line, what you do is you input that point in place of R, solve those equations. If you're getting the same value from all those equations, that means that that point lies on the line. Okay. Sometimes they ask you something like this. There's a point B that is the image of A after a reflection in the line L2. Find the position vector of B. So the idea is we have this line L2. We have found the position vector of the foot of the perpendicular in a previous part. Have you found that? No. So we knew that the lines are perpendicular. That's one thing that we knew. And we also found their point of intersection. So we knew these 2 things. The lines are perpendicular and their point of intersection is the point X. We know what that point is. That's minus 1, minus 1, minus 1. We found that before. Now they're saying the point B is the image of A. So A point is this. X is this. B is the image of A in the line L2. Where will this point B be? How do you find that? You can think of it like this, that X is the midpoint of AB. X is the midpoint of AB, right? Either use the midpoint formula or using the vector method, it will be much quicker. You can say this is A, X is the midpoint, B is supposed to be on the other side of the midpoint. So whatever distance you have to go in order to go from A to X in the X direction, it will be the same that you have to go from X to B. 4 units. So in order to go from -5 to 1, you have to go +4. So you do +4 more, and you get 3 from that. How do you go from 1 to -1? You have to do -2. You do -2 more, and that gives you -3. Minus and -2, that's -3. How do you go from -9 to -1? You do +8. You do +8 more, and that gives you 7. And that's the point B that we were looking for. The position vector of that point B is 3 -3, 7. Okay. So when they talk about reflection like this, that means that it's going to be the same distance on both sides, right? So whatever distance you have to travel from this point to this point, you travel the same distance in the other direction as well. Let's look at another example. We have these two lines, and they're saying they're perpendicular to each other, and that P lies on L. Find the values of the constants A, B, and C. Now, if they're perpendicular, what does that mean? Their direction vectors, their dot product should be 0. So that's one equation that we get, and that gives us the value for C. If the point P lies on L, what does that mean? It should satisfy that equation. The equation of the line L is this. We can put that point P inside this. The point P is 4, 7, -2. And then we get 3 equations from that. 1, 2, 3. All of these equations should give you the same value for lambda. All of these equations should give you the same value for lambda. So you solve these equations simultaneously then. And that gives you the values for A and B. Okay. Let's move on. Part B, it says the perpendicular from P meets the line M at the point Q. The point R lies on PQ extended with PQ ratio QR equals 2/3. Find the position vector of the R. So sometimes they extend this foot of the perpendicular problem a bit. For example, if you get something like this, you first have to find the foot of the perpendicular. So you have this line M. You have this line M. They're saying there's a point P for which we know the position vector that's given in a previous part. From this point P, if you draw a perpendicular, it meets the line M at this point Q. So Q is the foot of the perpendicular. The point R lies on PQ extended. So if you were to extend PQ, go to the other side, there's some point R on the other side. And it's such that PQ ratio QR, if this is 2 parts, this is 3 parts. That's the ratio. Okay. You can say 2/3, or if this is 1, this is 1.5, right? That's the ratio. How do you find the point R? Position vector of the point R. How do you figure that out? First of all, you can find the position vector of the foot of the perpendicular. How do you do that? That's a standard process that we follow, right? We have seen that before. Follow that whole process. Find the position vector of the point Q first of all. And that turns out to be -1, 5, and 2. Right? Foot of the perpendicular, that turns out to be -1, 5, and 2. Once you have that, now you say, you have the point P, you have the point Q. We know that from P to Q, if it's 2 parts, from Q to R, it's 3 parts. Okay. You see how much you have to go in order to go from 4 to -1 in the x direction, -5. Similarly for Y and Z, we figured out how much distance do you have to go from in order to go from P to Q. -5, -2, and 4 respectively. Now, since the ratio PQ to QR is 3, or is it 3? No, it's 2 to 3. We could think of it like this. It's 1 to 1.5. That means whatever this distance is, from Q to R, it has to be 1.5 times that. So this is -5. You multiply that by -1.5. That becomes multiply that by 1.5, and that gives you -7.5. -2 into 1.5, that gives you -3. 4 into 1.5, that gives you 6. So from Q to R, the distances would be 1.5 times these distances. You add those numbers here, you get the result. That's the point R. The position vector would look like this. And that's pretty complicated, but that's how you'd approach a problem like this. Okay, so you first of all find the position vector of the foot of the perpendicular. This much gets you 4 marks until this point. Then you have to use this ratio to figure out the position vector of the point. This is one way of doing this. The quickest way of doing this, thinking of it like this: the ratio is 2:3, or you can say 1 to 1.5. So whatever is the distance between P and Q, the distance between Q and R, they should be 1.5 times that. All right. Let's have a look at another one. Quadrilateral ABCD is a parallelogram. Find the position vector of D. We've seen this before. It's a parallelogram. We can draw a parallelogram like this, ABCD. Now, there was a question earlier that I missed. We could draw this in any order. It doesn't matter. So just draw a parallelogram and say, mark any of them as A, B, C, D. It doesn't matter as long as you go in order. So for example, I could start from any point here. I could say this is A, this is B, this is C, this is D. That's okay. I can go in the clockwise direction as well. I could go A, B, C, D. That's also fine. What you cannot do is that you mark A here at this point, and then you mark B here. That's not allowed. So you have to go either anti-clockwise or clockwise. Start from anywhere, doesn't matter. Just don't jump like this from one point to the other. So go either clockwise or anti-clockwise. All right. Okay. So what you do is you have this parallelogram. You have to find the position vector of D, draw this parallelogram, and now you can say, for example, AD vector is equal to BC vector. You could also have used BA equal to CD. Any two opposite vectors that are parallel to each other in this case, right? So we can use BC equal to AD, for instance. And that gives us OD minus OA. That equals OC minus OB, right? They should be equal to each other. And now we can make OD the subject, and that will give us that result. The second part is straightforward. And the third part, they're saying, find the area of the parallelogram ABCD. How do you find area of a parallelogram? You found the angle in the previous part, cos theta of this angle. Okay. And you have the lengths as well. This is square root of 62. This is 3. What you can do is you can break it into two triangles. So you have this triangle. Find the area of this triangle, multiply that by 2. Find the area of this triangle, just multiply that triangle by 2, and that will give the area of the parallelogram. Now, how do you find that? Like in the previous example, we have cos theta given, exact value of that. We found the value of cos theta in the previous part. How do you find the corresponding value of sine theta from that? Use the right angle triangle, cos is base over hypotenuse, find perpendicular from that, and that will give you sine, which is perpendicular over hypotenuse. Input that in the formula, find the area of the triangle, multiply that by 2, and that gives the area of the parallelogram in exact form. Okay. Then sometimes you get relatively more complicated problems. You have ratios given. It's from a recent paper. I'll just leave it for you to have a look at this. Blue part is horizontal base, and it's vertical like this. K is vertical. You have some vectors given. You have to find the vectors MD and ON. You have some ratios given, right? Cn is equal to 2NB. Midpoint of AB is M. You can use the midpoint formula for that, right? That we discussed earlier to find OM, and then use that to find MD. Similarly, for this ratio, you could have used Cn vector equal to 2NB vector, and then simplify that to find ON somehow, right? So you can have a look at this working. This is one way of doing this. You can do it using the other method as well. I've done this using ratios in this case, but as I said, a lot of people find it easier to do it using those vectors. So you can just do it that way. Cn vector that equals 2NB vector. Okay. Then use that to find the vector OC. This is a relatively difficult question. You can have a look at this later on your own time. Angles between vectors, but length of the perpendicular. These are standard problems. You can again have a look at the working. It's there in your notes. Again, a very similar problem. You have ratios given. and you have to find the position vector of M and the position vector of N. M is the midpoint. You can use the midpoint formula for that if you want. This formula that we discussed earlier directly. Skip this working. Just use the formula directly. And for that ratio, you could use this vector notation, input values in them, and you get the result from that, right? We talked about similar questions before as well. Find the vector equation through M and N. You can find that. Point of intersection. Right, so I have just added these examples to the notes. You can have a look at them. It's good practice for finding these, for dealing with these first parts, right? The ratio parts. There's nothing new as such. It's just, more practice that you can use these questions for. This is a bit tricky. Sometimes people find it a bit complicated. They're saying find the perpendicular from over to the line. Now we generally know how to find perpendicular distance from any point to a line, but what if that point is origin? If you have to find the perpendicular distance from origin to a line, now that actually makes things simpler. If you understand the concept correctly, it becomes even simpler, because now you could say you've got the equation of the line that's given in the question in the first part. You could say the position vector of this point X, what's that? That's the same as the position vector of this, that's the same as the equation of this line. And that turns out to be this. And now, earlier we used to have some other point here, P for instance, and we used to find the vector Px. In this case, the point that we are finding the distance from is just the origin itself. So you can just use the vector Ox directly. That's one vector, Ox. It's supposed to be perpendicular to the direction vector of the line. This is the direction vector of the line. This is the vector Ox. They're supposed to be perpendicular to each other. We find their dot product, put that equal to 0. Find the value of lambda from that. Once we have that, put that back in Ox in this case, because that's the distance that you're looking for. Put that here and find the magnitude, and that will give you the result that you want there. Okay, in this case, you just use the magnitude of Ox, right? It helps to draw a rough diagram like this. That will make it easier for you to understand, so that you know which two vectors you have to make the dot product equal to 0 for. So that will be Ox vector and the direction vector of the line L. And then you can solve that further. Okay, I hope that was helpful. That's how we deal with this vector problems. I've gone through all the concepts and many different types of questions. I hope that helps. Okay, just a quick check. You can see my screen and also see the screen moving like this. Yes. Okay, good. Thank you. Let's begin with this thing. Complex numbers. This is the next topic that we've got now. First of all, what are complex numbers? You would have seen equations, quadratic equations before at some point, that when we solve them, you end up getting a negative number inside square roots. When you have a negative number inside square root, you can write that in terms of this number that we define as iota. It has a value of square root of -1. We say whenever we have square root of -1, we would write that as iota, right? So we have defined this number called iota like this. It's represented by I. Whenever we have square root of a negative number, we can write that in terms of iota. How would you do that? So in this case, when we apply the quadratic formula on this equation, we end up getting this. Now, square root of -16, we could write that as square root of 16 times square root of -1. And square root of -1 can be written as iota. So it becomes square root of 16, which is 4 times iota. And then we simplify that, we end up getting 3 plus minus 2 iota. That means 3 plus 2 iota and 3 minus 2 iota. These are the two solutions of this equation. So earlier, when we used to say that this equation does not have any solutions, we meant that it has no real solutions, but it does have complex solutions. Okay, so it has two complex solutions like this. Now, these complex numbers that we've got, this is the standard form of complex numbers. We call this Cartesian form. You need to remember this name as well. Sometimes they refer to this name in questions as well. You need to know what this represents. X plus y iota, this is the standard form for complex numbers. It's also known as Cartesian form. Now, it has two parts. One part is real part and the other is imaginary part. Real part is the one that does not have iota with it. This is the imaginary part that has iota multiplied with it, right? So x is real, x is the real part, y is the imaginary part. This is notation. There's some notation that you need to know about. If they say re of z, that means real part of z. In this case, if the number z is equal to 5 minus 3 iota, real part of z is equal to 5, and the imaginary part of z, that is minus 3, right? So imaginary already incorporates that it will have an iota with it. So we say imaginary part of z, that's just minus 3. These are notations that we have for real part and imaginary part. Now, we often represent complex numbers using letters like Z, U, V, because X and Y, we use them for real numbers generally. So for complex numbers, it's a convention that we use Z, U, V letters like these, other than X, Y. Now, we have another terminology that we call conjugate of a complex number. If you have a complex number like this, 5 minus 3 iota, there's another complex number that's defined corresponding to that, and that's 5 plus 3 iota. We say that's the conjugate of this number z. It's represented, it's denoted by this notation z star, z asterisk. So if we have x plus y iota, the conjugate of that z asterisk, that is x minus y iota. What happens is the imaginary part's sign is flipped and it becomes the conjugate. If you have two numbers like this, one is minus 4 plus 7 iota, another is minus 4 minus 7 iota, you see the imaginary parts have different signs. These are conjugates of each other. Together we say it's a conjugate pair. Okay. Then we need to know how to evaluate powers of iota. If it's iota power 1, that's just iota. Iota square, what would that be? Since iota is defined as square root of minus 1, square root of minus 1 whole squared, iota square root gets cancelled, and we have minus 1 left from that. Now, this is a very important result that we will be using in almost every single complex number problem. That square of iota squared is minus 1, right? So iota squared is a real number. If you were to evaluate higher powers, sometimes you have to evaluate iota cube as well. How can you do that? Iota cube can be written as iota squared into iota. Then iota squared is minus 1, so it becomes minus iota. Iota raised to power 4, that's just iota raised to power 2 into iota raised to power 2. Iota squared into iota squared, that becomes minus 1 into minus 1, and that's plus 1. That's this. And similarly, you can go on like this. It's a cyclic pattern. It keeps repeating after this. Iota raised to power 5 is iota, then power 6 would be this again, power 7 would be this again. However, we would just need to go up to iota cube generally. So you see, odd powers of iota are imaginary. Even powers of iota, they are real numbers. So this is real, this is real. Okay. Now, you need to be able to add and subtract complex numbers. Addition subtraction works like it works for any expressions in terms of x, y, for instance. Just add and subtract the like terms. The real parts get added and subtracted to each other. Imaginary parts get added and subtracted to each other, right? You can see that here. Multiplication, when you have two complex numbers that are multiplying, we do multiplication like we normally do as well. We multiply every term of the first bracket with every term of the second bracket, and we get an expression like this. However, after multiplication or division, the final result that we want, that has to be in this form, x plus y iota. Now, in this multiplication, we end up getting iota squared. So what we do is we don't leave it as iota squared. We would have to convert it to minus 1 first of all. So we say iota squared is minus 1. Replace that with minus 1. And then you input that here, simplify everything, and that gives you 45 plus 10 iota here. Okay, that's how multiplication works. If you have to divide two complex numbers, how does that work? If you have 4 minus 3 iota and 6 plus 7 iota, you want to divide one complex number by another complex number. Let's say you want to do u over v. How would that work? 4 minus 3 iota over 6 plus 7 iota. The final result that we want has to be in this form, x plus y iota. Now, in this case, we have iota in the denominator. We don't want iota in the denominator. We only want it in the numerator in this form, x plus y iota. So the point is we want to get rid of iota from the denominator. The way to do that is This process is called rationalization. What we do is we multiply and divide by the conjugate of the denominator. Now, what's the conjugate of the denominator? This is 6 plus 7 iota, right? The conjugate of that is 6 minus 7 iota. We multiply and divide that fraction by the conjugate. And what happens when we do that is we have a plus b here into a minus b. When we do a plus b into a minus b, we end up getting a squared minus b squared. So we only have iota squared in the denominator, and we know iota squared is a real number. So that can be replaced with -1. And that's how we can get rid of iota from the denominator, right? And then the numerator gets simplified like we normally do. We just multiply these two expressions. We have iota squared there. We'll replace iota squared with -1. Simplify everything at the end. We write the real part separate, imaginary part separate. 3 over 85 minus 46 over 85 iota. That's the result that we end up getting when we multiply, when we divide these two complex numbers. Okay. Now, why did we multiply and divide by the conjugate? To get a square minus b square here, because that gets rid of the iota. When you have even power of iota, it becomes real. If you just had something like this, 4 over iota, for instance, in this case, if you want to get rid of iota, or let's say 4 over 3 iota, if you had something like this, one way to do this could be that you multiply and divide by the conjugate of the denominator. The conjugate of 3 iota, what would that be? That would be minus 3 iota. You could say multiply and divide by minus 3 iota. However, in this case, it's much simpler to just multiply and divide by iota, and that will be sufficient because all you want is that you have iota squared in the denominator. So if you just multiply and divide by iota, that will be sufficient in this case. That gives you 4 iota over 3 iota squared, and that gives you 4 iota over -3. So we've gotten rid of the iota from the denominator. However, when we have both real and imaginary parts, then we can't just multiply and divide by iota. Then we have to multiply and divide by the conjugate, and that will eliminate iota from the denominator. If we have any other power of iota, for example, you're saying if we had iota cube in the denominator, we would convert that. First of all, we'll say that that's iota squared into iota, and that simplifies to minus iota. So that will simplify to iota. All right. Okay, now let's move on. Two complex numbers, when are they equal to each other? When two complex numbers are equal to each other, their real parts have to be equal and their imaginary parts have to be equal. Now, this is very important. You will see later on, you will get equations in which we'll have one complex number on the left side, another complex number on the right side. If they're equal to each other, we would say the real part on the left and right, they are equal to each other, and the imaginary parts on both sides, they're also equal to each other. So that means x equals a and y equals b in this case. Okay, now keep this in mind. We'll have a look at some examples. Let's say we've got a quadratic equation like this. We want to find the values of c. How do you do that? It's a quadratic equation. For solving quadratic equation, you can just apply the quadratic formula, input values in this, simplify everything. Now, generally, for equations that have real answers, it's sufficient generally to just input values in the formula and write down the answers. But in complex numbers, it's necessary for you to show the working. You will not get marks if you do not show working in the exam. So you have to make sure that you show all working and clearly show the examiner how you're converting square root of something negative to iota. This step is very important. Okay, and then you simplify that and you get the result from that. Okay, take another example. So you can sometimes have equations like these as well, where you have iota in the equation itself. So in this case, we've got iota in the equation. But it's a quadratic equation still. How do we solve this quadratic equation? Input values in the quadratic formula. When you do that, inside the square root now, you get 4 iota squared plus 20. You simplify that, and you're not getting any negative number inside the square root in this case. However, you have iota already outside here. You've got iota outside here already, right? So you just simplify this, and you get the result. These are the two solutions that we're getting from this: 2 plus iota and minus 2 plus iota. Now, notice one thing. In the previous examples that I showed you, in the very first example that I showed you, I solved this equation. I got two solutions from that: 3 plus 2 iota, 3 minus 2 iota. Both of these solutions were conjugates of each other. You see, the equation only had real coefficients. There was no iota in that original equation. In this case, when I solved these two equations here as well, When I solved this equation, I got two roots. They were both conjugates of each other again. In this case as well, the original equation did not have any iota in it, right? So it looks like a pattern that we'll talk about in a few minutes, that when we solve polynomial equations like these, their answers, if there are any complex roots, they always occur in conjugate pairs like this. However, there's a condition for that, that there should be no iota in that equation. When we had iota here in this case, in this case, the solutions that we got here, they were not conjugates. In this case, the real parts have different signs, but the imaginary parts, they have the same sign. So these are not conjugates, right? So in this case, that does not happen. Now, keep that in mind. We'll talk about that in a few minutes. Let's have a look at another example. We have two complex numbers, W and C. They satisfy this relation. Given that Z is equal to 1 plus iota, find the value for W. How do you do that? You can input Z equals 1 plus iota here. You do that. That simplifies to this. Now you've got iota squared in the denominator. You first have to simplify that. That becomes iota minus 1 plus 2. And then you've got one complex number in the numerator, another in the denominator. You want your final answer in x plus y iota form. So how do you get rid of the iota from the denominator? You multiply and divide by the conjugate, simplify everything, and you get the result from that. But the second part says, given instead that W equals Z, find the value for them in complex numbers as well. You've got W equals Z plus iota over iota Z plus 2. That's one equation that we've got. And we have another equation that's W equals Z. We can put W equal to Z here, and that gives us this. Then multiply this denominator on the left side, and that gives us a quadratic equation. Now it's a quadratic equation. We can use the quadratic formula, input values in this, solve that equation, and we get the result from that. It becomes a bit lengthy, but we get two answers from this. However, in this question, they said the real part of Z is supposed to be negative, right? In our answers that we got here, you can have a look at this working. One of them had a positive real part and the other had a negative real part. They said that the real part is supposed to be negative. So we only consider the one that has negative real part and we say that's our final answer. Okay. So in complex numbers as well, sometimes you may have to solve simultaneous equations like these. And then they can become quadratic like this as well. And you just solve them like a normal quadratic. When you have a negative number inside the square root, you would just write that in terms of iota. Okay. Now, times what by conjugate? I'm not sure what you mean. Let's discuss that at the end. There's no W here. We've already put W equal to Z, right? So the W is eliminated. There's no W anymore, right? Let's talk about that at the end, okay? Let's try to be a bit quick. The complex number W is such that the real part of W is greater than Z, and we have another equation that's W plus 3W conjugate equals iota W squared. Now, in this case, we have this equation. This also looks like a quadratic equation. However, the problem is we've got two unknowns here. We've got W and we've got W conjugate. There are two unknowns, right? When we have two unknowns and only one equation, we can't really solve that, right? In equations where you have both a complex number and its conjugate together, what you do is you input input one of those complex numbers as x plus y iota, and the conjugate, that would be x minus y iota, right? So you input these values like this because you cannot solve it directly. You've got two unknowns. What you do is you say if W is equal to x plus y iota, then W conjugate is going to be x minus y iota, right? You input those things here, simplify everything. Now, after you've done the simplification, what happens is you end up getting this on both sides. On the left side, you have 4x as the real part. On the right side, you have minus 2xy as the real part. On the left side, you have minus 2y as the imaginary part. On the right side, when you take iota common from the terms that have iota in them, x squared minus y squared is the imaginary part. Now, if these two complex numbers are equal, the one on the left side, the one on the right side, then that means the real parts are supposed to be equal to each other and the imaginary parts are supposed to be equal to each other. We get two simultaneous equations from that and we solve them simultaneously to get the values of x and y. In the question, they said that the real part of w is supposed to be positive, so we only consider the possible answer in which the real part, which is x, is positive, and we ignore the other answer. So this is a standard method that we have for problems like these. Whenever in an equation you have both a complex number and its conjugate, you do a substitution like this. You put that complex number equal to x plus y iota and its conjugate equal to x minus y iota. You'll have one complex number on the left side, one on the right side. You do comparison and solve that equation further. Now, we talked about this earlier, roots of polynomials. For any polynomial, this is a standard rule that we've got. For any polynomial that has real coefficients that do not have any iota in them, if there are any complex roots, they always occur in conjugate pairs, right? If the equation does not have any iota in it, then the solutions that you get, if they are complex, they always occur in conjugate pairs. Okay, so if you know one root, for instance, for example, if one root is 2 plus 3 iota, you know for sure that 2 minus 3 iota is also going to be a root, right? Now, since they occur in conjugate pairs, the number of complex roots that you would get would always be even in such cases because they are going to occur in pairs. So you can have 2 complex roots, 4 complex roots, 6 complex roots like this. And that also tells us that the total number of roots of any polynomial is always equal to the degree of the polynomial. So if you have a quadratic equation, for instance, it will always have 2 roots. Earlier, we used to say that we would either have 2 roots or no real roots. When we have no real roots, then that means you have 2 complex roots. So for any polynomial, if it's a cubic polynomial, it always has 3 solutions. If it's a quartic polynomial, quartic is power 4 polynomial. In that case, you always have 4 roots. Now, some of them may be complex, some of them may be real, but the total number of roots is always going to be equal to the degree of the polynomial. So, for example, this is not something that you need to memorize as such, but just for understanding. If you have a quadratic equation, for instance, the total number of roots is always going to be 2. And now one possibility is that both of them are real and none of them are complex, or both of them are complex and none is real. 2 complex and 0 real. These are the 2 possibilities that we can have. We can't have 1, 1. Similarly, if you have cubic, then the total number of roots is 3. One possibility is that all of them are real, or 2 complex and 1 real. The number of complex roots that can never be odd in such polynomials where the coefficients are real. Okay. Now, why is that important? Let's have a look at this example. Let's suppose you've got this equation z cubed minus 3z squared minus 3z4 minus 4 equal to 0. And you're given that z equals 4 is a solution of this equation. What you need to do is you need to find all the complex solutions. So you have a cubic equation. How many solutions is it going to have? 3 solutions. You're given one solution. That's the real solution. How do you find the corresponding complex solutions? Now, if z equals 4 is a solution, that means z minus 4 is the factor of that polynomial. What we can do is we can do polynomial division. We can do division, long division. Divide that polynomial by z minus 4 and we get a quotient from that, and that's the other factor that we have. Now that's the other factor. You equate that to 0. This was the polynomial, this equal to 0. This was the equation. We have factorized that now. Z minus 4 into z squared plus z plus 1 equal to 0. We say either z minus 4 is equal to 0 or z squared plus z plus 1 equal to 0. We can solve that quadratic equation, find the value of z from that. We get 2 values of z, and these are the complex roots that we were looking for. So in complex numbers, the one other topic that is also tested sometimes is polynomials. So you will need to do polynomial division sometimes like this. You'll have one solution given, you'll have to find the other solutions. In this case, the real solution was given. So we said this is the factor. We did long division and found the other factor and the other solutions based on that. Let's look at this example now. Now you're given that you have this polynomial equation. It has one root, that's 1 plus iota square root of 3. Now, given this, you need to find the other two roots. You're given one complex root in this case. In the previous case, you were given the one real root. This is one complex root that's given. Now, if this is a complex root, look at the polynomial. There's no iota in the polynomial. All the coefficients are real. That means if this is one solution, then one other solution has to be its conjugate. So that's 1 minus iota square root of 3, right? Now, you've got two solutions now. How do you find the third solution now that's remaining? We could say, think about this. How do quadratic equations work? If you have, or any equation, any polynomial equation works. If you have an equation like this, you factorize that, you get this, x minus 3 into x minus 4 equal to 0. And then you say either x minus 3 equals 0, x minus 4 is equal to 0, and you get x equals 3 or x equals 4 from that. Now, if you know what the final answers are, and you want to go back to the original equation, how do you do that? You can go backwards like this. You can say, okay, x equals 3, x equals 4. Let's go one step back. And that gives you x minus 3 equal to 0 or x minus 4 equal to 0. And then you multiply those two factors, x minus 3 into x minus 4. And then you go back further and you get that quadratic factor that you started from. So if you have solutions given, you can go back to the original quadratic factor using this method like this. We can do something similar here with these complex roots. We know that these are the solutions. These are the solutions. What are the factors going to be? We bring these terms to the left side. We bring 1 plus iota square root of 3 to the left side, 1 minus iota square root of 3 to the left side. And that gives us that this is one factor and this is another factor. These are two factors. And now what's the next step? We multiply these two factors, right? Just like we did here. When going backwards, we could multiply these two factors so that we can get back to that quadratic factor that we had. So we multiply these two factors now. It becomes z minus 1 minus iota square root of 3 into z minus 1 plus iota square root of 3. And now you have to do this multiplication. Now, since these roots are always going to be conjugates, when this multiplication will always be of this form, it will be a minus b into a plus b. Right? So you can do this multiplication directly like this. You could say z minus 1, for instance, in this case is a, and then iota square root of 3 is b. So this is a minus b into a plus b, and you know that will become a squared minus b squared. The longer method would be that you multiply every term from the first bracket with every term in the second bracket. So z into this, into this, into this, that will be 3 terms. And in total, that will become 9 terms. That's a lot of calculation to do. You could do that if you wanted. But a simpler way of doing this would be to think of it like this, a minus b into a plus b, and that becomes a squared minus b squared. Right? Simplify this further and you get this quadratic factor. So now you know that polynomial has this quadratic factor. How do you find the remaining factor now? You divide that polynomial with this quadratic factor and you get that linear factor that you were looking for, and that will give you the third solution. Right? So this is how you can solve problems like these. When you have one complex solution given, the one other solution is going to be a conjugate, and then you multiply those, you make factors from them, multiply those two factors, you get a quadratic factor that would not have any iota in it. Iota will get eliminated. Then you can do division to find the other remaining factor. This is one way of doing such problems, and you must know this method. But there's an alternative that will work in most problems like this as well, and that is sum of roots and product of roots formulas. Now, what is sum of roots and what is product of roots? Let's say you've got an equation like this, 3x squared minus 21x plus 36 equal to 0. You solve this equation and you get two roots from this, x equals 4 and x equals 3. Now, if you add 4 and 3, you get 7. This is called sum of roots. If you multiply 4 and 3, you get 12. This is called product of roots. So for this equation, the sum of roots is 7 and the product of roots is 12. Now we actually have formulas that we can use to find sum of roots and product of roots of any polynomial directly without actually solving that. We could find sum of roots and product of roots directly. How does that work? For sum of roots, we have this formula that's minus b over a. We could use that to find the sum of roots. For example, in this case, this is ax squared plus bx plus c. The value for a is 3. The value for b is minus 21. Put that in minus b over a, and that gives you 7. That's the sum of roots. The product of roots is given by the constant term divided by the first term. The constant term divided by the first term. So that's c over a in this case, and that gives you 12. That's the product of roots. Now that's very helpful, but let's generalize this for bigger polynomials, and then I'll tell you how to use that. For quadratic, and for any other polynomial, for cubic, for power 4, power 5, the sum of roots has the same formula. That will remain minus b over a, minus b over a, minus b over a. So b is the second highest coefficient of the second highest power, and a is the coefficient of the highest power, right? So this formula for sum of roots will remain minus b over a. But for product of roots, the formula is the constant term divided by the first term. Constant divided by first term. And there's another detail there. When the degree of the polynomial is even, then the formula has a plus sign with it. If the degree of the polynomial is odd, the formula has a negative sign with it, the product one. The sum formula remains the same. That's minus b over a, minus b over a, minus b over a. For the product, if it's in even degree, the formula has a positive sign. If it's an odd degree, the formula has a negative sign. Okay. In general, you could say something like this. If you have a polynomial of this form, ax raised to power n plus bx raised to power n minus 1, and so on, it keeps going on until you have the last term, that's the constant, whatever that is. Sum of roots is given by minus b over a, and product of roots is given by z over a. It will be plus z over a if it's an even degree, minus z over a if it's an odd degree, right? These are the general formulas that you can use. Now, how are they helpful? Look at that same example again that we saw earlier, and we had to do multiplication, find the quadratic factor, and then do long division. And after that, eventually, find the other factor and find the other solution that we got there. But all of that could be done much quicker. We have this equation 2z cubed minus z squared plus 2z plus 12 equal to 0. That same polynomial, it has this solution. We know that one other solution is going to be the conjugate. That's 1 minus iota square root of 3. And now we know this is the polynomial. The sum of roots of this polynomial is given by minus b over a, right? We know that a is equal to 2, b is equal to minus 1. In this polynomial, this is b, this is a. Sum of roots is minus b over a, so that's minus into minus 1 over 2. That becomes plus 1 over 2. And now we know one root, that is 1 plus iota square root of 3. The second root, 1 minus iota square root of 3. The third one is one that we do not know. We call that z3, and we just find the value of z3 from this equation. That turns out to be minus 3 over 2. That will be at least 4 marks, maybe 5, 6 marks question. You can do this directly like this, much quicker, much more efficient, and gets you full marks. That's an alternative that you can use in this problem. Okay, let's move on. Then you have Argand diagrams. To represent complex numbers on a diagram, we have this a diagram called an Argand diagram. It's very similar to the Cartesian plane x-y axis. What we do is, to represent complex numbers graphically, we have this diagram in which the horizontal axis represents real numbers, the vertical axis represents imaginary numbers. So if I had to plot any point, for instance, 3 plus 4 iota, that would mean it's 3 on the horizontal axis, 4 on the vertical axis. That's the point W. If we had to plot another point, for example, 3 iota, where is that going to be? And the real part is 0, imaginary part is 3. That will be this point here. If it's only a real number, for example, minus 2, that will be here on the horizontal axis, and so on. You can see that. Now, on an Argand diagram, we have some terminologies that are there for any complex number. Number one, modulus of a complex number. Then we have argument of a complex number. What's the modulus of a complex number? Modulus is the distance from origin of the point representing the complex number on an Argand diagram. Distance from origin. So for example, if you have this point z 4 minus 3 iota, that's somewhere here. What's the distance from origin? You can find that using Pythagoras. In general, we could say z is equal to, if we have a complex number z equals x plus 4, x plus y iota, the modulus of that is going to be given by square root of x squared plus y squared. That comes from Pythagoras. So for example, if we had 4 minus 3 iota, what's the modulus of that? That's going to be square root of 4 squared plus 3 squared, and that turns out to be 5. That's the distance that this complex number has from the origin. Okay, so modulus of a complex number, that's distance from origin. It's calculated using this formula, square root of x squared plus y squared. Now, the notation that we have for this is this, the modulus sign, or it's also represented by the letter R, as we will see later. Then another thing is defined, that's argument of a complex number. What's argument of a complex number? Argument is the angle made with the positive x-axis by the line joining the complex number and origin. So for example, if I have this complex number 4 plus 5 iota, now that's going to be here 4 plus 5 iota. If I were to draw a line that joins this point with the origin, that's this blue line, the angle that this line makes with the positive x-axis, that's this angle, that is the argument of this complex number. Now, how do you find this argument? You can think of this right angle triangle. You're looking for this angle here. You can use tan for that, right? This is perpendicular. This is the base. Tan theta equals 5/4. And that gives you the value for theta. That's 0.896. Always use radians in general in paper 3, unless a question specifically uses degrees. You will always be using radians. In integration, differential equations, iteration, complex, in these topics at least, you always have to use radians. So this angle turns out to be 0.896, and that's the argument of this complex number. Now, there is a range that we have for argument, and that is that argument is always supposed to be between minus pi and plus pi. So that's the convention that Cambridge uses, that whenever you write an argument, you would write that within this interval from minus pi to plus pi. Now, what does that mean? It's going from, this is 0, this is pi. On the positive side, this is where the interval ends. If you go in the third or fourth quadrant, you'll have to go from the negative direction. That means any complex number in the first or second quadrant, it will have a positive argument, and in the third and fourth quadrant, it will have a negative argument. Let's have a look at some examples for that. Let's say we have a complex number that looks like this, minus 2 plus 2 under root 3 iota. How do you find the argument of this? Remember, argument is the angle from the positive x-axis. That's this yellow line that you see here. Now, minus 2 plus 2 under root 3 iota, which quadrant is this in? The real part is negative, imaginary part is positive. It's going to be on the left side here, right? Top left, that's the second quadrant. That's where the argument is going to be. We are looking for this angle. That will be the argument. This is where the complex number is going to be. The argument is going to come from here, like this. Now, how do you find this? You can think of this right angle triangle. You find the basic angle first of all. It's called this basic angle alpha. Now we know the base of this triangle is 2. The height of this triangle is 2 under root 3. So we say tan of alpha, that equals 2 under root 3 over 2. So essentially what we'll do is we'll divide the y component with the imaginary part with the real part like this, ignoring the sign because we're just looking for the basic angle. Basic angle in this case turns out to be pi over 3. What's the argument then? We find the argument from there. From the positive x-axis, that becomes pi minus pi over 3. That's 2 pi over 3. Similarly, if you were in any other quadrant, if it's minus 7 iota, in which quadrant is that going to be? Real part is negative, imaginary is negative. That means left and down. So it will be in the third quadrant. Now in the third quadrant, we can find the basic angle. Let's call this angle alpha. How do you find that? The perpendicular and the base both are the same in this case, 7 and 7. You say tan alpha equals 7 over 7. The basic angle turns out to be pi over 4, right? That's the basic angle. And then what's the argument going to be? Remember, the interval is from minus pi to plus pi. So if we go from this side, it will go outside the interval. So we'll have to go in the negative direction. This will be the argument. We can say that's pi minus pi over 4. But since we're going in the clockwise direction, you put a negative sign with that. So that's negative 3 pi over 4. That's the argument that we get from this. So first of all, you find the basic angle and then look at which quadrant it is in. Based on that, you write down the argument. If it's in the first or second quadrant, that's going to be positive. If it's in the third or fourth quadrant, that's going to be negative. This is what happens when it's in the fourth quadrant. 3 minus 2 iota, that means right and down. That's fourth quadrant here. Again, you find the basic angle. How do you find the basic angle? Divide the imaginary part with the real part, and that's equal to tan alpha. You'll get the value of the basic angle. Now, since it's in the fourth quadrant, you have to go clockwise, and that's the angle that you get. That's the argument, minus 0.588. That's your argument. This is the general method that you can use. Find the basic angle, use the positive values of y and x, find the basic angle, and then look at which quadrant you are in, write down the angle within this interval. If it's first or second quadrant, the argument is going to be positive. If it's third or fourth quadrant, the argument is going to be negative, right? So that's how you find arguments. Now, using modulus and argument of a complex number, we actually get two other forms of complex numbers, and we call them modulus argument form, or sometimes we can call them polar forms as well. Now, what are these forms? This was the Cartesian form, the first one that we did already, x plus y iota. There are two other forms of writing complex numbers that you need to remember. They're not given in the formula sheet. They're standard forms that you need to memorize. R into cos of theta plus iota sine theta, and R e raised to power iota theta. Now, there's some background to this, where they come from, but that's not relevant for us right now at this point in a revision class. So we have to remember this, right? R into cos theta plus iota sine theta, and R e raised to power iota theta. Now, in these forms, R represents modulus, theta represents argument, okay? So you can write any complex number in these three different forms. Now, how do you get to those forms? How do you write a number in those forms? For example, if you have something like this, z equals minus 2 under root 3 plus 2 iota. If you want to write this number in those other two forms, you need the value for the modulus and the value for the argument. Now, how would you get that? Like using the methods that we discussed before. Use the modulus formula, square root of x squared plus y squared, and that will give you the modulus. That turns out to be 4 in this case. That's the value for r. Find the basic angle. This complex number is in the second quadrant. In the second quadrant, real part is negative, imaginary part is positive. So it's in the second quadrant. You find the basic angle, and that turns out to be pi over 6. Based on that, you can write down the argument. The argument is 5 pi over 6. Once you have that, you can say this number could be written in those two other forms, r into cos theta plus iota sine theta. That would become this. Just input values in place of r and theta, or r e raised to power iota theta. That would become this, right? So you can write that in these two different forms like this. How do you do the other way conversion? For example, if you have the modulus argument form given and you want to go back to the Cartesian form, if you have the cos and sine form like this, in order to go from this form to x plus y iota, you can just put this on your calculator, put cos pi over 3 in your calculator, and that will give you 1 over 2. Put sine pi over 3 in your calculator, that will give you under root 3 over 2. And then just simplify this and you get the result, right? So other way around is pretty straightforward. You just have to simplify this cos pi over 3, evaluate that on your calculator, and similarly for the other one. What if you have the e power iota theta form given? How do you go from this form to the Cartesian form? Now, first of all, you figure out what's the argument in this and what's the modulus in this. How do you do that? This is the original complex number that you're given. Compare it with the standard form, r e raised to power iota theta. What is coming in place of r? In place of r, we've got 6, so that's the modulus. In place of the argument, we have minus 4 pi over 3. You see, you have the negative sign there as well. That's going to be part of the argument. That's minus 4 pi over 3. That's the argument. So now we have this form. In this form, we have the modulus and the argument. What we do is, if you want to convert it to x plus y iota form, first of all, what we do is we write this in the cos and sine form, right? In the cos and sine form, you input the value for r is equal to 6, theta is equal to minus 4 pi over 3, and then just put this on your calculator, put this on your calculator, put this on your calculator, evaluate them, get these numbers, and then just simplify this, multiply 6 inside, and that eventually gives you this complex number in the Cartesian form, right? That's how this conversion is done. Yes, you always use radians here. Always use radians. Do not use degrees. Now, From these new forms, if we had to find modulus and argument, we already talked about e power iota theta form earlier. So if we had 8 e raised to power iota into 2 pi over 3, 8 is the modulus and 2 pi over 3 is the argument. If there was a negative there in the power, that would also be part of the argument. We would say the argument is negative in that case. What about this cos and sine form? So for example, if I had something written like this, what's the argument in this form? 3 into cos of pi over 6 plus iota sine of pi over 6. Compare it with the standard form. In place of r, we've got 3. In place of theta, we have pi over 6. So we say the modulus is 3 and the argument is pi over 6 in this case. But sometimes what happens is you end up getting something negative like this. Cos of 3 pi over 4 minus iota sine of 3 pi over 4. What about this? The standard form that we have looks like this: r into cos theta plus iota sine theta. Now, how can this number be negative when it's supposed to be positive in this form? Where does this negative come from? We basically have these identities, trigonometric identities. When you have sine of minus theta, that is the same thing as minus sine theta. And when you have cos of minus theta, that is the same thing as cos of theta. So if you have a minus sign inside the sine function, that minus comes outside. If you have a minus sign inside the cos function, that disappears. That just gives you cos theta. Now, why is that important? Because in this form, when you have a negative sign here, this negative sign is actually coming from the argument. The actual form was this. So they wrote it in simplified form and asked us to find the modulus and argument from this. The actual form was actually like this. There was a negative inside the argument here, minus 3 pi over 4. There was a negative inside this argument here, minus 3 pi over 4. And in the middle, we had a plus sign here. That was the actual form. However, if you were to simplify this, as I just told you, the minus sign inside the cos, that disappears. So that could be simplified to this. And the minus sign inside the sine function, that comes outside. That's why this becomes negative. So the argument from this would actually be minus 3 pi over 4. The modulus is 3. So in problems like these, now you can just remember, whenever you have a negative sign here, that means the argument is negative, right? You can just remember it like this. Whenever this is negative, that means the argument is negative. You can also think of it like this. Imaginary part is negative, right? Imaginary part is turning out to be negative. If the imaginary part is negative, then that has to be below the x-axis, right? So that's where the argument is negative, right? So you can also remember it like this. So just remember, when you have a negative sign in this form, that negative is going to go with the argument. The argument is going to be negative, right? And that's the logic behind it. Now, in some recent papers, you would see that they want you to find the modulus and argument from power forms like this as well. So you have this power like this, 3 into cos of 2 pi over 5 minus iota into sine of 2 pi over 5 whole raised to power 4. Now, what's the modulus of this complex number and what's the argument of this complex number? Now, if we were to simplify this, simplification of this is quite complicated because we've got a minus b, we've got two terms, and we have to evaluate power 4. We'll have to use binomial expansion for that. That becomes pretty complicated. When you have to evaluate powers, of complex numbers, the best form for you for using there is the re raised to power iota theta form, because evaluating powers becomes very straightforward in that form. There's no plus minus involved here. You can just multiply the power with the existing power. I'll show you how. So this is the complex number, right? 2 pi over 5, cos 2 pi over 5 minus iota sine 2 pi over 5, and we've got 3 outside. What we can do is we can say, look at this complex number. The modulus of this complex number is 3, and the argument of this complex number, because of this negative sign, that's minus 2 pi over 5. That's the argument. So we can write this in re raised to power iota theta form. That's the easiest form to work with when you have to evaluate powers. So write it in this form: re raised to power iota theta. R is 3, theta is negative, so we have minus iota into 2 pi over 5 whole raised to power 4. Now we can evaluate the power. 3 raised to power 4, that becomes 81, into e raised to power iota, e raised to power minus iota into 8 pi over 5. So now what's the modulus? The modulus is 81. What about the argument? From this form, the argument appears to be minus 8 pi over 5, right? However, they would have the condition given in the question that the argument has to be between minus pi and plus pi. This is not in that interval. This is outside the interval. Now, where is minus 8 pi over 5 going to be? It's actually going to be like this. This is minus pi, and then you go beyond that. It'll be somewhere here, actually. This is the angle that we're talking about. Now, that's outside the interval. How do you bring that inside the interval? You can go one full circle, 360 degrees. That's 2 pi radians, right? So in order to get back to the same point, by doing one full circle, how do you do that? You either have to do plus 2 pi or minus 2 pi. So you can try that. Try plus 2 pi, minus 2 pi, whichever of them gives you a result that is within that interval. So this is minus 8 pi over 5. This is not in that interval. What you can say is this is negative, right? If you want to bring it inside the interval, what you can do is you can add 2 pi to it, plus 2 pi. And what does that give you? That gives you 2 pi over 5. That's the argument that you have that falls inside the interval. That will be the argument of this complex number. So if your argument is going outside the interval, what you do is you try doing plus minus 2 pi to bring that inside the interval, because 2 pi, that completes one full circle and you get back to the same point. And that will bring your number inside the interval if it is outside the interval right now. So that will be the argument 2 pi over 5. So when you have powers to evaluate like this, you can convert them to this form and then evaluate the powers. Now, there's a theorem that we have here that's not explicitly part of your syllabus, so you don't necessarily have to be able to do it. You can just do this working, but it makes things a lot simpler. If you have cos theta plus iota sine theta whole raised to power n, this actually simplifies to cos of n theta plus iota sine of n theta. If you want, you can use this directly. So when you have a power in this form, cos theta plus iota sine theta whole power n, that power comes down and gets multiplied with the theta. Okay, so if you look at that same example again, the example that we saw earlier, we could do that directly like this as well. We could say, without conversion, 3 raised to power 4, that's 81. And now we have seen what happens in this case. The power will just come and get multiplied with the argument. So 2 pi over 5, that will become 8 pi over 5. And now you could say the modulus is 81. And what about the argument? There's a negative sign here as well, right? The argument is minus 8 pi over 5. And that when you add 2 pi to that, that gives you 2 pi over 5. That's the argument, right? You can do it directly like this as well without even doing that working. If you remember this theorem is called the Mover's theorem. It's part of the further math syllabus, but you're allowed to use this as well if you want. That will save some time for you. Okay, let's move on. Now, the next thing that you need to know about is properties of products and quotients of complex numbers. What does that mean? When two complex numbers are multiplied, we need to know what happens to their modulus and what happens to their arguments. When two complex numbers are multiplied, you can see this working here, the logic behind it, the background of it. But we get this result that whenever two complex numbers are multiplied, their moduli are multiplied and their arguments are added, right? So let me just show that to you quickly. When you multiply these complex numbers, you see 20 and 4, they will get multiplied and will give you 80. So the modulus is the product of the individual moduli. When you multiply e power iota pi over 6 and e power iota pi over 4, bases are the same, so the powers get added, right? So powers get added, that means the arguments get added. When you multiply two complex numbers, the moduli get multiplied, the arguments get added. When you divide two complex numbers, the moduli get divided and the arguments get subtracted. Okay, so for instance, if you had these two complex numbers and you were asked to figure out what's the argument of z1 into z2, how would you do that? You would just sum their arguments, 2 pi over 3 plus 5 pi over 6. Now you add them up together, and that will be the argument of the product. Now in this case, that's turning out to be 3 pi over 2. That's going outside the interval. The interval is this. How do you bring that inside the interval? You can try plus 2 pi or minus 2 pi. Plus 2 pi will make it even bigger. Minus 2 pi, that brings it to minus pi over 2, and that falls in the interval. So we say the argument of that product is minus pi over 2, and that's your final answer. Okay, that's the argument here. So these are properties that we've got that you need to remember. If you have argument of u times v, that will be the same as argument of u plus argument of v, right? Argument of a quotient, that will be argument of the numerator minus the argument of the denominator. For modulus, we've got the same rules. If two modulus are multiplied, we if the two complex numbers are multiplied, their moduli are also multiplied. If two complex numbers are divided, then their modulus are also divided. Arguments, on the other hand, get added and subtracted respectively. Okay, let's have a look at this example. So you'll have to use these properties often when you are asked to prove equations like these. Now, the first part is straightforward here. I've skipped that. In the second part, it says, find WZ. So you've got two complex numbers given, W and Z. They ask you to find WZ first of all, so you can evaluate that, multiply those two complex numbers. That turns out to be 17 plus 17 iota. And then they're saying, by considering arguments, even if they're not said that, you would understand from this equation, that you have to use the properties of arguments. Whenever they say tan inverse of something, and that's part of an equation, or tan of something that's part of an equation in the case of complex numbers, you have to use these properties of arguments, that they get added when numbers are multiplied and so on. So in this case, we've got two numbers multiplied, W and Z, and that's giving us 17 plus 17 iota. W is 5 plus 3 iota, Z is 4 plus iota. Can we find the arguments for all of them? Argument of W, it's in the first quadrant. This is also in the first quadrant. This is also in the first quadrant. All of these are in the first quadrant, right? So their basic angles are going to be the same as their arguments. You can find the argument for each one of them. For the first one, it turns out to be tan inverse of 3 over 5. Now you keep it in this form. Do not convert to decimals, because the equation that they want, they have exact values there. So tan inverse of 3 over 5, we got that there. Find the argument of this as well, tan inverse of 1 over 4, right, for this. And for WZ, it becomes tan inverse of 1. Tan inverse of 1, it actually is an exact value, and that's pi over 4. So now you're getting that the argument of WZ is pi over 4, and the other two arguments are these two. Now you can use that property. You'll clearly write this, that argument of W plus argument of Z, that should equal argument of WZ, right? That's the property that we did earlier. So we could say, when these two are added, that should equal pi over 4. And that's the equation that we wanted to prove there. Okay, let's look at another example of this. I'll skip the first couple of parts. They aren't that complicated. In the last part, they say, by considering the argument of u over u conjugate, prove this thing. Again, you have an equation that has tan inverse in this. You have two complex numbers dividing, u and u conjugate. U is this, u conjugate is this. And you've also evaluated u over u conjugate, and that is this. When two complex numbers are divided, what happens to their arguments? Argument of u over u conjugate, that should equal argument of u minus argument of u conjugate, right? So you can find the individual argument, find the argument of u that's in the first quadrant, that is tan inverse of 4 over 3. Find the argument, argument of u over u conjugate, this is in the first quadrant. Tan alpha equals 4 over 5 over 3 over 5. Find the basic angle, that will be the same as the argument, and that turns out to be tan inverse of 4 over 3 here. Then you find the argument Then you find the argument of u, that's also in the first quadrant. So that's tan inverse of 1 over 2. Then you find the argument of 2 minus iota, that's in the fourth quadrant now. Find the basic angle. The basic angle turns out to be tan inverse of 1 over 2. However, since it is in the fourth quadrant, that means it has to be negative. We'll have to go in this direction. The argument would be minus tan inverse of 1 over 2. That will be the argument. Okay, now we've got these three arguments, put them in this equation. Argument of u over u conjugate, that should equal argument of u minus argument of u conjugate. Simplify that and you get that result that they wanted. You can prove that equation like this. Okay, all right. Let's move on. Finding square roots of complex numbers. That's another thing that you have to do. How do you find square roots of complex numbers? Now you need to be able to do them in both x plus y iota form and the other form r e raised to power iota theta form. If you have a complex number in this form and you want to find the square roots of this complex number, how would you do that? Now, this is the standard process that you will use for this. It's generally a 5-mark question, sometimes even 6. You say, let x plus y iota be a square root of that complex number. Then what we're looking for is x plus y iota, that should be equal to 1 minus 2 under root 6 iota power 1 over 2, right? That will be the square root of that. But evaluating power 1 over 2 is very difficult, right? How do you do that? You'll have to use binomial, and that has infinitely many terms. So that does not help. What we do is we say, let's bring this to the other side. So it becomes x plus y iota whole squared. That equals this. You get an equation like this. And now you just solve this equation. How would you do that? You simplify the left-hand side. Simplify the left-hand side. Put iota squared as -1. This is what you get. You've got a real part on the left side. You've got an imaginary part on the left side. Similarly on the right side as well, you've got a real part and an imaginary part. The real part should, if these two complex numbers are equal, their real part should be equal to each other, and their imaginary part should be equal to each other. From that, we get two equations: x squared minus y squared equals 1, and 2xy equals minus 2 under root 6. You solve these two equations simultaneously. When you do that, you'll have to make one variable the subject from the second equation, either y or x, put that in the other equation. You would get a quartic equation. This is a quartic equation. Now, sometimes in questions, they will say, make a quartic equation to find square roots. Now, do not get confused by that. You just have to follow the same standard process. This equation that you're getting here, this is a quartic equation. Quartic equation is power 4 equation, right? You will automatically get that when you do that. When you solve it simultaneously. Now this is a disguised quadratic then, right? Powers are in the ratio 2:1. One power is double the other. So we can use the substitution to make it a quadratic. Solve that quadratic, put that substitution back at the end, and we get two values of x from this. Remember, x is supposed to be a real number. X is supposed to be a real number. So you ignore the case when you have x square equals -2. You don't write iota there. The value for x that you're getting, the possible values of x that you're getting are plus minus under root 3 from this. Put them in the other equation now, and that will give you the corresponding values of y. And you get two square roots from this. 3 under root 3 minus under root 2 iota minus under root 3 plus under root 2 iota. And notice these square roots are negative of each other. They're not conjugate. They're not conjugates. They're negative of each other. For example, just like for real numbers, if 16, if we take square root, if you find square roots of 16, they're plus minus 4. In complex numbers as well, it's going to be plus minus something. So you can see this is one. The other one is just negative of that. Multiply that by negative, you get the other one. These are not conjugates. Okay, they're negative of each other. These are two complex numbers these are two square roots that we were looking for. Now, be careful about the terminologies. This is square root. Root is different. Root means solution of an equation, right? Square root is something totally different. They're not related. Okay. Now, this is very important. You need to know how the square roots of complex numbers are related to each other. So if you have one complex, if you have one square root, so let's actually plot them on an Argand diagram. One was under root 3 minus 2 iota. So one square root is here, and the other square root is here, minus under root 3 plus under root 2 iota. Now, what's the relation between them? How are they connected to each other? These square roots are 180 degrees or pi radian rotation of each other about the origin. Square roots are always pi radian rotation of each other about the origin. It's true for real numbers as well. If we have 6 here and minus 6 there, square roots of 36, for instance, they are pi radian rotation of each other. And it's true for complex numbers as well. Any two square roots of the same complex number, two square roots of the same complex number, they are pi radian rotation of each other. Okay. Now, why is that important? Because you will need to find square roots of the complex numbers of complex numbers in this form as well. You have to find square roots of complex numbers in this form as well. So sometimes you will get a complex number in this form, and they would want you to find the square roots of that in the same form. Now, one way could be that you convert it to x plus y iota form first, and then you follow all of that process, and then you convert it back to r e raised to power iota theta. But that will be too much work, and this is actually going to be less marks than the other one, because this is going to be easier and quicker. How do you do that in this form? Now, in the previous form, because of that plus or minus in the middle, evaluating power 1 over 2 was difficult, right? But in this case, in r e raised to power iota theta form, in this case, evaluating powers is not that difficult. So finding square roots could just be done like this directly. We could say we have 4 e raised to power minus iota pi over 6. Just take square root on both sides. On the right side, the power is 1 over 2. So 4 raised to power 1 over 2, that is 2. E raised to power minus iota pi over 2, pi over 6, you multiply that by 1 over 2, and that becomes pi over 12. And this is what the square root turns out to be, 2e raised to power minus iota pi over 12. Now that's one square root. What about the other square root? It's not going to be plus minus. Plus minus is not in this form. That's only in Cartesian form. You cannot have a negative sign here because this number outside represents the modulus. Modulus can never be negative, so you would not put minus here for the other square root. The other square root, as we discussed earlier, is supposed to be pi radian rotation of this about the origin. That's why that transformation was important to understand. If you have one square root, that is, for example, here, the other is going to be pi radian rotation on the other side. Now, if it's going to be a rotation, that means the modulus is going to remain the same because the distance from origin, that will remain the same, that will not change. What about the argument? What about the argument? If this argument is minus pi over 12, what is the other argument going to be? How do you go from this to this? It's a pi radian rotation. You could say the other argument is going to be minus pi over 12 plus pi, and that gives you 11 pi over 12. That will be the argument of the other square root. That's 11 pi over 12. So you say the other square root is therefore 2e raised to power iota into 11 pi over 12. And that's it. These are the two square roots that we were looking for. So what you'll do is you'll put a power 1 over 2 there. You'll find one square root from that directly. And then if the argument of that first complex number is negative, of that first square root is negative, you add pi to that to get the other argument, right? So pi radian rotation means you could either do plus pi or minus pi, both will work, right? However, in this case, if you do plus pi, you get something inside the interval. If you do minus pi, you get something outside the interval. So you should be doing plus pi so that you get something inside the interval that's minus pi to pi. So that's what we do. Square roots are pi radian rotation of each other. All you have to do is, let's look at this example now. To find one square root, just put power 1 over 2. and that will give you one square root directly. This is the first one. For the other square root, the modulus will be the same. For the argument, you just do either plus pi or minus pi, whichever gives you an answer inside the given inside the interval from minus pi to pi. In this case, the original argument is positive. If you do plus pi, that will go outside the interval. If you do minus pi, that will be inside the interval. So you do minus pi to get the other argument, and that's the square root. That's the other square root that you were looking for. So this is the standard method that you have. Finding one square root is fairly straightforward. Finding one square root is fairly straightforward. For the other one, what you have to do is the modulus will remain the same. For the argument, if the first argument was positive, you subtract pi from that to get the second argument. If the first argument was negative, you add pi to that to get the second argument. Okay. If the first one was positive, you subtract pi. If the first one was negative, you add pi. Okay. All right. If it is already positive and you add pi to that, that will go outside the interval. Right? That will not be inside the interval. So that would not make sense. You have to be inside this interval, right? From minus pi to pi. So that's how you find the other square root. Now you can see that this method is much quicker, right? Finding square roots in this form is much quicker. So there's a question, could we just convert this complex number to r e raised to power iota theta form first? Find the square roots in that form and then convert them back to x plus y iota form. That's possible, but that will be too much work as well. You're doing one conversion and then the other conversion. It's not going to be very helpful. And in some cases, it's not going to be even allowed, because in recent papers, you will see they often say, make a quartic equation and then find the square root. So when they say make a quartic equation, that means that you have to follow this method so that you get that quartic equation, and then you solve, then you find those square roots. So sometimes that is going to be necessary. So you have to know both of these methods. Okay. One for x plus y iota and the other for r e raised to power iota theta form. Let's move on. Okay, next we've got loci. We have loci in complex numbers. Now there are three different types of loci that you would have here. Number one, fixed distance from a point. If you are at a fixed distance from a point, that locus is a circle, right? If you have 4 centimeters from O, for instance, that means it's a circle with radius O, with radius 4 centimeters and center at the point O. If you are at an equal distance from 2 points, that's a perpendicular bisector of those 2 points, right? These are two loci that you have. And the other one, the third one will be of argument. We'll talk about that later. Now, how are these loci related to complex numbers? Let's think about that. Now, before we do that, remember, whenever you draw Argand diagrams, use the same scale on both axes. Use the same scale. Whatever is 1 unit on the horizontal axis, it should be the same thing that is 1 unit on the vertical axis. Do not use different scales, otherwise your circles are going to look like ovals. Your perpendicular bisectors are not going to be good, and that will not be acceptable. You will draw these diagrams accurately. You will measure on the ruler and mark those points properly, 1 centimeter, 2 centimeter, and so on. Okay. Now, and you will be drawing circles with compass, perpendicular bisectors with compass ideally as well, so that the diagrams are accurate. Okay. Now, how is loci related to complex numbers? Let's say you've got modulus of z equal to 3. What does that mean? Modulus of z, what does that represent? Modulus represents distance of z from origin. So if distance of z from origin is equal to 3, what we're saying is there's a point z, its distance from origin has to be equal to 3. Distance from a point is fixed. That's a circle. It will be a circle of radius 3 units and center at the point O. Okay. If we have modulus of z less than or equal to 3, what does that mean? Distance of z from origin, that should be less than or equal to 3. So you make a circle and you shade the inner part of the circle. And that's the region that satisfies this condition. Now, What if you have something more complicated like this? Modulus of z minus 2 equal to 4. Now for this, you need to know a notation. And that is whenever you have z minus something, modulus of z minus something. What does this notation mean? It means distance of z from this point. Okay, this notation means distance of z from this point. Z minus something modulus of that. Okay. So for example, if you have z minus 2 modulus that equals 4, what that means is distance of z from the point 2 that is equal to 4. So what's the locus going to be? It's going to be a circle with this point as the center and this as the radius of the circle. Okay, so you draw a circle like this with 2 as the center and radius equal to 4. If you have z plus 2 minus 3 iota, now this is not the standard form. So the first thing you have to do is you always have to convert it to the standard form. What's the standard form? Z minus something. Okay, so you have to convert it to that form first of all. You take minus common from these two terms, and that becomes this. And now this is the center of the circle, and this is the radius of the circle, right? Minus 2 plus 3 iota is the center, and then 2 is the radius. You draw that circle there. Now, from this, we actually get a form for equation of a circle as well. Sometimes they may ask you, I have seen a couple of questions like this in past papers, where they ask you to write down the equation of a circle in this form. Okay, so this is another. So one form is what you've done in coordinate geometry before: x minus a whole squared plus y minus b whole squared equals r squared. But in complex numbers on an Argand diagram, we can use this form for equation of a circle as well. Z minus some expression, z minus that point. Modulus of that equals r. The number on the right side, that represents the radius, and this represents the center. Okay, you can write it. So this is equation of a circle. This is equation of a circle with minus 2 plus 3 iota as the center and 2 as the radius. What if you have this? Z minus 1 plus 2 iota, modulus of that equals modulus of z plus 3. Now, first of all, you have to convert it to standard form. Before that, you cannot do anything. The first thing is to convert it to standard form, z minus something. Now, it looks like you have z minus something here, but no, you have to take minus common outside. Take minus common, that leaves you with 1 minus 2 iota inside. On the right side, you have z plus 3, right? That is z minus minus 3. So now this is the point that we're talking about. This is the point that we're talking about. We're saying z is such that its distance from 1 minus 2 iota is equal to the distance of z from this point. Now we're talking about 2 points. We're not talking about 1 point anymore. We're talking about distance from 2 points. Distance from 2 points is equal. What kind of locus is that? That's a perpendicular bisector. What we do is we mark these 2 points. One point is minus 3 and the other point is 1 minus 2 iota. We mark those 2 points. And then the locus is going to be the perpendicular bisector of those 2 points. It has to pass through the midpoint of the line joining those 2 points and should be perpendicular to that line. Okay, perpendicular bisector. You can use a compass for this. If you're not using a compass, still draw it as accurately as possible. You can mark the midpoint and then make a right angle here using a set square or a ruler. Make sure that the angle is 90 degrees. Okay. It has to be reasonably accurate. That's important. Now, you could have inequality here as well. Again, you convert it to standard form, and then you're saying distance of z from this point is greater than distance of z from this point. What does that mean? Which point is z closer to? The distance is more from this point and less from this point. So that means the point is closer to minus 3. The point z is closer to minus 3. So what you would do in this case would be you would draw a perpendicular bisector and shade the side on which you have the number minus 3. Shade that side on which you have minus 3. Okay. It's not going to be that when you have a greater than sign, you shade the upper region, you have minus and you shade the lower region. No. You have to think about which point you are closer to. Which point you're closer to. So you're closer to minus 3. So you shade this side on which you have -3, you shade that side. Okay. Now it's a strict inequality. You could draw a dotted line here as well because the points on the line, they are not included. However, in A levels, they don't deduct marks for that. If you have greater than or greater than equal to, both of them are normally dealt with the same way. It doesn't make any difference. What about argument? So you have, this is another locus that you have. Argument of z equals 2 pi over 3. This is the third type of locus that you can have. Z is a number such that its argument is 2 pi over 3. Now, where is argument going to be measured from? From the positive x-axis, right? That's where you measure argument from. Now, what's the argument? This is 2 pi over 3. So from that point, from that line, you measure 2.2 pi over 3, and you draw a line like this. That is going to be the locus of this point, right? From the origin, you have a line in this direction. But here as well, you could have z minus something, z plus something. Now, in this case, how do you understand this? This is the standard notation that we've got. Argument of z minus some expression. We would say this means argument of z from the horizontal line drawn to the right side of that point. So we will be measuring the angle from that point. If we draw a line on that point, the angle will be measured from that point. For instance, if you have argument of z minus 2 iota, and that is equal to minus pi over 6. What do we do for this? What's the point that we're talking about? We're talking about 2 iota. Where is 2 iota? This is the point 2 iota. We draw a horizontal line, this yellow line. You don't necessarily have to draw this. You can draw a dotted line like this, like I've drawn here. Draw a dotted line. The argument has to be, the angle has to be measured from this line now. What's the angle? That's minus pi over 6. Minus pi over 6 is on this side. It's you go clockwise. My pi over 6 is 30 degrees. So you roughly draw that angle. You can ideally use a protector for this. Or you can do it without that as well. That's going to be acceptable. But I would recommend still that you do it using a protector better, because a lot of times you have a next part to this question in which you have to do some calculation. And that becomes much simpler if you've drawn the diagram accurately. It makes it easier for you to understand what's happening in that situation. So I would recommend that you draw it accurately, especially if there's a calculation part after this. If they have something like this, argument of z plus 2, that is between minus 2 pi over 3 and pi over 6. First of all, you convert it to standard form. This is z plus 2. You say this is z minus minus 2. So now we're talking about the point minus 2. That's that point of reference. Mark that point minus 2. This is the point. And this is the point minus 2. So the argument is going to be measured from that point. So this yellow line that you see, we're measuring argument from that. One argument is minus 2 pi over 3, that's minus 120 degrees. And that is in this direction here. And the other is pi over 6, that's in this direction, 30 degrees. And then they're saying the argument is between these two values, So you shade this region like this, right? Like I've done here, this green part, that's the part that satisfies both of these conditions. This is another example. If you have argument of z minus 2 plus 3 iota, again, you convert it to standard form. The reference point, the point of reference is 2 minus 3 iota. So argument will be measured from that point. Now, when you have an angle of pi over 4, or 3 pi over 4, or minus pi over 4, these are very important to be drawn accurately. What's pi over 4 angle? Pi over 4 angle is 45 degrees. 45 degrees. When you have a 45 degree line, it always has a gradient of 1, right? It has a gradient of 1. And whatever distance you're traveling horizontally, it should be the same distance that you travel vertically, right? Because it's an isosceles triangle that you get like this. So opposites, these sides have to be equal to each other. So with a pi over 4 angle, whatever distance it is that you're traveling in one direction, it should be the same distance that you travel in the other direction, as in horizontal direction, vertical direction. For example, in this particular case, you're measuring argument from 2 minus 3 iota. Let's mark that point here. 2 minus 3 iota, that's this point here. What's the argument? Pi over 4. Pi over 4, that's the argument. Now, you would draw a line here like this. Measure pi over 4, 45 degrees, right? Now, this line that you draw, it must pass through this point 5. It should not be to the right of 5, to the left of 5. It has to pass through 5. Why? Because the vertical distance from this point to the x-axis, how much is that? That's 3 units. So if you're going 3 units up, you have to go 3 units right. So that means you have to pass through this point. If it's not passing through point 5, that will be wrong. Okay. And if there's a calculation part after this, it's very unlikely that you'll be able to do that. Okay. So for pi over 4 lines, you have to be very careful. Similarly, minus pi over 4 will be 45 degrees in this direction. 3 pi over 4 will be 45 degrees in this direction. So whatever is the distance you are traveling in one direction, it should be the same distance that I'm traveling in the other direction. That's important for pi over 4 lines. Yes, that's what I said earlier as well. You have to plot the points, measuring them using a ruler. As in, you have to mark these points on these axes with measurement, right? You can say 1 centimeter for 1 unit. Place a ruler and mark the points using that. Okay, that's important. Otherwise, if the diagram is not accurate, the calculation part becomes even more difficult. Okay, now based on these loci, you would have to do some calculation sometimes. They will ask you to find greatest value of modulus of z, least value of modulus of z. Modulus represents distance from something, right? Now, there are two types of loci that you have. One is a line and the other is a circle, right? Now, when you have to find the least distance from a line, that distance is always perpendicular distance. So for example, let's say they have this locus that's a line, and they say, find the least value of modulus for points on this locus. Now, let's say this is the origin. What's the least modulus going to be? The shortest distance from origin to that line, that's always perpendicular distance, right? Shortest distance from a point to a line, that's always perpendicular distance. What if the locus was a circle? So let's say the point z could be anywhere on the circumference of the circle, and what you want to do is you want to figure out the shortest distance from a point to the circumference of the circle. So for example, they might ask you, what's the least value of modulus? How do you find that? Least value of modulus again is going to come when you have a line that makes 90 degrees with the circumference, right? What would that line be? Normal to the circle, right? If you were to extend that, that will actually pass through the center of the circle. So shortest distance is going to be, you draw a line from that point to the center of the circle, where that line cuts the circumference. Until that point, this distance is the shortest distance. How do you find that? You would have the point O, you have the point R as point C. You can find the distance between O and C, subtract from that the radius, and that will give you that shortest distance. What about this largest possible distance, the greatest possible distance from origin to a point on the circumference? For that, what you would do would be, you would say, start from here. What's the greatest distance? You can go here, go to the other side, and go all the way on the other side like this, such that you pass through the center of the circle and then cut the circumference on the other side. That will give you the greatest distance from a point to the circumference of the circle, right? That's the greatest distance that you have in this case. Passing through the center and going and cutting the circumference on the other side. This distance is OC plus R, right? That's the greatest distance. So when they ask you for greatest modulus, that's something that you may have to use sometimes as well. And then what about arguments? For example, let's say you have a point O here, and you want to find the locus is a circle like this. Okay. You want to find the least argument for points on this circumference. What's the least argument going to be? Argument is measured from the x-axis, right? So this is where the argument is going to be measured from a horizontal line, right? keep increasing this angle. What's the first time that you touch the circumference? That's this point here, such that you make a tangent at this point. This angle is going to be the least argument. What about the greatest argument? That would be that you make a line like this from that point again. You keep increasing, keep increasing. How do you maximize this angle? When the line touches the circle on the other side, that is when the argument, that's when the angle is going to be maximized. It's called that angle beta. This is the maximum argument, the greatest possible argument that you can have here. Okay, and how do you find these values now? When you have two tangents, remember that circle property, you would always break it down like this. We'll make a line from that point to the center of the circle, so that you get two right angle triangles like this. And then using those right angle triangles, you can find these arguments somehow. Using those right angle triangles, you would have some lengths, like you'll have radius there, you'll have this distance from O to C. You can use that to find some angles. Similarly, you'll have the point C, you'll have the point O. You can also make a right angle triangle like this, and that will give you some lengths as well, some angles as well. Okay, so you can use those properties to find this. Kite property, you can call it that. It's that circle property in which you have two tangents coming from outside the circle, right? You get a kite like this, you break it in the middle, you get two congruent triangles. You can use those triangles to figure out the angle, right? That depends on the question. So these are all the different concepts that you have in complex numbers. Now let's have a look at some questions quickly. On complex numbers, I'll go through them quickly. You have the notes with you. You can go through them in your own time as well later on. Now, when you draw loci, a lot of times they give you two conditions at the same time. For example, here, they're saying modulus of z is less than modulus of z minus 2, and argument of z minus u is between 0 and pi over 4. Now, in this case, there was a first part to this question in which u was given to be minus 2 plus iota, right? U is minus 2 plus iota. That's given in the question. Okay, that's not something that we're assuming. That is given in the question statement. Okay, now, how do we draw these loci? Modulus of z is less than modulus of z minus 2. We can think of modulus of z as modulus of z minus 0, right? So we're talking about distance from origin. Distance of z from the origin, that is less than the distance of z from 2. We're talking about distance from 2 points. When we talk about distance from 2 points, the locus that we draw is a perpendicular bisector. So we'll be drawing a perpendicular bisector here. For those 2 points, one is 0 and the other is 2. What's the perpendicular bisector going to be? It's going to be a vertical line at 1, right? That's the perpendicular bisector. And now the condition is distance from 0 is less as compared to distance from 2. Which side should we shade? It's closer to 0 because distance from 0 is less, right? And it's far away from 2. So the side on which you have 0, that is the side that's going to be shaded. So for this vertical line, 0 is on the left side. So you shade the left side because of that, right? So left side is what you would consider. But that's not the only condition that you have. You have another condition as well. And that is that the argument of z minus u, that is between 0 and pi over 4, we are given the complex number u. U is minus 2 plus iota. We can mark that point here. This is the point minus 2 plus iota. So argument will be measured from that point. Minus 2 plus iota, at that point, we could draw a horizontal line and measure the argument from there. One is 0. So we have a line at 0 here like this. And the other is pi over 4. Now, again, as I said, you have to be careful about pi over 4 angles, 45-degree angles. Whatever distance you're traveling horizontally, it should be the same distance. It should be the same distance that you're traveling vertically. Okay, so if you're traveling 2 units horizontally, you have to be traveling 2 units vertically. So this line has to pass through 3 here. That's necessary. Okay, so that's the other line. And you have to be between these two lines. So between the two lines and to the left of that vertical line, what's that region? That's this green shaded region that you have. That satisfies all of those conditions. That is what you would shade there. It does not matter if the line is shaded or if the line is dashed or not. In A levels, they do not deduct any marks for this. Okay. You could also remember it like this: when you have an inequality, shade the side towards which the inequality is no, not the side. Look at the side to look at the point to which the inequality is pointing. So this is an inequality, right? It's a less than sign. The pointed side is towards zero. So the inequality is pointing towards zero. So you will shade the side that has zero. Okay. So that's not logical, but as in, that's just a way to remember. I told you the logic behind that, as in it has to be close to zero. But if you just want to, not think much, you can say whichever point the inequality is pointing towards, you will shade that side, right? So it's pointing towards zero. So whichever side zero is on, that will be the side that you shade. Okay. All right, let's move on. This is another example. Again, you're given two inequalities here. Perpendicular bisector of 1 and iota, you would draw that. And then you have to be closer to 1, right? 1 and iota. So 1.1 is this, iota is this. Perpendicular bisector of these two is going to be the y equals x line, right? Because this looks like this. It's a -1 gradient. When you draw perpendicular bisector of that, that will be the line y equals x, a 45-degree line like this. Okay. The other is modulus of z minus u is less than or equal to 1. So distance of z from a point that is less than or equal to 1. We're talking about 1 point here. So that's a circle. Center of the circle is going to be u, which is 2 plus 2 iota. And the radius is 1. So you draw that circle. You have to be inside that circle and towards the point 1. So inside the circle towards the point 1, that gives you this semicircle. When you draw this accurately, you'll get this semicircle. Okay. That's what you shade there. And then they're saying, use a diagram to calculate the value of modulus of z for the point in this region for which the argument of z is least. Now, what does that mean? We want to find out modulus of z for the point for which argument of z is least. Now, where is the argument least? You measure argument from the origin, right? Where is the argument least? Where is the argument least? That's going to be when you have a tangent here at this point A that I've marked, right? This point A is what we're talking about. This is the point at which the argument is least. At this point now, we have to find the modulus. How do you do that? You can make a right angle triangle. Whenever you have a tangent, you draw a right angle triangle like this. And using that right angle triangle, you can find whatever is missing. So the radius is 1, you know the side is 1. And you know the distance between the origin and the center. You can find that, right? Using distance formula. So you find that distance turns out to be square root of 8. Use Pythagoras to find the length of OA, and that turns out to be under root 7. You say that's the value of the modulus of z at that particular point, right? So you have to do these calculations. Based on this locus. Okay. They have to be passing through the points through which they have to be passing, right? For example, if you draw a circle of radius 1 and center is at 2, 2, you have to make sure that on the left side it goes up to 1, on the right side it goes up to 3 here, below it goes up to 1, up it goes up to 3, right? So you have to make sure that is happening. If you have a pi over 4 line, you have to make sure, as I said, it's traveling the same distance horizontally and vertically. Okay. All right, let's move on. This is another example. You can have a look at this. Modulus of z less than or equal to 3. That's inside the circle. Real part of z is greater than or equal to -2. What does that mean? Real part is plotted on the horizontal axis. So if real part of z is greater than or equal to -2, what that means is horizontal axis is x, right? So we're talking about this. X is greater than or equal to -2. So you draw the line x equals 2. What's that line? That's going to be a vertical line. This line here. This represents when real part of z is equal to -2. Greater than or equal to -2, that means you have to be to the right of this. And then you have this argument condition as well. You shade the region that satisfies all of those conditions. You can see that here. Okay, let's move on. Now, this is a fairly tricky one. Look at the second diagram, second question, the second part of this question. Argument of z minus 2 iota, that is equal to pi over 6. And modulus of z minus 3 is modulus of z minus 3 iota. They intersect at the point P. So you draw those two loci, and they intersect at this point P. And they want you to represent the number P in the form re raised to power iota theta, such that you have the exact value of theta. R can be in decimals, but the value of theta has to be exact. How do we do that? So when we draw these loci, for the two loci that we have are, you have this 3 here, the other is 3 iota. You mark those 2 points. You've got this point 3 here, this point 3 iota here. When you draw perpendicular bisector of this, it's going to be the y equals x line. It has to pass through the origin. If you don't draw this accurately, you will not be able to do the second part. So when you draw perpendicular bisector of this, it passes through the midpoint and passes through the origin because of it being perpendicular to that. And then this is one locus that you have. The other is that the argument of z from 2 iota, what's the point 2 iota? This is the point 2 iota. From this point, the argument is supposed to be pi over 6. You draw a 30 degrees line from that. Now that does not have to be very accurate, 30 degrees line. That will be approximate and that's okay. So this angle is pi over 6. Okay. And now we are supposed to represent this number P in the form re raised to power iota theta. How can we do that? We have to find the modulus of this number and the argument of this number. What's the modulus going to be? Let's figure out the angles. Do we know the angle? Since we knew that it's perpendicular bisector of this original line had an angle of had a gradient of -1. Its negative reciprocal would be a gradient of 1. Gradient of 1 lines have an angle of pi over 4. So we know that this angle is pi over 4, right? It's y equals x line, as we said. The angle is 45 degrees or pi over 4. So the argument has to be pi over 4. We know that, right? What about the modulus? How do you find the distance OP? You could think of the angles like this. You could say, if this is pi over 6, this is 90 degrees, or pi over 2. Pi over 2 plus pi over 6, that total angle becomes 2 pi over 3. Sorry about that. That total angle becomes 2 pi over 3. This angle at the bottom is pi over 4. You can find the third angle as well. You've got 3 angles in that triangle, and you know one side, this side is 2 units. So you can find the side OP using sine rule, and that gives you the result. That's what you were looking for. That's the modulus of the point P. And then you can write that in re raised to power iota theta form. No, you can't do this from the graph. You have to do this by calculation. You cannot measure from the graph or mark or take the point from the graph. That's not allowed. It would not be so accurate in any case. 3 significant figures, you can't get an answer to 3 significant figures from a graph that does not even have a grid, right? So you can't do that. Okay, now the first 2 parts of this question are really straightforward. You have to find modulus and argument of them. And then in the last part, you see, they're saying the roots that we got in the first part, you have to show that they also satisfy this equation. Z raised to power 6 equals -64. How do we do this? Evaluating such big powers of Z is going to be pretty long if you do this power 6 right? You'll have to use binomial expansion, and that becomes fairly complicated then, fairly long. You'll have iota raised to power 5, iota raised to power 6, right? So how do you deal with problems like these? Remember I said evaluating powers is simpler in re raised to power iota theta form. They made you find the modulus and argument in the second part for both of those roots. You can write those roots in this form: re raised to power iota theta form, 2e raised to power iota power 6, and 2e raised to power minus iota power 6. You write those numbers in this form. And then you input these numbers in this equation to see if they satisfy or not. So convert them to re raised to power iota theta form, and then you input them in that equation, this equation. Now simplify this, evaluate the power. When you evaluate the power, you end up getting this. Now, how do you know that this is equal to minus 64? Now you go back to the cos theta plus iota sine theta form from this, right? R into cos theta plus iota sine theta form. Simplify that, put this on your calculator, and sine of 5 pi is 0. Cos of 5 pi is minus 1, and that gives you minus 64 equals minus 64. Do exactly the same thing for the other root as well. Convert it to re raised to power iota theta form, input that in that, and then you go back to the other form to simplify that, and that proves that this satisfies the other equation, this equation as well, right? So when you have large powers, like big powers like this to evaluate, using the re raised to power iota theta form is much more efficient. Okay, this is another example. You can have a look at this. Sometimes you have to use trigonometric identities and complex numbers as well. Very rare, but you may end up having to do that sometimes. You can have a look at this working. It's just trigonometry. Okay, so W in the second part, they said that W has modulus 1 and argument 2 theta. So that W minus 1 over W plus 1 is iota tan theta. Now, since we have to say that I have to convert it to tan theta, that means trigonometry is involved. So we write it in the r cos theta plus iota sine theta form, right? And that becomes this. Then we just input that in this form and simplify that, use the double angle identity, simplify everything, and try to, get to that form that we want, iota tan theta, using trigonometry. You can have a look at this working. I'll move on after this. Okay, this step is important. So at one point, I got this tan theta into this whole thing. And now the final result that we want, that has iota tan theta. So they want an iota in the numerator, right? To make that process quicker, what I did here was I said, okay, I want iota tan theta in the numerator. So let's multiply and divide by iota. Iota is just a number, right? So we can multiply and divide by iota at this step. This is what we want, and everything else we want to just cancel out somehow, right? So you simplify the denominator, and that gives you this, and then you get some cancellation that happens there. Okay, let's move on. You can have a look at this working. This is another example. You draw this locus. In fact, this is the other way out. So in this case, what happens is they give you a shaded region on the diagram. This is part of the question. They give you this part shaded like this. And then they say find two inequalities in terms of Z that define the shaded region. How do you do that? How do you write down two inequalities yourself? How do we think about this? We have a circle. What's the center of the circle? -2 and 1. In complex number form, we can say that's -2 plus iota, right? That's the center. What's the radius of the circle? That's 3 units. So we have to be inside the circle. So we could say, we could write down the equation of the circle like this: modulus of z minus 2 plus iota, that should be less than or equal to 3, because we have to be inside the circle. That's one inequality that we get. We put an equal to sign here because they're saying the boundaries of the region are included in the shaded region. So we put an equal to sign there as well. And then what else? The shaded part is below this line. This line that we've got, the shaded part is below that line. Now, what is this line? It's y equal -1 line. Now, in Eigen diagram on the vertical axis, we've got the imaginary part, right? So we can say that's imaginary part of z equal to -1. We have to be below this line. So we say imaginary part of z is less than or equal to -1. Sometimes we have to do this as well, that they give you uh, a shaded part themselves, and you have to write down the inequalities from that. So you have to write down the inequalities. So in this case, we had modulus of z. This is the standard format, z minus some expression, modulus of that is equal to r. That's the standard form of a circle that we discussed earlier, right? So center is -2 plus iota. We put -2 plus iota there. Radius is 3. We put 3 there. But instead of being equal, we say it's inside the circle, shaded part. So we put a less than equal to 3. We put less than equal to sign there because we have to be inside the circle. All right. Hope that makes sense. And then for the other one, we got imaginary part of z less than or equal to -1, right? Then they say find the greatest value of modulus of z for points in this region. Now, what about the greatest value of modulus of z? Modulus of z means distance from origin, So we start from here. What's the greatest distance in the shaded part? What's the greatest distance in the shaded part from the origin? Is this the greatest? No. You can keep going further and further until you touch the touch the shaded part on that extreme end, like that. That's the greatest value of modulus. How do you find that? How do you find this distance? That's quite complicated. Now, a quicker way of doing such things, if you can't think of something more efficient, you can use the equation of circle form from paper 1, if you remember, to find this point. And then you can find the distance easily after that. How do you find this point? You know the y coordinate. The y coordinate is -1 at this point. Do you know the equation of the circle in coordinate geometry form? X minus a whole squared plus y minus b whole squared equals r squared. Sometimes that becomes very helpful in these first sense. Center is 2, -2, 1, radius is 3. We could say the equation of the circle becomes this. Now, when y is equal to -1, find the value for x that you get. The value for x that I get is this, -4.236. That means that's the x coordinate of that point. So that point that we're talking about is -4.236 and -1. Find the distance of this point from the origin, use Pythagoras or the distance formula, and that gives the distance. That's 4.35, and that's what we were looking for. So sometimes when you're looking for the point of intersection of a circle in an Argand diagram, it helps to use that coordinate geometry equation of circle form to find that point, and that makes things easier. Okay, it'll take a few steps, but it's not that long that it takes. Just a few steps, easy steps, rather than spending a lot of time thinking about another more efficient method. You will spend a lot of time thinking there. Just use that equation of circle form to find that point, and then it becomes very straightforward after that. And this is another example: cos of pi over 7 plus iota sine of pi over 7 whole raised to power 4 divided by this. We need to find the exact value of argument of this complex number. Two complex numbers are divided. When two complex numbers are divided, what happens to their arguments? What happens to their when two complex numbers are divided, what happens to their arguments? Their arguments are subtracted, right? Now, what are the individual arguments? Argument of the numerator. What's that? We can use the De Moivre's theorem that I told you about. Multiply 4 with this. Argument of the numerator is 4 pi over 7. Right? That's the argument of the numerator. What about the denominator? We have a negative sign here. That means it's minus pi over 7. You subtract from 4 pi over 7 minus pi over 7, and that gives you 5 pi over 7. That's the argument of u. That's what you were looking for. Alternatively, you could convert it to r e raised to power iota theta form, and then evaluate that power. That's also not that difficult, right? Evaluate power 4, that gives you the argument that's 4 pi over 7. For the denominator, it's obvious as the argument is minus pi over 7. You find their difference and you get the result from that. Okay, I'll answer questions in a few minutes once we're done with them. Done with it. I think there are only a few examples left. Now, this is something that they ask about a lot. If you have a complex number u and its conjugate, a complex number and its conjugate, they're always reflection of each other in the x-axis, right? Because the imaginary part is opposite. So if you have one point here, the other point will be on the other side. It's always reflection in the x-axis, or you can say reflection in the real axis. So if argument of u in this case was 5 pi over 7, that's in the second quadrant here, right? 5 pi over 7, that's greater than 90 degrees, greater than pi over 2. That's 5 pi over 7. What about the argument of u conjugate? That will be here. On the negative side, that becomes minus 5 pi over 7. That's the argument of u conjugate, and its reflection in x-axis. Okay, this is a recent question that you can have a look at. Z equals 1 plus y iota. You have to find 1 over z first of all. That's just using conjugates. In the second part, they say, show that a minus 1 over 2 whole squared plus b squared is equal to 1 over 4. Now, what does that mean? This form that we found in the first part, that was a plus b iota. So this was a and this was b. No, this was not b. This whole thing was b, right? Including the negative sign. They're saying, show that this is equal to 1 over 4. The left-hand side is equal to 1 over 4. So what we can do is we can just, input values in this, simplify everything. It requires some simplification, and eventually things get cancelled out and you get 1 over 4 as the result. That's what you have to prove in this case. That the left-hand side equals 1 over 4. Now you have this locus to draw. That's pretty straightforward. Now this is important. In the previous part, what we've done is you have drawn this locus that satisfies these two equations. Real part of z is equal to 1, and the modulus of z minus 1 over 2, that is equal to 1 over 2. This is a circle, radius 1 over 2, center at 1 over 2. Real part of z1, that's this vertical line. Now, these are the two loci that are given by these two equations. Now they're saying the complex number z is such that there's a complex number z such that the real part of z is equal to 1. That's this condition, right? Use your answer to part B to give a geometrical description of the locus of 1 over z. Now, how do we think about this? In the second part, we have shown that a minus 1 over 2 whole squared plus b squared, that is equal to 1 over 4, right? That's what we have shown in the first part and in the second part. Now, what does this look like? A minus 1 over 2 whole squared plus b squared, that equals 1 over 4. Does that form look familiar? That's the form for equation of a circle, right? X minus a whole squared plus y minus b whole squared equals r squared. So it's very similar to that. A represented the horizontal axis, A represented the real part here, B represented the imaginary part here. So this is the form of equation of a circle, such that the center of the circle is 1 over 2 and 0. And radius is what? Radius is square root of this, that's 1 over 2. So in the second part, the form that we were given, if we compare that with the standard circle equation form, the variables here are a and b, not x and y. If we compare with that, we actually get that it's a circle with radius 1 over 2 and its center at the point 1 over 2 and 0, that's actually the locus that you have drawn in the previous part, right? That's this circle. That's the locus of 1 over z that follows that form of equation of a circle. So sometimes we get these weird problems in some recent papers. This is another very different kind of locus problem that you'll find in a recent paper. And the complex number z satisfies modulus of z equals to an argument of z between 0 and pi over 4. Use the Eigen diagram below to sketch the locus of the points representing z. Now, where could z be? Modulus of z is equal to 2. So it has to be on the circumference of the circle, right? Center 0 and modulus 2. And the argument is between 0 and pi over 4. Now it has to be on the circumference. The argument is between 0 and pi over 4. That means 0 and 45 degrees. So we draw a 45-degree line here. Pi over 4 gradient line and a 0 gradient line. Now, what's the region that satisfies both of those conditions? You have to be on the circumference of the circle, and the argument has to be between 0 and pi over 4. That's this yellow region here. That's what satisfies both of those conditions. This is what represents z. On the same diagram, sketch the locus of the points representing z squared. Now, what is z squared going to be? When you square a complex number, that means it's z times z, right? Modulus will get multiplied, so that will be 2 times 2, then that's 4. What about the argument? Arguments get added. So argument of z squared is going to be 2 times argument of z. So argument of z squared therefore would be between 0 into 2 is still 0, and pi over 2, because pi over 4 times 2 is pi over 2. So the other one is when you have a circle of radius 4 units, a circle of radius 4, that's this outer circle, and the angle, the argument is between 0 and pi over 2, 0 and this line pi over 2. Which region satisfies that condition is this region, right? This is where both of these conditions are satisfied, this highlighted part. Now you can either get rid of the rest of it or make sure that you clearly show that this is the only part, the shaded part, that satisfies the condition. You can also just erase the rest of it because that's not needed, but erase the rest of it like this if you wanted, or at least just shade that part that satisfies the condition. Okay. Why is the argument of z squared until I think my iPad also wants to sleep now. I'm not sure what's happening to it. बस कर जो भाई क्या हो गया? Okay. Okay, so this is what we had, right? Argument of z squared would be product of argument of z squared would be the sum of the argument of z, right? Argument of z into z is argument of z plus argument of z. So that's 2 times argument of z. Now, if argument of z was between 0 and pi over 4, what about argument of z squared, then we multiply this interval by 2. 0 times 2 remains 0. Pi over 4 times 2 becomes pi over 2. So its argument becomes pi over 2 for that reason. Okay. You can have a look at this example. Express z squared in this form. You can see that working. In the second part, they're saying the complex number w is such that z squared w is real. Now, when they say something is real, that means it has to lie on the horizontal axis, right? That's what it means. And z squared over w modulus of that is equal to 12. Find the two possible values of w, giving an answer in the form r e raised to power iota alpha, where r is greater than 0 and alpha is between minus pi and plus pi. Now, how do you find w from this? Now, first of all, z squared w is real. That's what they're saying, right? We could say w is equal to r e raised to power iota alpha like this. Evaluate z squared w from that. We know the value for z squared already from the first part. Z squared w turns out to be this. Okay. Now they are saying it's real. Okay, it's real. That means it has to be on the horizontal axis. If it is on the horizontal axis, then that means that the argument would either be 0 or it would be pi, right? It either be on the right side or on the left side. So argument can either be 0 or pi. These are the only two possibilities that we have. And they're also saying that the modulus of z squared over w, that is equal to 12. Now, if using the modulus, we could actually find the modulus of w easily. That turns out to be 1 over 3, right? Because we know the modulus of z squared already. And from that, we can get the modulus of w. That turns out to be 1 over 3. What about the argument? The argument, as we said, could either be 0 if it's on the right side on the real axis, or pi if it's on the left side, right? So we could say this argument minus pi over 3 plus alpha could either be equal to 0 or it could be equal to pi. And that gives us the two possible values of the argument. One is pi over 3, the other is minus 2 pi over 3. And then you can say the complex number w therefore is either 1 over 3 into e raised to power iota pi over 3 or 1 over 3 into e raised to power minus iota 2 pi over 3. It's quite tricky the first time you look at it. You can have a look at this working again and understand what's going on. Since it said that it's real, it had to be on the horizontal axis, right? So that's why the argument had to be either 0 or pi. Okay, all right. This is another loci problem. You can look at the first part. That's pretty straightforward. In the second part, they say find the greatest value of argument of z for points in this region. Where will the greatest value be? When you touch the circle at the highest point here, right? That's where the greatest and the argument would be greatest. And now we have to find this argument. How do you do that? Again, if you can find this point somehow, that will simplify things for you. Now, there might be a more efficient way of doing this as well, yes, but that will require some thinking as well, right? So you can directly find that point using the equation of circle form, right? The equation of the circle, you know that you know that this point is x equals 5 because of that line that you have there. What line do you have there? Do you have that line? Yeah, perpendicular bisector of 0 and 10 that is passing through 5. So the x coordinate is known. You put that, you get the corresponding y coordinate. That turns out to be this. And then you can find the angle based on that, right? So this equation of circle often is helpful to find that point where the circle is intersecting with some line, the equation of circle from coordinate geometry, and then you can do the calculations after that. This is another example. In the first two parts are polynomials. Okay, this is another thing that they often ask you to do in complex numbers. Show that some number is a root of an equation, and that's a complex number, right? How do we do that? How do we show this? It has z cube as well, right? you would evaluate z square and z cube on the side first of all. So this is z, evaluate z square from that first. And once you have z squared, then you can multiply z squared with z again to find z cube. So you have z cube and z square. Then you input them there, and the iotas will get cancelled out eventually, and you'll get 0 at the end, right? So you have to show this working. Without working, you'll not get marks. You have to show this working, okay? Now, this is important. In this part B, they told you that this is one root of this equation, -1 plus 2 under root 6 iota. And then they're saying in the next part, the complex numbers z, which are roots of this equation, p of z squared equal to 0. Now, how do you find those complex numbers? First of all, we know this is one root, -1 plus 2 under root 6 iota. This is another root. They told us that x equals -3 is also a root. If x plus 3 is a factor, x equals -3 is a root. So we know another root. Since all coefficients are real here, the conjugate of this would also be a root. So we know the three roots of the previous equation. When p of z is equal to 0, the three roots that we have are these, this, and this. Okay. They're saying find the roots of this equation, p of z squared equal to 0. For that equation, that would mean we have z squared equal to this, or z squared equal to the other complex number, or z squared equals -3. So instead of z being equal to those solutions, we have z squared equal to each one of them. And then we find the possible values of z from this. How do you do that? If z squared is equal to this, we have to find the square roots of this complex number. How do you do that? Using the x plus y iota method. X plus y iota whole squared. Apply that whole process. You get the two square roots, and they give you this. These are two roots. Do the same thing for the other complex root. You say z squared equals that. Again, apply that process for finding square roots of that complex number, and you get two other square roots. These are two more solutions. And then you have z squared equals -3. This is easier. Take square root. When you take square root, you have plus minus. That becomes plus minus under root 3 iota. So you get 6 solutions in total for this. You had solutions of p of z equal to 0. They wanted solutions of p of z squared equal to 0. So whatever was the solution for z, we said z squared should equal them as well, and find the corresponding values of z from that then. Okay, that's another thing that can happen. Now we have this complex number. We know the argument of this complex number is -π/4. First of all, they say find the value of a and hence express z in the form x plus y iota. How do you find the value for a? First of all, you can write this complex number in x plus y iota form. Okay. As in split it into two. You have iota in the denominator, right? To be able to find the argument, you need x plus y iota form. You need the real part separate, the imaginary part separate. So you multiply and divide by the conjugate, and that gives you this form. Now, this is the real part, this is the imaginary part, including the negative sign, right? Now they're saying that the argument is -π/4. That means it has to be in the fourth quadrant here. -π/4. What's the basic angle that we get from that? The basic angle is π/4. So now we can apply that formula. We can say tan of π/4, that should equal the imaginary part divided by the real part. And then we get an equation from that. Solve that equation to find the value for a. We're getting two values of a here. They said that a is supposed to be an integer, so we only consider the integer value. Put that value of a back in this, and that gives you the complex number in x plus y iota form. So sometimes they will give you the argument of a complex number like this, and there will be something missing. This is how you would approach that. You will separate out the real part and imaginary part, and then you find the argument and find the argument in terms of that variable or that unknown, and equate that to the given argument. You have these complex numbers u and w, they're defined like this. They want you to find u squared over w. First of all, that's straightforward. You can look at the work for that. Now, the second part says state the least positive integer n such that both imaginary part of w raised to power n is equal to 0 and the real part of w raised to power n is greater than 0. How do you think about this? What's w? W is given to be 3e raised to power 1 over pi over 3 iota. What about w raised to power n? You can put whole power n on that, and that gives you 3 raised to power n and e raised to power n pi over 3 iota. What's the argument that you get from this? The argument is n pi over 3. Now, if the imaginary part of this is 0, that means it has to be on the real axis, right? It has to be on this real axis. Real part is positive, that means it has to be on the right side. It has to be on the right side of this. So it's on the real axis on the right side. Now on the real axis, what are the possible angles that you can have? You can have 0, you can have 2 pi, you can have 4 pi, and so on, right? They want the least positive integer value for n. You can try 0, you can put n pi over 3 equal to 0, that gives you n equal to 0. That's not what we want. What we want the positive value. You put n pi over 3 equal to 2 pi, and that gives you n equals 6. That's the least positive value of n that we get, and that's the final solution. Okay. Then you have this Argand diagram. You had to find this locus and then find the greatest value of argument of z. Greatest value of argument of z would be at this particular point. You can either find that point using the equation of circle and then use that to find the argument, or you could use circle properties by making a right angle triangle like this and finding this small angle here and then saying that angle at the circumference is half the angle at the center, and then find the argument by subtracting that number from pi. You can look at this working here and this. I am too tired now to explain this. You can have a look at this later on, not that difficult. That's all that we've got in complex numbers. I hope that was helpful. We will end this here. If you have any quick questions, you can let me know. Okay, logs and linear law. This is the next topic that we've got. Now, logs are closely related to indices. In fact, they're just another way. Okay, and before we start, you can actually go out and ask the kids to not make so much noise. Okay, so this is the next topic that we're doing, logs and linear law. Logs are very closely related to indices. It's actually just another way of writing indices. So we need to know indices rules for this as well. You will need to use them a lot in this topic. So let me just quickly remind you about them. If you have two numbers multiplying, two expressions multiplying, the bases are the same, the powers get added, right? If you have two things dividing and the bases are the same, the powers get subtracted. If you have two things multiplying and they have the same power, we can write that as a common power. Now, these work both ways, remember. In this topic, you will often find that you'll have to do it the other way around. If you have this expression, you can write it like this. For example, 5 raised to pi x plus 2, we can write that as 5 raised to pi x into 5 squared. Similarly, for the next one, If you had a raised to power x minus y, that could be written as a raised to power x over a raised to power y. So that means 3 raised to power 2x minus 1, for instance, we could write that as 3 raised to power 2x divided by 3 raised to power 1 like this, right? So we'll have to use these rules the other way around quite often. If we have two things multiplying with the same power, we can write that power as a whole outside. That's not true when you have a plus or minus in the middle. A raised to power m plus b raised to power m, that's not the same thing as a plus b whole raised to power m. Don't do that. If you have two things dividing with the same power, again, this power can be written as a whole outside as well. If you have a raised to power m and then whole power n, if you have a power outside the bracket like this, those powers get multiplied, right? And if you have something like this, you could write that as either this or this as well. For example, if you had 5 raised to power x whole raised to power 3, you could write that as 5 raised to power 3x. You could write this as this as well, 5 raised to power 3 whole raised to power x. You could write this as well, 5 raised to power x whole power 3. You could write one of those inside and the other outside the bracket. You will have to do something like this in some cases. For example, when you have to separate one power in some cases for doing some substitution. For example, in this case, if you had an expression like this, if you wanted to use a substitution for solving some equation, as we'll see later, 3 raised to power x. For that, you would want to separate out 3 power x from here. Now, this is where indices rules are going to be very important. How do you separate out 3 power x from here? So you have to write it as 3 raised to power something. First of all, 81, what's that? 81 is 3 raised to power 4. So we could write it as 3 raised to power 4 first of all. Now these powers can multiply. 3 raised to power 4 minus 2x, that's what it becomes when these powers get multiplied, right? And now we could break them down into two parts. We could say 3 power 4 divided by 3 power 2x. Again, what we want is we want to separate out 3 power x so we can replace that with u for using that substitution. What do we do now? 3 power 2x, we could write that as 3 power x whole squared, right? 3 power x inside bracket, and outside we have power 2. And now we could write that as u squared. The numerator could then be simplified to 81 if needed. And that's how you could write that in terms of u, right? So you'll have to use indices rules like this to separate out something power x sometimes for using a substitution, right? This is as complicated as it can get sometimes. Now, what are logs? Logs are just another way of writing indices. If you have, for instance, 3 raised to power 4 equals 81, these same numbers, 3, 4, and 81, they can be connected to each other in another form as well using logs. We would say log of 81 with base 3, that equals 4. It's the same 3 numbers, but they're connected using logs as well. That's another way of writing this index form. Now, how do we understand that? How do we understand that? Log of 81 with base 3, that equals 4. That basically means, so this notation means we're asking ourselves, what power of this number 3 is going to give us 81? What power of 3 gives us 81? That's what these logs mean, right? The base, we think of it like this. What power of this number gives us 81? It's 4, right? You can put this on your calculator. Log of 81 with base 3, you get 4 from that because that's the result that you got from this. That's how you understand logs. In general, if you have log of a base b, what does that mean? That means you're asking yourself what power of b is going to give you a. What power of b is going to give you a? Okay, that's what this notation means. Now, you need to be able to convert log form to index form. For example, if you have something written like this, log of 125 with base 5 equals 3. If you wanted to write that in index form, understanding what we know about logs now, we are asking ourselves, what power of 5 will give us 125? 3. So in index form, we could write it like this. We could say, let's take this 5 to the other side so that it becomes the base of 3 in the index form. And we get 5 cube equal to 125 from this. So in general, if you have log of a with base b equal to c, we could get rid of the log. So if you have log on one side and constant on the other side, and you want to get rid of the log, this is how you would do it. You take the base on the left side to the right side, make it the base of that number, in power form like this. That's how you can do this conversion. Okay, this is very important. You have to do this a lot when solving equations. For example, if you had this equation, you wanted to find the value of x from this, log of x base 2, that equals 5. What's the value of x that you get from this? You can take 2 to the other side, make it the base of 5 in power form, and you get x equals 32 from that. Now, these are important rules that you need to remember about logs. If both the numbers are the same, if the number that you're taking log of and the number that's the base, so this number at the bottom, this is called the base of the number, base of the log, and this is what you're taking log of. So when base is the same as this number, the result is always equal to 1. So log of 6 with base 6 is 1, log of 3 with base 3 is 1, log of a with base a, we can generalize it like this, that is always equal to 1. In general, that's equal to 1 with some exceptions. We'll see them. Log of 1 with any base in general, that is equal to 0. Log of 1 is equal to 0. Okay, because 5 raised to power 0 gives us 1, 7 raised to power 0 gives us 1. So that is why log of 1 with any base in general, that is 0. These are some two general rules that you should know about. Now, base cannot be 1. That will be problematic. Now, there's logic behind all of these, but I'm not going to that right now. We have these conditions for log. The number that you're taking log of, this number always has to be a positive number. It cannot be negative. It cannot be 0. You cannot take log of 0. You cannot take log of a negative number. And the base as well, base always has to be, base also has to be positive. Both these numbers, they have to be positive. For the base, we also have another condition that the base should not be equal to 1. Now, in your syllabus, you will not be worried about the base generally. The base would be given, or when you're taking log yourself, you will be taking log base e, which is ln or ln, or that's the only log that you will generally be taking yourself. So we don't generally have to worry about the base, but this number, need to remember, this number always has to be positive. Now, there's some logs that are used very commonly, and there's some notation that we've got for them. One is a log that has base e. Now, e is a number, just like pi is a number. Pi is 3.141 something. E is 2.71828. It's a number. It's a constant, right? It's a constant, but it's a special constant. It has a lot of applications, and it's found at a lot of different places in nature for some reason. This is a constant e. A log that has base e, we call this ln or ln. These are two different ways of representing this or pronouncing this, ln or ln. Log with base e. This is a short way of writing this. The actual function is log base e. This is just a short way of writing that. So whenever you see ln written, understand that means log with base e. Okay, it's also called natural log sometimes. And then there's another log that's used a lot in practice, which is lg, or when it just says log, that means the base in this case is 10. So whenever you have log base 10, there's a short way of writing that. You can just write lg or just log with no base. That means that it's log base 10 if the base is not mentioned. Okay, so these are two notations that we have, short ways of writing them. Because these logs are used a lot, we have these short forms so that we can write them quicker. ln, log base e, lg, log base 10. Now, in our syllabus, again, we can do everything without lg. We'll just use ln everywhere, right? Because we will be doing integration, differentiation of this later on as well. So we'll just stick to ln everywhere, unless a question uses some other log base. In that case, we could work with that. Otherwise, whenever we're taking log ourselves, we will always take just ln, log with base e. Now, If you have ln of x equals 3, how do you solve this equation? If you think of it like this, base of ln is e. So we could think of it like this, that's log base e of x, that equals 3. E goes to the other side, becomes the base of 3 in power form, x equals e cubed. When they want exact answers from you, you would write them in terms of e like this. If they want answers in decimals, you can write them in decimal like this, and that's your final answer. Now, we will need to be able to solve different types of equations using logs. That's one major thing that you have to do using this function. But for that, there are some laws of logarithms that you need to know about. First of all, you've got multiplication law of logarithms. What's that? I've written them using ln because that's what we will be using most commonly, but it works for any base. As long as it's the same base, it works. So in this case, if we had ln of xy, for instance, that means inside the log, we've got two things multiplying, then it becomes ln of x plus ln y. Outside log, it becomes addition. Inside log multiplication, outside log addition. That's called multiplication law of logarithms. For example, ln of 7x, we can write that as ln of 7 plus ln of x. Ln of this, that can be written as ln of x plus ln of 3x minus 1. Also the other way around, it works both ways. When you have multiplication inside, you could write it like this. When you have addition outside, you could write it like this as a single log as well. It works both ways. So if you have, for instance, ln of x plus ln of 5, you can write that as ln of 5x. You had addition outside, that becomes multiplication inside. Now, remember the condition. The rule only works when you have multiplication inside log or you have addition outside log. These are the only cases in which this rule works. If you have ln of x plus 7, you have plus inside log. You can't do anything with that. You cannot simplify this. It's not ln of 7x. It's not ln of x plus ln 7. None of these works. Ln is not a number that you can just multiply with x and 7 separately like this. It doesn't work. When you have plus or minus inside the log, that is something that cannot be simplified. If you have multiplication outside log like this, ln of x times ln 4, again, you cannot use the log any of the log rules here. It stays as it is. It's not ln of x plus 4. It's not ln of 4x. It's none of that. These rules only apply when you have multiplication inside log or addition outside log. Multiplication inside, addition outside. Okay. Similarly, we have division law. When you have division inside log, outside log, that becomes subtraction. So we have ln of x over y, outside log, that will become ln of x minus ln y. Okay, division inside, subtraction outside. This is how this could work on different examples. This will remain as it is. You cannot apply that rule here. This also will remain as it is. You cannot apply that rule here. Okay, so none of these is true. It's not equal to ln of 8 minus ln of 5, ln of 5. It's not that you can take ln common. No, you cannot do that. It's not that you can cancel out ln. Okay, so none of those things is possible, right? This will remain as it is. Okay, you can't apply this rule here. Okay, then you've got the power law of logarithms. What's the power law? If you have log of something and you have power on top of that, the power law says that this number can, whatever is there in the power, that can come outside and get multiplied here. So if you have ln of x raised to power 4, you can multiply 4 outside, and that becomes 4 ln x. If you have ln of 3 raised to power x, that becomes x ln 3, and that, as you might notice, is very helpful when you have x in the power. When you have exponential functions, when you have x in the power, that is where we use logs a lot, because in order to solve that equation, we want to bring x down, and logs help us do that. The power law, that can help us bring that x down here like this. Similarly, if you have 2 ln of x minus 5, we could apply the power law the other way around as well. We could take this number to the power. Again, it works both ways, this rule as well. If you have something in the power, you can take that outside and multiply this. If you have something multiplying outside, you could take that to the power like this. Okay, that's the power law. If you have ln of x whole cube, for instance, the rule does not work in this case because this is whole power. The power law requires that the power is only on this thing. Okay, it's supposed to be only on this thing. And now, if you had ln of x cube, for instance, that will become 3 ln x. That will be fine. That can work. If you had something like this, you'll see such problems when we go further. Ln of 5 into 3 raised to the power x. Now, you cannot use the power law on this yet because power is not on this whole thing. It's only on 3. You would first have to break it into 2 parts and write it as ln of 5 plus ln of 3 raised to power x, and that becomes x ln of 3. This is how you would break it. First of all, you apply multiplication law to break it like this, and then after that, you can use the power law, not before that. Now, this is something that you'll have to do a lot later on in integration and differential equations. Whenever you have an uh, an answer in which you have log as any of the terms, when you have multiple logs in the final answer, you would always have to write them as a single log term. Now, how would you do that? Using multiplication division laws. For example, if you've got something like this, 3 ln of x plus 2 minus 3 ln x, you have done some integration, let's say, and in the final result, you are getting this. You cannot leave it like this. You have to make sure that you write it as a single log term. How do you do that? In this case, both of these numbers are the same. These multiplication and division laws that we saw earlier, they only work when there's nothing multiplying outside. There's nothing multiplying outside here, right? There should not be anything multiplying outside, just 1 or minus 1. In this case, we've got 3 multiplying outside with both of them. We cannot use the division law yet. We can first, since both of these numbers are the same, we can take them common outside. So that gives us 3 outside. And then inside, we've got this. We've got minus outside log. Inside log, that becomes division. So we can write that as 3 outside times ln of x plus 2 divided by x. Another way of thinking about this could be that you take 3 to the power, and it becomes ln of x plus 2 whole cube minus ln of x cube. And then we apply the division law to write it like this. And then it becomes whole power. Then you can write 3 outside. Gives you the same result, but longer. When you have the same numbers, it's more efficient to take that number common outside. However, sometimes what happens is these numbers are different. For example, you could have something like this: 3 ln x minus 4 ln 6 plus 2 ln of x minus 7. And what you want to do is you want to write this as a single log term. How do you do that? Now, these numbers are different. You cannot take any of them common outside as such. So what you do is you, first of all, write them in the power forms. Take all of them to the power. So write 3 in the power, so it becomes ln x cube. Write 4 in the power, it becomes 6 power 4. Write this 2 in the power, it becomes x minus 7 whole squared. Now the numbers outside are gone. We can apply the multiplication and division law on this. When you have more than 2 terms, how will those rules apply? Whichever terms have plus, you can do this all in one single go. The terms that have plus, they will get multiplied in the numerator. So you have plus with ln x cube. So you have x cube in the numerator. You have plus with this term. You would have x minus 7 whole squared in the numerator here as well. This term has minus with it. So 6 raised to power 4, that will go to the denominator, and that will be divided like this. And then you can simplify this. That's that expression written as a single log term. So that's something that you have to do for every differential equation or integration problem in which you're getting an answer in terms of log. You have to write that as a single log term. Then you have to solve equations using logs. If you have so one possibility is you've got something as straightforward as this: 2 raised to power x equals 32. In fact, this is something that you've done in O-levels already. 32 is an integer power of 2. You could write that as 2 raised to power 5, and that gives you x equal to 5, because if the bases are equal, then the powers are also supposed to be equal. However, if that number was not a perfect power of 2, for example, if it was 40, how do you solve this equation? This is where logs can help. What we do is we take log on both sides. It's an equation. And in an equation, we can apply the same operation on both sides, right? So we apply log on both sides. So it becomes ln of 2 raised to power x, that equals ln of 40, right? We take log on both sides. Now, on the left side, why we're taking logs, by the way, because we've got x in the power, right? We want to bring x down. And logs can help us do that, because when we take log on both sides, on the left side, we have 2 raised to power x. We can apply the power law, bring x down, and that becomes x into ln 2. X ln 2 equals ln of 40. We can take ln 2 to the other side, and it becomes ln of 40 divided by ln 2. Put that on your calculator, and you get a result from that. That's the value of x that you get from this. Now, in these questions, they will always, not always, but mostly have a level of accuracy specified in the question statement, that you want 3 significant figures, 3 decimal places, 4 decimal places, whatever it is. You have to make sure that you follow that exactly what they're saying. Otherwise, they lose marks because of that. Don't round off values in your working too quickly, because that can make your final answer inaccurate, and again you can lose a mark because of that. Now there are different types of equations that you could get here. This is the simplest kind. You take log on both sides. Now another possibility could be that you have log on one side already and the constant on the other side. We have seen this example before as well. Ln of 2x plus 1, that equals 3. What's ln? Ln can be thought of as log base e, right? That's what it is. So we can write this as log base e. E goes to the other side, becomes the base of 3, and we get 2x plus 1 equals e raised to power 3. That's the equation that we end up getting from this. And now we can find the value of x from this, make x the subject, that gives you the solution. So when you have log on one side and constant on the other side, when you have log on one side, constant on the other side, this is what you can do, and that would give you the result. Take this example. You could have some other base like this as well. Log of 3x plus 1, base 4, that equals 2. Base is 4. You take 4 to the other side and make it the base of this number in power form, and that becomes 4 squared. 3x plus 1 equals 4 squared. That gives you the value for x. X turns out to be equal to 5. Okay, let's move on. Now, sometimes what happens is you've got a single log on both sides, right? You've got log on both sides now. Ln of 2x plus 1, that equals ln of x plus 7. Now, when you have a single log on both sides, what you say is you've got log of 2x plus 1, you've got log of x plus 7, and they're both equal to each other. If the log of these two numbers is equal, that means that these two expressions should also be equal to each other, right? Only then their logs will be equal to each other. Those expressions themselves are equal to each other. So if their logs are equal, we say that those expressions are equal as well. 2x plus 1 equals x plus 7. In that case, of x equals 6. Okay. Now, that does not work directly when you have multiple log terms. You cannot just get rid of log here like we did in the previous example, because on the right side we have two logs. It's not log of one whole thing. We have to convert it to a single log term first of all. How can we do that? So when we have multiple log terms in this case, we have to make them a single log term on both sides. On the left side, it's already a single log term. On the right side, if we have minus outside log, we can write that as division inside log, so it becomes ln of x over 5 like this. And now, if this is equal to this, then the expressions inside, they should also be equal to each other. So x squared minus 1, that should equal x over 5. And that gives us the value for x when we solve it further. Now, this is very important as well. We get two values of x from this. X equals 1.1 and x equals minus 0.905. Whenever we solve equations involving logs, we always need to check if the solutions that we're getting, they satisfy that equation or not. In the previous examples involving logs, we were just getting one solution. In that case, in the exam, you would only get equations that have some solution. So we're getting one solution only. So even if you don't check that, you get away with that. But when you have multiple solutions, you always have to check them, because there is a possibility that you end up having one value of x that does not actually satisfy the equation because of having a negative number inside log. So in this case, if you were to input minus 0.905 inside this equation, what happens is when you input it either here or here, both of the logs are becoming negative, right? The inner parts, the inner values are becoming negative. You input here, it becomes ln of minus 0.905. That's not acceptable. You cannot take log of a negative number. This equation will become undefined. So that value is not possible. Okay, you have to input that. It's not that always, whenever you have a negative value of x, you would always ignore that. No, that's not necessary. What if the equation was like this? Ln of x squared plus 1, that equals ln of x plus 2 minus ln of 5. In this case, if this was a solution, this would not be a problem, because if you input that here, the value becomes positive. The value remains positive. If you input that value of x here, the value inside log, that remains positive. So that's not a problem. So you won't always just ignore any negative value of x. You have to input that and see if inside log you are getting any negative value because of that. In this case, you are getting that. Even if one value inside log becomes negative, that is sufficient for it to be undefined. And we would say that we have to ignore that solution. So that's not possible then. Okay. This is not the same as x square minus 1 over x square minus 1 equals x minus 5, right? Don't do that mistake. We can only equate the inner terms when we have a single log on both sides like this and nothing else apart from that. Now, this is another case that you would have. You have log on one side, on the other side, you have a constant plus a log term. What about this now? How do you solve this equation? For equations like these, what you do is you take all log terms to one side. So you could say ln of x minus ln of 2x minus 1. So take log terms to the left side. On the right side, you just have 4 left. And now make this a single log term. You can apply the division law here, right? Apply the division law, and that gives you this ln of x over 2x minus 1. And now this is one of the forms that we've seen before. We've got one log on one side, a constant on the other side. We can get rid of the log because we know the base of ln, what's that? That's e. We take e to the other side, make it the base of 4. So we get x over 2x minus 1, that equals e raised to power 4. And now we just have to make x the subject. If they wanted an exact value, you would not use decimals here. If they wanted an exact value, you would keep e as it is. And you'll try to make x the subject. When you make x the subject, this is what you end up getting. And that's your final solution. If they want decimals, then you would just input this on a calculator and evaluate the corresponding decimal value from this. So x equals 0.505. That's the solution that we get for this equation. Now, sometimes you end up getting equations like these. 3 raised to power x equals 2 plus 3 raised to power minus x. What about this now? Now, taking log on both sides here is not going to be helpful. If I were to take log on both sides, ln of 3 raised to power x, since we have x in the power, we want to bring x down, right? If I were to take log on both sides, the problem with that is that I end up getting plus inside log. And that is something that cannot be simplified. There's nothing that we can do with that afterwards, right? So when you have an equation in which inside the log, when you take log on both sides and inside log, you end up getting a plus or a minus, that's mostly not going to be helpful because there's no way to simplify this further now. There's nothing that you can do after this. So taking log here is not helpful. So what do we do instead? In problems like these, we do a substitution. We could say we've got 3 power something here, we've got 3 power something here. Can we make them both 3 power x? Yes, we can write 3 power minus x as 1 over 3 power x, like this. And then we could use a substitution, let u equals 3 raised to power x. And now that equation becomes this. Solve this equation, multiply by u. That gives you a quadratic equation. Solve this quadratic, you get 2 possible values of u from this. Use a large number of decimal places here because this is not your final answer. Do not round off yet. These are the two values of u that we're getting from this. Once you've got these 2 values of u, you put that substitution back. 3 raised to power x is either equal to this, 3 raised to power x is, or 3 raised to power x is equal to this. You can take log on both sides now. For in these equations, in the first equation, if you take log on both sides, you end up getting this value for x. In the other equation, if you were to try taking logs, on the right side, you have a negative number. Log of negative number is not possible. So from the second equation, you don't get any answer because any positive number, you can take any power of that. The result can never be negative. It will always be positive. Even with negative powers of a positive number, the result is always positive. So this equation does not give us any solution. Okay. And the only solution therefore is 0.802. And that's our final solution. So for problems like these, for equations like these, when you have some number raised to power x somewhere, and there's some other powers of that same number in that equation, and there's a plus or minus. In that case, you have to use a substitution. Taking logs directly on both sides does not help. Sometimes they will tell you to use a substitution. Sometimes they won't tell you, and you have to figure that out yourself. This would not work. This is what you have to do instead. Use a substitution. Okay, let's take another example. If you had something like this, 5 raised to power 2x minus 1, that equals 2 into 3 raised to power x. How do we solve this equation? Now, in this case, we don't have that problem. We don't have a plus or minus, right? So in this case, it is okay to take log on both sides right away. right? There's no point of using a substitution. And in this case also, we have 5 raised to power something here, 3 raised to power something here. Using a substitution directly here is not going to help as well, because we've got two different bases that we've got here. So the simple way of doing this would be to just take log in both sides right away. In this case, we can do that because there's no plus minus in the basis. So this would not be a problem. We take log in both sides, we bring this power down. Remember, when we bring this power down, this whole thing 2x minus 1 has to multiply with ln 5. Make sure that you're using brackets there. On the right side, we cannot use the power law yet. We'll have to break it down first of all into two parts. So it becomes ln of 2 plus ln of 3 raised to power x, and then use the power law here to bring x down. So it becomes x ln 3 here. We've got ln 2 here. And now make x the subject, take all x terms to one side, everything else to the other side, take x common here, and then make x the subject. That gives you the solution. If they wanted an exact solution, this is what you could have. You could convert it to a single log term in the numerator and in the denominator. And for this, if they wanted a decimal answer, then in that case, you would just write your answer in this form at the end. And that's your final solution. So if they wanted an exact answer, in this case, sometimes in the recent papers, they want you to write answers in this form, ln A over ln B. So in this case, if you had to do that, you would, in the numerator, say this becomes ln of 2 times 5. In the denominator, you could take 2 to the power, so it becomes ln of 5 squared minus ln 3. And then you could use the multiplication and division laws. In the numerator, you have ln of 10. In the denominator, you have ln of 25 over 3. You could do something like this. That's ln of A over ln B form. So sometimes you may have to convert it to this form as well. You should be able to do this. Okay, one log in numerator, one log in denominator. If they wanted decimals, like in this case, then you would just do this 1.09. Make sense? Okay, let's move on. What about this equation? Let's have a look at some examples now, some from recent papers as well, which are a bit complicated. But let's look at this. We've got log on one side and on a constant on the other side. Could we take e to the other side, make it the base of 1? Not yet, because we've got this 2 here. What do we do with this 2? There are two options that we've got. One is that we take 2 to the power and write it like this, but that's going to complicate things. We avoid taking these numbers to powers as much as possible, because if you were to take it to power, that will make it a quadratic expression and that will complicate things. Instead, the easy way of doing this would be that you first of all take 2 to the other side to make it 1 over 2, right? Rather than taking it to the power, using the power law here, just divide it on the other side, so it becomes 1 over 2. And now we know the base of log is e here. E goes to the other side, becomes the base of 1 over 2, and we have e raised to power 1 over 2 there. And now we just solve this further. Remember, this is just a number. E is a number, just like pi is a number. So e raised to power 1 over 2 is a constant. We have to find the value of x from that. How do you do that? You have to make this x the subject. How do you do that? You can take this term to one side. So this is what I've done. I've taken e raised to minus 2x to the right. Everything else on the left side. Now take log on both sides, because we've got x in the power here. We can take log on both sides. In this case, taking log is not a problem, because you might be thinking there's a minus here inside. So minus inside log, isn't that a problem? These are just numbers. 5 minus e raised to power 1 over 2. It is a constant. These are numbers. So we can just put this on our calculator directly. Ln of 5 minus e raised to power 1 over 2. Evaluate that, and then find the value of x from this. On the right side, use the power law, bring minus 2x down. Ln e is just 1. That's something that you should remember. Ln e is 1. So minus 2x comes down, times ln e, you find the value of x from that, and that turns out to be minus 0.605. Having minus or plus inside log would be a problem if there was an x involved there as well. So in this case, there's an x. If we just have known values inside, in this case, we knew what the values are. In this case, we just put them on our calculator, and that will give us the result for that. Okay, let's have a look at this example. We've got 5 raised to power x minus 1 equals 5 raised to power x minus 5. How do you solve this equation? Again, we've got a minus here. Taking log on both sides is not going to help, because we'll end up getting log of 5 raised to power x minus 5, and that's not going to be simplified. We take log and so we can't do that. What do we do instead? We can use a substitution. Then how do we use substitution? We have 5 raised to power x here. We've got 5 raised to power x minus 1. Using the indices rules that we talked about earlier, we could say this can be written as 5 raised to power x divided by 5. On the right side, we have 5 raised to power x minus 5. Now use a substitution. U equals 5 raised to power x, and then solve it in terms of u first of all. Put that substitution back, and then find the value of x from that. Okay, so in problems like these, you have to use a substitution. Okay, taking log like this is not going to help because you would not be able to simplify that in any way after that. Okay, all right. We looked at this example earlier in modulus as well. When you have modulus involved along with logs, all you have to do is just split that into two parts, remove the modulus sign, put plus minus on any one of the two sides, and that gives you two equations. And now you solve these two equations separately. You can use substitution for this if you want, and then solve it further using logs like this. Okay, so when you have modulus, you just use that idea for modulus that you remove the modulus sign, put plus minus in any one of the two sides, and split that into two parts like this. What about this equation? If you have something like this, e raised to power x plus e raised to power 2x plus e raised to power 3x, how do we solve this equation? Again, taking log on both sides, is that going to help? No, because if you were to take log on both sides directly, you would have a plus sign in the middle. So what do we do then? Can we use a substitution? You've got e power something here, we've got e power something here, we've got e power something here. Substitution might be helpful. So we say e power 2x can be written as e power x whole squared, e power 3x can be written as e power x whole cube. And now we could use a substitution, u equals e raised to power x, and that becomes this equation. And now we solve this equation, take all terms to one side, take u common, that gives you either u equal to 0 or this quadratic equation. Find the values of u from them, put that substitution back, and find the corresponding values of x. In two cases, we are getting u equal to 0. E raised to power x cannot be 0. We try taking log on both sides, it will be log of 0, that's undefined. In this case, it's negative. Again, log of negative number would not work. So that's also not possible. The only value of x that we get is from the middle number, that's 0.481. You may in some rare cases end up getting inequalities to solve as well. For example, if you have 2 raised to power x greater than equal to 7, you want to solve this inequality, you would solve it like you solve any equation. 2 raised to power x is greater than equal to 7. You take log on both sides like this, and then you bring x down. So it becomes x ln 2 that's greater than equal to ln 7. And then you find the value of x from that. Now, when you're solving inequalities, I would recommend that you evaluate logs before you divide them on the other side. Evaluate them before you divide them. Why is that important? Because sometimes this value might end up being negative. So when you divide it on the other side, the inequality sign might have to be changed. For example, look at this case, 0.5 raised to power x greater than 2. You apply log on both sides. On the left side, you get x into ln 0.5. Now, if you were to just divide it on the other side as it is, ln 2 divided by ln 0.5, that would be wrong because you would keep the same sign in that case, right? If it's not visible to you, if you just put this on your calculator like this, if you just put this on your calculator directly, ln 2 divided by ln of 0.5, now you would not notice that this value was actually negative and you were dividing by a negative value. So before you divide anything on the other side or multiply anything on the other side, first of all, evaluate that expression. ln 0.5, when you evaluate that turns out to be a negative number. So when you divide it on the other side now, the inequality sign would reverse. Okay, that has to be reversed. And then you say the final solution is x less than minus 1. That's the solution that we get. So log is actually positive for numbers that are greater than 1. If you take log of a number that's greater than 1, that turns out to be positive. Log of 1 is 0. But if you take log of a number that's negative, if you take log of a number that is between 0 and 1, that results in a negative number. So you have to be careful with logs of numbers between 0 and 1 because they're negative. When you divide them on the other side, the inequality sign would have to be reversed. So my recommendation is before you take them to the other side, evaluate them. So you can clearly see that the number is negative if it is. Now, this is something that will help you in some more complicated problems later on in integration differential equations. Ln x and e power x, these are inverse of each other. You can try finding inverse of ln x, and you would see that. So remember, base of ln is e, right? If I take that to the other side, it becomes e raised to power y equals x. So the inverse function for ln x is e power x, and inverse function of e power x is ln x. These are inverse of each other. Now, since these are inverse of each other, if you have something like this, ln of e cube, that is just 3. If you have ln of e raised to power minus 2, that's just minus 2. Why? Because ln and e, they kind of cancel each other's effect. They're inverse of each other, right? You can use the power law here as well in this case. So in this case, that's not as complicated to bring. You take 3 out here, you take minus 2 out here, ln e is just 1, so you get 3 and minus 2. But this is helpful when you have it the other way around. When you have e raised to power ln 7, for instance. Now this is equal to 7. E raised to power ln 3, for instance, that's equal to 3. So this directly simplifies to 7. This directly simplifies to 3. Because of this reason, the examiner would not accept any answers as simplified if you have log as a power of e. So in the final answers in integration and differential equation, you should avoid having log as a power of e, because you can always simplify that further. Okay, never leave an answer in which you have log as a power of e. Okay, you should simplify that further. So in general, this is helpful to remember. The second one is kind of easily understood using the power law, but this e raised to power ln x, that is equal to x, because these are inverse functions, they cancel each other's effect. Okay. Now, the next thing that you need to know about in this topic is linear law. What's that? If you have y equals 4x plus 7, if you have a number like an equation like this, for instance, that's a linear equation, right? It has a y-intercept of 7, a gradient of 4, it would look like this. If you had a quadratic equation, y equals 4x squared plus 7, what would that curve look like? That would be a quadratic curve with a y-intercept of 7 and a u-shaped curve like this. Linear law says that you can draw straight lines for functions like these as well. You can draw straight lines for these as well. Now, how is that possible? That's possible by changing the axes. Instead of plotting x and y, we can plot something else that will make it a straight line. For example, in this case, if I were to change the axis in such a way that on the horizontal axis, I plot x squared, on the vertical axis, I plot y, then this equation actually becomes y equals mx plus c form. Because if you compare, in place of x, we are getting x squared here. So in the horizontal axis, we have x squared plotted. In place of y, we're getting y. So on the vertical axis, we've got y plotted. So it actually satisfies that y equals mx plus c form, and it becomes a straight line if you change what you are plotting on the two axes. That's what linear law says, that if you in some cases, if you change the axes, a non-linear function can actually be drawn as a linear function, as a straight line, by changing the axes. So in this case, we could say y against x squared. This is a terminology that you need to be aware of. Whenever this says something like this, some expression against another expression, that's a straight line or anything. What's written first, that is supposed to be what's plotted on the vertical axis. What's written second, that's supposed to be plotted on the horizontal axis. So in this case, y is on the vertical axis, x squared is on the horizontal axis. Now, what do you need to do with that? You will need to draw straight lines, not just draw, but think of drawing straight lines of non-linear functions and find their gradients, their y-intercept. For example, in this case, when we drew this straight line, for the straight line, you see, if you compare with y equals mx plus c form, the gradient of this line is 4, and the vertical intercept, the y-intercept, that is 7. So the gradient is 4 and y-intercept is 7. We could understand that from this form like this. Now, sometimes we get exponential functions like this. For example, if we have 3 into 5 raised to power x squared, and they say show that ln y against x squared is a straight line. That's one thing. And then they want you to find the gradient and the ln y-intercept of this line. Okay, now first of all, let's stick to this. Show that ln y against x squared is a straight line. Now, how do you do that? The straight line form is this: y equals mx plus c. If they're saying ln y against x squared, what that means is on the vertical axis, what should we have on the vertical axis? On the vertical axis, we should have ln y. We represent that with capital Y. That's what we have on the vertical axis. On the horizontal axis, we have x squared. So the straight line equation is like this: y equals mx plus c. They want that in place of y, we have ln y, and in place of x, we have x squared. We want to convert this equation to a form like this, and then we can say that's mx plus c form. That's why it's a straight line. Now, how do we convert it to this form? We have log here, right? So we take log on both sides. This was the equation: 3 into 5 raised to power x squared. We take log on both sides. On the left side, we get ln of y. On the right side, we get ln of 3 into 5 raised to power x squared. Now, on the left side, we have what we wanted. We've got ln y. On the right side, we want this form: mx squared plus c. How can we have that? We can simplify the right hand side. It's a product inside log. We can split that and make it addition outside log, ln 3 plus ln of 5x squared, then use the power law to bring x squared down. So it becomes x squared into ln 5. And then you just rearrange this, write this term first, and you say that's ln of 5 times x squared plus ln 3. And now you compare it with the standard form, with the straight line form, which is y equals mx plus c. Since it is that form now, if in place of y we had ln y, in place of x we had x squared, and in place of the constant we had ln 3, we would get a straight line. We say it's y equals mx plus c form, so you would convert it to this form, and then say it's y equals mx plus c form. Writing this is important, that it's this form. That is why it is a straight line. That's what they wanted you to do first. Show that it is a straight line. Okay, so you convert it to y equals mx plus c form, and you write that down. Now they're saying find the gradient and ln y-intercept of this line. What about the gradient? Gradient is just this number. Whatever is coming in place of m here, that's ln 5. What about the ln y-intercept? What does that even mean? We have y-intercept. What is ln y-intercept? On the vertical axis here, we have ln y, right? So they're just asking you for the vertical intercept, right? What's that? That's ln 3. That's the ln y-intercept. We say that is ln of 3. The line would look like this, even though they've not asked us to sketch that here. But just for understanding, this is what it would look like. On the vertical axis, we have ln y. On the horizontal axis, we have x squared. This intercept is ln 3, and the gradient of this line is ln 5. And that's what it looks like, and that's how linear law is used. Let's take this example. You have a line given. The variables x and y, they satisfy this equation. The graph of ln y against x squared is a straight line. Again, the same variables, ln y on the vertical axis, x squared on the horizontal axis. And we know that the line passes through these points. Find the values of a and k corrected to two decimal places. How do you do that? How do you find the values of a and k? Now, first of all, you convert it to y equals mx plus c form. Ln y against x squared. So that means it has to be this form, right? Ln y equals mx squared plus c. How do you convert it to this form? We take log on both sides and simplify everything. You can see that here. And convert it to a format like this. And then whatever is the coefficient of x squared, that is the gradient. And this is the vertical intercept. Now, how do you find the values of k and a from this? They've given you that graph. We know 2 points on the graph. We have these 2 points. All you have to do is use those 2 points to find the gradient of this line. You can find the gradient of this line using those points. The gradient turns out to be this minus 0.419. And now the gradient that we are getting is minus k. So we say gradient equals minus k, and the value that we're getting from that, from those points that are given is minus 0.419. So the value of k that we have here is 0.419, and that's our final answer for k. What about the vertical intercept ln a? We can't find that from this diagram. It's just a sketch. It's not an accurate diagram for which we could find the value on the vertical axis here. So we can't do that. So what do we do instead? we say this is the equation that we've got now. Ln y equals minus kx squared plus ln a. This is the equation. We know the value for k already. Now what we can do is we can input one of those points inside this. Just like we used to do when finding equations of straight lines, y equals mx plus c. If you had to find the value for c, we used to input the values of x and y at any particular point. So in this case, that's what we do. We have the value of k. We write that here. That's the gradient minus 0.419. And we input one of those points here. Now, when we input those points, we have to be a bit careful. On the horizontal axis, we have x squared. On the vertical axis, we've got ln y. So these points that we are given, they do not represent x and y. They actually represent x squared and ln y. These are values of x squared and ln y. So x squared and ln y, when we input those values, for example, if you're inputting this value, in place of x squared, we would be inputting 0.64. In place of this whole thing, we put 0.64, not just in place of x. And in place of ln y, this whole thing we put 0.76. And then we solve that, find the value of a from that. We get ln a equal to 1.02816, and then base of ln is e. That goes to the other side, becomes the base of this number in power form, and you get the value of a from that. That's 2.80 to 2 decimal places. Okay. Sometimes they give you points like this on the graph, and you have to draw a line yourself, right? So you've got this grid. They did not give us these points. They only gave us, they did not give us the line. They only gave us these points like this. They were there on the graph. Now you had to find the values of a and n here. This is the equation that's given. You had to find the values of a and n in this equation. How do you do that? You can draw a line on this diagram here. From that line now, so in this case, this line is passing through every single point. Sometimes they say that the data is collected using an experiment. In that case, you might have to draw a best fit line sometimes. In this case, it's passing through all the points, so that's not a problem. But you may have to draw a best fit line sometimes as well. Now, when you draw a best fit line, you would be taking values from taking points on the line, not the original points, right? Like you do in experiments as well. When you draw a best fit line, you take points from the best fit line. You take points to find the gradient, and then just like before, we convert it to the straight line form. First of all, it's ln y against ln x. That means in y equals mx plus c form, in place of y, we want ln y. In place of x, we want ln x. So we convert it to that form. We take log on both sides and then simplify everything to convert it to this form, y equals mx plus c. And then the gradient in this case turns out to be n. So we find the gradient, equate it to that. And the y-intercept, the vertical intercept, that turns out to be ln a. Ln a equals 0.7. This is a grid that's given. So we could just find that value from this graph as well. That's turning out to be 0.7, and we equate ln a to 0.7. That gives us the value for a. Now, you can have a look at this example. It's not that difficult. I'll just leave it here if you want to have a look at in your own time. It's very similar. You can have a look at this. Okay. When they say a line intersects the axis of ln y, that means the vertical intercept, the y-intercept of the graph, that is ln y equals 0.5. What that means is they're giving you a point which is 0 and 0.5, right? So you could input that to find the unknowns there later on, like I've done here. Okay, now you can have a look at that. Now let's have a look at some recent questions. You got this. The number of bacteria in a population P at time t hours is modeled by this equation, where a and k are constants. The graph of L and P against t has gradient 1/20. So they've given us this gradient and intersects the vertical axis as 0.3. State the value of k and find the value of a correct to two significant figures. Now, how do you do that? First of all, you convert it to the standard form. Y equals mx plus c. What have they plotted here? ln p against t. So In y equals mx plus c form, we want L and P on the left side and T on the right side here. So we take log on both sides, first of all, convert it to that form. This is what we end up getting. Now in this form, the gradient is k. K is the gradient. So you equate that to 1 over 20. That's the gradient. And the vertical intercept, that's 3. So we say ln a equals 3. The value of a turns out to be e cubed. So we can find that easily, right? Like this. That's pretty standard. But now in the second part, they're saying, find the time taken for p to double. Find the time taken for p to double. What does that mean? Give an answer correct to the nearest hour. How much time does it take for p to double? Now, how do we think about this? Let's read the question statement again. The number of bacteria is modeled by this equation, right? We have the graph of ln p against t. On the vertical axis, we have ln p. On the horizontal axis, we've got t. T represents population, time represents, t represents time in hours. Time taken for p to double. Now, it's starting from 3, but what is starting from 3? ln p is starting from 3. They don't want ln p to double. They want p to double. So first of all, you should find out what the value of p is at this point. When ln p is equal to 3, the corresponding value of p that we get is 20.08. That's the value that we have in the very beginning. Okay. Then when does it double? You multiply that by 2. 20.08, you multiply that by 2. That gives you 40.16. And you now have this equation. In that equation, you can input, you got this equation, right? You know the value for k, you know the value for ln a, that a was 20.08. So we just input that here. And then we input p equal to 40.16 in this. And then solve that equation to find the corresponding value for t. That turns out to be 13.86. The question says you have to give an answer correct to the nearest hour. That becomes 14, and that's your final answer. In the previous part, they wanted 2 significant figures. So you had to make sure that you write a to 2 significant figures. What will be 2 significant figures for this? 20.08, it will just be 20, right? So this is a different kind of question that you see in the recent papers. Let's move on. Okay, question number, there's another question here. Now, in this case, they have this equation that satisfies this. X and y satisfy this equation. Show that the graph of y against x is a straight line. How do we do that? We want to convert it to y equals mx plus c form. How do we do that? We have x and y in the powers. We can take log on both sides so that we bring them down. When you take log on both sides, we end up getting this. And then we apply the power law. Simplify everything. Simplify everything. And now what you want to do is you want y equals mx plus c form. How can we get that? We want y the subject, right? We've got y here, we've got y here. So we simplify everything first. Simplify, take the y terms to the left side. Take y common, divide this on the other side now. Now, when you divide it on the other side, you want mx plus c form. These two terms separate. So that's why I've divided each term separately by this expression. It becomes 2 ln a plus ln b in the denominator for this and this here. Now, since a and b are constants, the question tells you that a and b are constants. That means this whole thing is a constant. This whole thing is also a constant. So that's y equals mx plus c form. That's a straight line. Okay, so sometimes you have this complicated algebra like this as well. Okay, so that's what we get from this. In the second part now, it says, given that a is equal to b cubed, state the equation of the straight line in the form y equals bx plus q. Now, how do we do that? A is equal to b cubed. This was the original equation, right? A and b were constants. Now they're saying a is equal to b cubed. This was the equation that we got here. Now, how do you write the equation in that form? Y equals px plus q, where p and q are rational numbers in the simplest form. We've got both A and B in these expressions. If we convert A to B or B to A, we'll just have one variable. So in this case, what I've done is I've said A is equal to B cubed. So let's replace all A's with B cubed. So in case of this A, we can write B cubed like this. Right? In place of this A, we can write B cubed. In place of this A, we can write B cubed. And then once we have everything in terms of B, we can simplify that using power law. We simplify the denominators, then L and B and L and B, they get cancelled eventually, and we get an equation like this. And that's our final answer. So sometimes you will see in recent papers, you get complicated examples like this. Okay, one last example. Positive numbers P and Q, they are such that this is equal to this and this is equal to this. Now, you will only be able to do them well if you have your concepts very strong for the laws of logarithms that we've got, multiplication law, division law, and power law, of course. They're saying, using this, express ln of p raised to power 7 times q in terms of A and B. Now, how do we do that? So what we want is this, ln of p raised to power 7 times q. Now you can think of this first, that what is it that we want at the end? Ln p raised to power 7 times q, that means this is basically ln p raised to power 7 plus ln q, and then that becomes 7 ln p plus ln q. This is what we want to find out. So if we can somehow find the value for ln p and the value for ln q, all we would have to do then would be input those values here, and we would get the result. Now they have given us these two equations. Now for the first one, we can apply the division law first of all to write it like this. This is one equation that we're getting. Simplify the other equation as well. Again, apply the multiplication on the left side first of all. It becomes ln q square plus ln p. Apply the power law, and that gives you this. Now we've got these two equations. We can just solve them simultaneously to find the values of ln p and ln q in terms of A and B. You can have a look at this working. What I've done is I've made ln p the subject here, put that in the other equation, and then simplified that to find ln q in terms of A and B like this. Once we have that, we input that back in this equation to find the corresponding value of ln p, and that turns out to be this. We've got ln p and ln q. All we have to do now is input those values in that expression, 7 ln p plus ln q, input the value for ln p, the value for ln q, and then simplify that to get the result that we wanted in terms of A and B. Simplify that, you get this 13 over 3 times A plus 8 over 3 times B, and that's your final answer. Make sense? So these are some of the more complicated questions that you would find in the research papers.